everyone. Good morning. We're going to get started. Welcome to the Harnessing Machine Learning Cross-Working Group. We have a lot of awesome talks today. Each speaker has about 15 minutes, which is their talk and questions. At the end of the first half, we do have ample time for discussion. So if you don't get to ask your question after the talk, feel free to save it for then. If you're online, please use Slido to ask questions, and if you're in person, please walk up to the microphone to ask questions. I think that's it. And we'll have our first speaker, Aman.
Oh, wait. It's just this. Okay. Hi, good morning, everyone. First things first, let me get the title straight. Sorry, that was too generic. I am Aman Gupta, and I'm a research scientist at Stanford University, and today I'm going to discuss our results from the newly developed deep learning parameterization for representation of atmospheric gravity waves in climate models. And so I guess I don't need to go through this slide in great detail, but essentially most of us might have encountered gravity waves in literature, or may have even encountered them in daily life. Essentially, they are fast-scale linear perturbations to a stably stratified atmosphere, which could be caused due to convection or uh-oh. Is there a pointer? It doesn't work. Oh, okay. Thank you. And these waves could be generated around strong thunderstorms, internal disturbances of a stable atmospheric layer, or even flow over mountains. Now, a typical life cycle of a gravity wave is, generated. A wave packet is generated through myriad of sources, and then it predominantly propagates in the vertical and grows in amplitude, encounters critical levels and breaks and drives the flow. Now, the representation of these waves in climate models have notable biases. So if we quickly look at this animation here, you'll notice a couple of things. These waves are generated over Andes, the Andean topography, but then they propagate, the wave packet propagates significantly, leaves waves. And as they move away from the source, they experience a change in wave number and orientation, and refraction in the wave. And then there's a temporal coherence to the packet, right? So these are the key properties that you would want a parameterization to represent in climate models. But then if you simply look at this wave again, sorry, I'm not able to figure out the pointer. But then for this given gravity wave phase structure, you would, if you explicitly compute the resolved fluxes, it would look something like this, but then a typical parameterization would give you a drag profile or a flux profile that looks something like this, disjoint, right? So there's barely any variability over the Southern Ocean, which what you would expect. And neglect of these properties leads to several biases. In the middle atmosphere, for example, erroneous QBO representation, delayed polar vortex breakdown in the austral summer stratosphere, even biases in the jet strength and the meridional overturning circulation in the mesosphere. And so in this work, what we essentially do is we create a deep learning parameterization which learns from high resolution observations the flux evolution of gravity waves, and then embeds, and then this scheme can be coupled to a dynamical core or an atmospheric model to then sort of substitute for the parameterization. And so the hope is that it can learn all the physics, all the prominent physical properties of gravity waves in the atmosphere, thus representing gravity wave effects with more fidelity. And so very simply what we do is we try to create a mapping between the background atmosphere, the background dynamical conditions, and the subgrid scale fluxes that a coarse model would usually miss. So we use ERA5 data, ERA5 reanalyses to compute the compute the fields. We coarse grain these fields, winds, temperature, horizontal winds, vertical wind, and potential temperature on from a 25-kilometer grid to a 280-kilometer grid, which is what a typical kilometer resolution would be. And then corresponding to that, we compute the subgrid scale fluxes. The direction flux is shown here, U prime, omega prime, V prime, omega prime. And then we, again, coarse grain them from a 25-kilometer grid to a 280-kilometer grid. And so we create this mapping where the input of the model is these coarse grained conditions, and the output of the model are the directional fluxes, the subgrid scale variability. And so we train a set of 3 models, sort of representing different degrees of non-locality. The first one, model M1, as I call it, is simply inspired from traditional parameterizations. You give it one column of data, like one column of input background field, and then it predicts the flux in that single column. The second model, M2, has slightly non-local, slight non-locality associated with it, where instead of one column, we give it 9 columns. So one central column plus 8 neighboring columns worth of input field, and it predicts the flux in that central column. So more information to predict the flux in the same column. And then on the other hand of the spectrum is this fully globally non-local model where we throw in all the information we have over all longitudes, latitudes, and pressure levels, and then we use a convolutional neural net to predict fluxes over all the latitude, longitudes. So it's like a one-shot prediction for the whole atmosphere. And again, we train it on 4 years of ERA5 data first, and then because ERA5 does not resolve the whole gravity wave spectrum, at least in the mesoscales, we complement it with 4 months of fluxes computed from a 1.4 kilometer IFS model from ECMWF. And we evaluate it on 3 key statistics. First is simply, how it performs in time, in real time. Like, what's the temporal evolution? Does it get the temporal coherence correct? Second is the seasonal averages. Does it get the seasonally averaged flux distribution correct? And the third is a histogram, just to look at the range of values the scheme can predict. I would quickly run through the results. I mean, looking at the first test, we look at 6 well-known gravity wave hotspots, both orographic, non-orographic. And what we notice, if you start from the mid-latitudes here, is that the 3 models compared to ERA5, like the predictions from the 3 models match pretty well with ERA5 in the mid-latitudes. We quantify it using the Pearson correlation coefficient, and they are pretty high, almost indistinguishable between the models. But then the problem is that the tropics have much lower correlation coefficients. If you look at the values, I hope they are visible. The single column model performs the poorest, and the most non-local model performs, provides the most accurate predictions. And so just to focus on the Drake passage again and kind of give a flavor of what the scheme is, predicting, like the horizontal structure of the fluxes. And you see that there's a clear, the scheme is clearly learning this horizontal propagation of the fluxes away from the topography. It's identifying the sources well, like the Andes, the Antarctic Peninsula, certain sources along the Southern Ocean. And then it's also, basically we get a coherent profile of the fluxes that match pretty well with the underlying training data. And similarly for seasonal averages, we look at the JJA June-July average mean. This is the ERA5 fluxes, and then these are the differences. So the 2 models, M1 and M2, that are single column and slightly non-local, they give reasonable predictions in terms of predicting the mean climatology. But then there's these notable biases around, notable errors around the steep Andean topography. But then those biases are again alleviated when they're not there for the predictions made by M3, with a caveat that there's certain introduction of the biases in the tropics. So that's okay. I mean, I'll discuss more later. And then the third test is just looking at the histograms of the fluxes, global fluxes predicted by these models. The left column shows the mean, the histogram of the means, and we see that there's a strong agreement between ERA5 and all the 3 models. So in a mean sense, they get the range pretty well. But then if you look at the daily samples, that sort of brings out a sort of a key flaw in these schemes, at least in our models, is that they struggle to predict like really small values. They're getting the tails right, and then again, UNet is performing better. The M3 model is performing better than M1 and M2, but then it fails to predict really small values. I'll skip this figure, but it's essentially saying the same thing. Now, what I've shown so far is step 1, where we only train the model on error 5, but it does not resolve the whole gravity wave spectrum. So now, step 2 comprises of transfer learning, where we retrain parts of the model on super high resolution 1.4 kilometer IFS data. And so now, if we look at this figure, so this is the climatology, or this is the seasonal average from error 5 for 2015 northern winters. This is the profile we get from IFS. Before transfer learning, we see a nice agreement between the predicted fluxes from our models, but then if we try to predict the same fluxes for error 5, we get notable weaker fluxes, right? The fluxes here are much weaker than here, so the model is not really getting the magnitudes correct. But after transfer learning, we do notice that the model learns the IFS climatology well, so it's like correcting the magnitudes based on its previous training and getting a distribution which is closer to what we see in the high resolution model. And then if we simply compare, if we run it again after transfer learning on error 5, we notice then again the spatial distribution is quite similar to what it was before transfer learning, but then now there's this correction of fluxes thanks to the transfer learning on high resolution data. So essentially, this shows that there's a possibility, there's a potential to mix different data sets, different high resolution data sets, to train a machine learning scheme that can, that would be more generalizable and kind of provide correct flux magnitudes throughout the atmosphere. I mean, I don't have, yeah, that's pretty much it. Do I have time? Yeah, so, I mean, we recently submitted this paper to James. It's under review. Please feel free to have a look at it. But essentially, I know I've sort of discussed a lot of information here, but essentially, the key takeaways are that machine learning trained on machine learning schemes trained on like higher resolution data tends to learn the physical properties of gravity waves and represent them, and possibly represent them better than the traditional parameterizations. Our transfer learning experiments indicate that different high resolution data sets, which are sort of sparse, not available for a long time interval, and so on. It's possible to combine different data sets to create a scheme that learns the best from all data sets. Now again, there's this limitation that I mentioned. We are working on it. Why the model fails to predict these really small values, which form the weak part of the gravity wave field. And then there's other tests we are working on right now, versus simply testing how our scheme performs on different model outputs from different sort of models with different underlying numerics, like the ICON model, for example, or high resolution vacuum runs. And then we are also trying to, we are also working on the most stringent test, which is what happens when we couple this scheme with the with the climate model, with CAM7 in this case. And does the model blow up? Does the model perform well? Do we get the QBO periods right? Do we get the stratospheric warming frequency right? Do we get the polar vortex erosion in the southern hemisphere, the timing of that correct? Yeah, that's a challenge we're facing right now, because coupling the M1 model is sort of straightforward, coupling it to CAM, but then coupling the M3 scheme, which requires collecting global data from all processors, is a challenge. But I've talked to some people here today during this workshop, and I've had some promising leads. So hopefully, we'll start working on it. Thank you.
Thank you for the presentation. When you went from M1 to M2 to M3, did you maintain the structure of your ML model, or did you change it? And if you changed it, are the improvements due to the non-locality or the difference in structure?
Yeah. So when we went from so between M1 and M2 have a very similar structure, with an exception that we have a convolution layer, a single layer in M2, which is not there in M1. And then we've tried to keep the hyperparameters as identical as possible. M3 is quite different from M1 and M2 because M3 is a convolutional neural net-based architecture. It uses something called as an attention unit. So it's completely different from M1 and M2. But then if you look at it, the training samples for M3 are much less than M1 and M2 as well. So the fact that it's performing, providing better results, even if the number of training samples are less, it's quite noteworthy.
My question is related. So for your M3, the UNet, it's more like treating a 3D field as 2D images with a segmentation, and the different images representing the different vertical layers. So I would guess it's very easy to reproduce this horizontal propagation, but have you ever looked at whether this machine learning model is reproducing like the vertical structure?
Yes, I don't think I have a plot here, but we looked at the variability and the vertical profiles. It matches pretty well. We discussed that in the paper. Sorry, I don't have it here.
Hi, Gupta. Very nice talk. So I have a question regarding, so do your machine learning model have any forcing input? Because like you are training the model using the era 5, say for example, present day. With the present day training, do your model have the capability to give the output for different kind of forcing, like historical or the future scenario forcing?
Yeah, I'm not fully sure. We don't have any forcing.
Because the system is not linear. I mean, it's non-linear
Yes.
thing. So your input have some sort of forcing thing so that it can do, like if the forcing scenario change, how it can change.
There is no climate change signal that we use in our training explicitly. The hope is, and I've not tested it yet, so I can't say for sure. The hope is that it learns the connection between the wind shear and the wind profile, and it learns the location where the waves dissipate. So I think that should, despite a changing wind structure in a changing climate, if it learns that, it should be able to provide plausible predictions, but yet to be tried. Thanks, great question.
Thank you.
Awesome. Whoa, he's allowed. I have a question for you. Great talk, by the way. So when you moved from M1 and M2 to M3, there's sort of a significant jump in complexity of the network. And thinking about your last point here, the technical aspects and also like the speed aspects of putting that back into a climate model are probably a significant jump. Have you done any testing on and off a GPU to see what kind of requirements this would put on the actual climate model when you're moving it forward?
Yeah, I haven't benchmarked the speeds yet, so I can't say for sure, but other people have sort of trained similar schemes on parameterization data, and they've found that they don't get a speed up, but they don't get a slowdown either. So it sort of remains the same. But then we are trying a new approach to couple the models to CAM, so we are hoping that it will be faster. But again, I can't say for sure. Maybe in a month I would have better answers. And in terms of M3 and M1 and M2, they don't have, they have very similar number of parameters. It's not radically different. So, and M3 is definitely faster to train than M1 and M2, maybe because of some optimized performance. I don't know, maybe it's a structure because the fields are like tensors rather than single columns. I don't know. But yeah, in that sense, they're not that different. So it's not like that the number of parameters are radically different that gives them an edge over the others. Yeah, thanks.
We'll move on to our next speaker. Our next speaker is Ram Saravanan.
So good morning. I'm going to talk about data-driven models for predicting precip. The first author is CG1, who's my grad student, who's not here, who's online. The photo is just an ad to publicize him. The other collaborators, Courtney Schumacher, Istvan Junyok, and Raymond Wong, all at Texas A&M University. So I'll talk about my philosophy of machine learning first. I'm a physicist. I'm a climate modeler. And I think of machine learning using this quote from William Gibson, which says, the future is already here. It's just not evenly distributed. And you can use that for many things. You can talk about EV adoption. You could talk about impacts of climate change. You can also talk about machine learning in the sense. When you use machine learning to predict, you're assuming Some part of the future is somewhere in the phase space. It could be in time and space, in the training data, and that's your motivation for predicting, using machine learning for predicting. And one way I think about it is that people say you can learn physical equations using ML or AI, and one of the fundamental equations is the Clausius-Clapeyron equation. It's going to tell you how intense precip is going to be. And if you look at the bottom, it's extremely complicated. And if you had data in that dotted box that you see there, and if you train a model on it, it might fit a quadratic or a cubic. It's not going to fit that really complicated looking expression. You need lab experiments and physics to do that. So machine learning has limitations, and but if physics-based model isn't working well or it's too expensive, I'm willing to consider machine learning. So those are the two cases I would consider machine learning, and I'll say those are the cases I'm encountering right now. So we know that machine learning models predict weather very well. I'm not going into the details of this plot. I'm sure you've seen it in many places. It's from WeatherBench. Typically, they predict geopotential, temperature, winds, things like that. Blue is good, red is bad. So there's a lot of blue out there. But precip is a different story. Machine learning models are doing precip, but sometimes they don't do it at all because it's hard. And sometimes they do it large scale. And if you want very regional precip, it's hard to do with machine learning. Okay, so machine learning is still not doing as well with precip as it's doing with geopotential, for example. And it's rapidly evolving, so someone might publish a paper tomorrow saying this is solved, but things happen very fast, but this is the current state. But precip is interesting. It happens on kilometer scale, and I was hoping to attend the other session to talk about kilometer scale modeling, but, and it's local. The local temperature, the local humidity, and some say local winds affect precip. Something happening 100 kilometers away isn't going to affect precip immediately here. It can affect it after some time. So there's physical concept of, there's no action at a distance in the physical mechanism of precip. So, and how we represent precip in a climate model with say 100 kilometer grid, we can't do the kilometer scale representation. So we do subgrid scale parameterization based on some physical assumptions. So the way it works is you run the model out to climate and look at the simulation of precip. And this shows climatology of precip and a persistent problem. I've been in this field over 30 years, and some of these problems go back a long time. And that one of them is the double ITCZ. And what you see here is the observations. There is no double ITCZ in this part of the Pacific, and models tend to do that. And this is a persistent problem, and physics-based approaches haven't solved that. Okay, so you might want to consider alternative approaches, and that's how I came up with machine learning. The other problem that physics-based models have is the high-frequency precip is not represented well. GCM drizzle rather than have intense rain, and in terms of climate change impacts, that's an issue as well. So physics-based approaches haven't done that well in simulating precip, and this is going back decades. So this shows, in this figure, what it shows is GCM's rain rates in the x-axis and frequency in the y-axis, and observations. The very high rain rates are not simulated by climate models traditionally. With ultra-high resolution, there's hope to improve it. Again, that's expensive. Okay? So if you don't have the resources, then what can you do? So the reason to do precip is that physics-based models still struggle with it. The other reason is there's lots of data. There's lots of satellite data. And the hope was that we can do pure data-driven models to predict precip. That was my initial question. This predates deep learning. Can we do precip prediction with just pure data and no physics? And why the 1D approach? I'm going to use a 1D approach, and that mimics GCMs. It has the physical properties. It has no action at distance. It has translation invariance. So what works in one region works in another region at different times. That's a fundamental physical property. And that makes it more generalizable for climate applications. So that's the hope here. So about 5 years ago, we did a basic statistical model using a technique called generalized linear modeling. And we built a statistical model to try predict precip using a column approach. And we did it for the tropical Pacific, where precip is very important to predict. We used logistic regression and gamma regression, and in the regions that are shown here. And then what we found was that the model the simple column model, statistical model, can predict the spatial structure of precip fairly well. So in terms of climate applications, it did a pretty good job. And we did different types of precip in this. And we used track satellite data using GPM and TRIM, so actual active sensors rather than passive sensors. That'll become important a bit later. So we used the best precip data we had and tried to predict it. And we used mirror reanalysis for the flow conditions. And so the model did a decent job predicting the spatial structure, but it still struggled with the high frequencies. It was a sort of a linear model. It tended to be Gaussian with some transformation, log transformations. So this shows, again, the model precip, drizzle, observations, high frequency, intense rain. And the generalized linear model didn't do much better than the GCMs. So that was the basic statistical approach. And then more recently, we started using deep learning approaches. We use something called over-parameterized networks, where the number of parameters vastly exceeds the number of data points. And this shows the loss function. And it's interesting that statisticians don't overfit, but in machine learning, that's pretty common. And it actually provides benefits. And we found that the over-parameterized model did pretty well. It did a lower error rate in predicting compared to other approaches like generalized linear models or random forest. The over-parameterized model did a better job in getting the error down in the two regions we considered for the 3 types of rainfall. It also got the high frequencies better than the generalized linear model. So we're making some progress with predicting precip using pure data and flow conditions derived from reanalysis. So this shows the, again, the rain rate, logarithmic percentile here. The observations is here, and the over-parameterized network is here, and the GCMs typically are here. So the over-parameterized network is getting the high frequency right, and also getting the mean more or less right. And then the idea was to see if we can actually go and put this in a GCM eventually. We're not anywhere close to that. But then we started building a model where we can use output of ML models for flow and try to predict rain. So that's the next step we're working on currently. So the plan is to use a 3D ML model, maybe GraphGAS or ForecastNest, get the flow conditions from there, and feed it to a 1D machine learning model, a column model of rain, and then try to predict. And we started doing it with ERA5 for input and the output, the flow conditions input, ERA5 rainfall output. And then we started thinking about doing a pure satellite product called iMerge. So we're working on it, and we're encountering some difficulties there, and that's what I'm going to talk about. So the data we're using is ERA5 quarter degree, and we have 4 years of training data and 4 years of test data. We're looking at summer rain in the Western Pacific. We have 13 levels. We use elevation, and we're looking at the Papua New Guinea region, so the elevation plays a role in affecting precip. And we also tried putting a lat long local hour as sensitivity studies to see if that affects the machine learning prediction. And initially, we did it with ERA5 to see if ERA5 data set can be predicted. And then later, we'll do it with the iMerge product, which combines GPM, TRIM, and IR to fill in gaps where the active sensors tracks are not available. We used multi-layer perceptron, very standard technique. This is some machine learning details. I'm not an expert on that. My student can answer some of the questions. But we had 3 million samples and 24 million parameters, so it's over-parameterized. And so the input is the flow conditions, TUV, relative humidity, output is precip. And initially, we're doing it just for ERA5. So the model, this model does a decent job getting the spatial patterns right. On the left is ERA5. On the right is the 1D model trained on ERA5. And it's getting the basic structures right just with a column approach. And we do RMSC and median absolute error. Again, the first column is using only TUV and relative humidity. And then we added lat long to see if that makes a difference to prediction. We used the hour of the day to see if we can get the diurnal cycle better with that. And then it didn't make a huge difference. The model was caring only about the flow conditions, not about these extra geographic or temporal parameters, which is a good thing, it's more physical. So we have translation invariance in the terminology of physics in this case. But if you look in detail, the model does well for synoptic conditions, large scale, thousands of kilometers. That's on the top, ERA5 and on the left, and machine learning on the right. For smaller scales, it's having difficulties. It's not doing as well. That's what you see at the bottom left is ERA 5 and write this model. So it's not doing that well with a smaller scale precip. The annual climatology, again, the model does a decent job, but there's some offsets, and it's probably related to how orography is represented. So the next step was trying to predict I-merge precip, which is more direct measurement of rainfall, with ERA 5 flow conditions. And what you see in the top row is just comparing I-merge to satellite data set in ERA 5 for 2 different days, and you can see the differences. So I thought we had good data for rain, but in some sense you don't have good data for rain. And that becomes, I mean, if you remember Jonah Shaw's talk from the first day, we don't have true data. All data are contaminated by some kind of model in some sense. And then we did a pattern correlation between I-merge and ERA 5 using different accumulation intervals. That's what you see at the bottom. If you average 1 hour up to 5 days, and there's a pattern correlation in the Western Pacific, and you can see they start to agree as they go to longer time scale, but they don't agree in very short time scales. Okay, so we don't know what the truth is for rain. And so this is actually my conclusion slides, which are preliminary, so we're still in the middle of this. So you can have an E to E model using ERA 5 flow to predict ERA 5 precip. Does a good job. But if you use the same model but try to predict I-merge precip, it doesn't work because the 2 precip are different. We have been trying to train a model, take ERA 5 flow input and I-merge precip. It actually doesn't work that well as the E to E model. Right? And that's where we are right now. And the way I'm trying to understand is that the small scale flow features in ERA 5 that are consistent with its own precip, but not consistent with I-merge precip. And if you understand how reanalysis works, it ensures consistency. And so small scale features in ERA 5 are also some kind of fiction. So we don't know the small scale flow features. We don't know small scale rain features because I-merge itself is a combination of passive and active sensors and involves retrieval, which involves assumptions. So in some sense, we may be able to predict only spatially and temporally smooth precip using machine learning because we don't really know the small scale features in time and space. I mean, I-merge is 30 minutes time, 10 kilometer grid, but I don't think we really know things on that scale. Smooth prediction may be okay for weather, but if you don't have these, the physical relationships there, it's more a statistical relationship, then you worry about how we'll generalize to climate. So that's where we are. Thank you.
I'll ask a question. Thanks for your talk. How did you come to the choice of over-parameterization?
There was an earlier paper where we didn't do that. It didn't do that well, and we found that it works much better. Yeah, it's more trial and error.
And what are the compute requirements of training something with?
These are one reason we did the 1D was very cheap. We can do it. I mean, it's negligible compute requirements. Yes, it's 1D model. This is basically unfunded research. We don't have big computer or time money allocations.
Very interesting talk. I was wondering, have you looked at using like those 20th century simulations, the output of UV and TQ, and your model to predict precipitation? Does it get rid of the double ITCZ problem that you mentioned at the beginning of the talk?
Could you say the 20th century analysis, you're saying?
Well, use the model data, the model UV.
Yeah, my goal was to do pure data, which you can realize I'm not sure we have pure data, but I didn't, when you use machine learning to emulate data, you get a model. When you use machine learning to emulate a model, you get a faster but slightly worse model. So I want better model. So
Right. I was just thinking, so you have this trained model that was trained to use observation and to predict the observation. But if you use the model simulated TQ-UV as the input and the same model, the same relationship that you find from the observation, do you get rid of some of the model predict precipitation biases, which would suggest potentially those biases are, like you mentioned, due to some of the smaller scale processes, parameterizations, but not due to maybe simulated flow field or something.
Sorry,
like that.
I'll talk to you later. I don't fully understand your question, but with ERA 5, we thought we were doing a consistent, because ERA 5 precip is controlled to some extent by the model. So it is consistent with the flow in era 5. So if we did this for a model flow and model precept, we probably do a decent job, I think.
Right. Okay, we can talk later.
Yeah.
Thanks.
Great, we should move on, so thank you. Our next speaker is Sene Van Loon.
All right. Yeah, I'm Sene Van Loon. I know the Van Loon name carries some weight at NCAR. I am not related to Harry, and I've never even met him, but same last name. So I'm going to talk about some work we've been doing at Colorado State, just north of here, together with Maria Rugenstein and Libby Barnes. We have a related paper, accepted in GRL, it should come out any day now. So recently there's been a lot of machine learning based climate emulators coming out that replace traditional climate models. And I say climate models, but it's at this point mostly atmospheric models that replace this with purely machine learning based things. The benefit of it is that it's fast and a lot of weather models have been coming out, but now also some of these models are stable on climatic timescales. So you can run them for 300 years without any problem. So one of them is the AI2 climate emulator ACE that has been trained on a couple different data sets. For example, FE3 GFS, the E3SM atmospheric model, and ERA5 data. And there's also the Camulator now that Will Chapman will talk about later. That's based on the credits architecture and trained on CAM data. But with actual climate models, we have since the 60s been trying to evaluate them and building trust slowly. And these climate emulators have been coming out over the last couple of years, so we need to be able to evaluate them to see if we can actually use them for scientific discovery. We propose one way of doing this using idealized patch experiments called Green's function simulations that are essentially SST-forced simulations with localized perturbations, and I will go into more detail. And we can call this some sort of distillation model of the emulator. So I will mostly be talking about ACE, the AI2 climate emulator, because the ratio was offline, as you know, last week, so I couldn't do these simulations in Camulator, unfortunately. So ACE is an autoregressive model that it's atmosphere only. I show here some of the inputs, and so forcing is SSTs, CI's fraction, incoming solar radiation, and CO2 concentration. So it's a typical atmospheric model that you can run AMIP simulations with. And it predicts, based on the current state of the atmosphere, it predicts 6 hours in advance. And that's what it's been trained on, just this 6-hour time step. And still, it's kind of impressive that just by learning the 6-hour time step, it's stable on century timescales and can predict a reasonable climate. So these are the 3 versions I've been testing. I've mostly been interested in the ERA5 version, so that's trained on reanalysis, but it's also trained on the E3SM atmospheric model and GFS. So the nice thing about these emulators is that they're very fast. You can get about 1,500 simulated years per day on a single GPU, as compared to way more with traditional models. So we can run these simulations very fast. So Green's function simulations, a Green's function in general is a way to solve a linear differential equation. So in our case, the differential equation is solved generally by a GCM. We do have to, this Green's function is a linear method. So how you find this G, the Green's function, is by forcing the model with localized delta functions pretty much. So in general, you get a forcing and a response, F and R, to a linear operator. But if you do this with these delta functions, you get the Green's function, and that represents a general solution of this linear differential equation. So what we do in atmospheric models to get to this Green's function is we run a lot of simulations. We start with just an annually repeating SST climatology. So this protocol has been described in this GFMIB, Block Johnson. This should be 2024 actually, but these simulations have been done in atmospheric models for a while now. So you start with this annually repeating climatological SST, and that's the baseline control simulation. And then you run these separate patch simulations. So on top of the annually repeating SST, you take one of these patches and increase the sea surface temperature in that location. It's usually a cosine patch, so it's kind of smooth. You run the simulation for about 10 years and calculate some value that you're interested in. I call this F here. So, and you subtract that from the control to get your average response to this localized patch perturbation over 10 years. And then you move on to the next patch and so on. And so there's about 100 patches here that you have to run for 10 years. So in an atmospheric model, this is quite expensive. It takes a couple of weeks to do these simulations, but people have done it. But in these emulators, we can do it in a couple of days. What you get then is you can calculate the so-called Green's function, or this is the response of a certain variable that you're interested in with respect to sea surface temperature. And so you can think of this as trying to calculate the numerical derivative of this variable that you're interested in with respect to SSTs. And so this Green's function really represents a linearized response to of the climate to SST forcing. So a little bit as a sideline, these Green's function simulations in the last couple of years have mostly been used to study the radiation budget of the Earth, and that's why we wanted to try this in these emulators too. In the global mean at the top of the atmosphere, the radiative imbalance N is equal to the rate of forcing plus the rate of response. The forcing is the excess energy we put into the system, and the rate of response is how the planet responds to that. And so only N, the rate of imbalance, is something we can measure, and to get the forcing and the response, we have to rely on climate models to get that. The rate of response is usually written as linearly related to global mean temperature, with lambda here the feedback. But this feedback parameter tends to change depending on how the SST warming occurs. So to move from this global mean feedback that changes over time to a localized feedback, we use these Green's functions. So this is an average Green's function map calculated in different atmospheric models. And so this is one of these Green's functions, and it shows that the local feedbacks. And so if you would multiply this with an SST map, you would get your radiative response. So instead of having this global mean lambda times T, we actually have a map of local feedbacks times the full map of SSTs to get the radiative response. And so this is what you get in atmospheric models. The hatching here is where the models do not agree on the sign, but in general, we expect these feedbacks to be negative in the West Pacific, where there's convection, and then positive in regions of stratocumulus decks, because if you, in these stratocumulus decks, if you heat the surface, you evaporate away the clouds, so you get a positive feedback, while in the West Pacific, for example, you tend to heat the top of the clouds in the East Pacific that actually stabilize those stratocumulus clouds and stabilize the atmosphere. So what does this map look like if we do this in climate emulators? This is what we get in ACE Era 5. And it looks surprisingly well. So it's trained on only Era 5 data. So it's closer to observations than we can get with models. And it gets the same features of negative feedbacks in the West Pacific, positive feedbacks in the East Pacific. And again, this was trained on 6-hourly data, and on climatic timescales, we get a reasonable looking Green's function map. If we do this in the EAM version, it also looks great, I would say. If we do this in ACE FE3, it does not look what we expect it to be. And in particular, you can really see the patch structure in this. Like, you can see where the patches, the SST patches were forced, which means that there's some kind of weird response going on in this model. We hypothesized that it might be due to these models not being, because this is a numerical weather prediction model, they don't have energy conservation. So this might be the reason that they don't get it. We can use these Green's functions to reconstruct the time series of the radiation. So again, this is this global mean framework, and by multiplying it with the SST maps of the historical that we observed, we can get the time series for R. This is what we get from the ACE Era 5 Green's function map, and I'll put these up here. The gray lines here is the predictions from that we get from GCMs, and that's what we expect. We expect this time series to go down because we force the system, so the response has to be we want to send out more energy. And so even though this ACE Era 5 and ACE EAM Green's function maps looked reasonable, if we use them to reconstruct the time series, it really doesn't work. The ACE Era 5 one actually has a positive trend, which is definitely not what we expect. The ACE FE3 one actually does better in the internal variability, but it has some weird decadal variations that shouldn't be there. So the question is, can we use these climate emulators for scientific discovery? I think we're not there yet. But if we could, they do offer some nice benefits. For one, we can probe the observed climate system in a new way. Because these Green's functions, in principle, they turn off the forcing. So it's been trained on historical climates where we cannot turn off the forcing, but these Green's functions offer a way of doing that. And although I focused on global mean radiation, I want to emphasize that you can use any variable that you want. And this is just as an example. You can study the effect of warming in the West Pacific on the 500 hectopascal geopotential height, for example. This is in ACE Era 5, and it looks kind of what we expect to. So even though we find a physically realistic sensitivity map in ACE, it fails to capture the expected negative trend in the radiation. And so we think this might be due to lack of energy constraints. And this is one reason we want to try this in the camulator, because it actually has physical constraints built into it, and you can turn it off and on again. So we want to do these Green's function experiments in camulator using with the physical constraint and without, to test this hypothesis. And in a sense, this looking at radiation is just because they've been used for radiation for a while now, but we do not know what this true sensitivity looks like. So even though we have some idea from the models, we do not know if this is the truth. Using Camulator, for example, we can actually compare directly with simulations in CAM. So finally, back to this idea of distillation model. These emulators really need systematic testing, and that can be done by doing forced simulation runs. There's multiple ways of doing it that people have been using for traditional physical models for a while. We argue that Green's functions should be part of this systematic testing, and so because they can distill this nonlinear statistical black box of the emulator. So just as if you would make your favorite whiskey, you take a distillation machine, you input the emulator, and out comes the Green's function. And so this is what you miss is all the nonlinearity, small scale features, short time scales, but what you gain is this physical understanding of these Green's functions. We have an idea how these Green's function maps should look like. We have an idea of how the climate should respond to a localized warming, for example. So for one, this is an out of distribution test because these localized forcings have never been seen during training. It's a linearized causal response, and they're physically interpretable. So I'll leave it at that. Thank you.
Thanks, that was really neat. I was wondering, so you said the training had never seen these responses. I feel like there's several examples where these emulators aren't getting good information about the Jacobian from training on time stepping. Do you feel like the way forward is to keep training on the time stepping, or do you need to include information about sensitivities explicitly in training?
That's a good question. It could help or it could not help. I think that's one of the things we need to understand, like how does it get the climatic timescales correct by training on 6-hourly time steps? I do not know. So it's one possibility to try to get that in there, but I wouldn't know how to, actually.
We are checking Slido, so if you have any questions online, please put them there.
A nice talk. This is more a comment than a question. I just wanted to highlight that the models we're training on, like the reanalysis system or the Earth system models, like they don't conserve energy for the right reasons. Like we use energy fixers, and regionally they don't really close the energy budgets very well. So it sounds to me we have some work to do in the traditional modeling space as well to train these emulators.
Yeah, that's fair. It is. It was just said that these emulators are always going to be worse than the training data we put in. And even if we have a perfect model, yeah, we need the correct training data, but we don't have it yet.
Great, thank you. We'll move on to our next speaker, Dave.
Okay, thanks. That was great. A lot of perfect talks to lead into this. So I'm going to try to motivate the group to be thinking about how we're to move towards a machine learning enhanced version of CSM, sort of taking advantage of a lot of these new machine learning capabilities that we're learning about to make a quantum step in the quality of CSM to build, essentially to answer that question, to build a better model for training for emulators. Probably won't get to the emulator part in this talk, but it's part of the overall vision here in the CSM activity. So I start with this slide in most of my talks these days, which is a figure from Veronica Eyring's perspective paper that I was a co-author on along with Pierre Gentine and others, which sort of outlines a vision for the sort of the future of Earth system modeling, next generation Earth system modeling. So if we go under the perspective that one of the there's lots of reasons we build Earth system models, right? But one of the fundamental reasons in the climate science world is we need to provide actionable, reliable, relevant, and accurate information for stakeholders, users of the data that are trying to make decisions related to climate change. If you say that's a core reason we're doing this, then we need these models to be getting better. So models have been getting better over time. CMIP 3, 4, 5, it wasn't a 4, we skipped it, 5, 6. The models have gotten better, but it's slow, like a painstakingly slow process to make these models better. The physics is getting better, but the quality of simulations is getting better at a relatively slow pace, although at least it's steadily getting better. And so the big question is, can we accelerate that using machine learning? Because the urgent need for this information. At the same time, there's kilometer scale models that are being developed. There's other high resolution models like LES or genetic numerical, which we know are providing, in a lot of cases, more accurate simulations for at least specific parts of the system. Less reliance on parameterizations. And at the same time, there's an increasing array of Earth observations. We know we're underutilizing them in the development of models and also in the evaluation of our models. And then also at the same time, we know that large ensembles are going to be required for us to understand the role of internal variability for trying to understand the uncertainty in climate change projections. So you cannot most likely rely on these kilometer scale models, even if they got to the same quality that we have now or had all the features, because it'll be almost impossible to run ensembles. Maybe with an emulator you might be able to get there. That's another question. But so in this world, then the framework we're putting forth is that we need to try to, well, we don't need to, but one option is to try to build hybrid models, which is combining machine learning based parameterizations and machine learning based calibration technologies to really make a step function change in the quality of our Earth system models. And so it's sort of the way all these kind of pieces of the model development world are working together: kilometer scale modeling, LES, Earth observations, and machine learning all coming together. And then you can then take that information and use machine learning again to do downscaling, regional refinement, et cetera, to drive impact models. So that's a framework. Fortunately, within CSM, we have these two pretty big activities: the Learning the Earth with Artificial Intelligence and Physics, which is the LEAP project. It's NSF Science and Technology Center. It's about a $25 million project. Hopefully, will be renewed for another 5 years. And then also the M-Squared Lines project, which is supported by Schmidt Sciences. And both these two activities are working to do exactly this, which is to bring new machine learning-based parameterizations or parameter estimation or optimization technologies into CSM to build the next generation CSM that will hopefully give us more accurate projections. So I'm going to start off with a few things that we've been doing. One is working on machine learning enabled parameter optimization. This is mostly coming out of the LEAP activity. And most of those of you who were here this, for Monday saw me give this slide. And basically we made a lot of progress within LEAP towards this. So on the land side, in both the land and the atmosphere, we've started there. On the land side, Linnea and Katie and Daniel Kennedy have been building up a set of tools that allows us to do parameter optimization and uncertainty quantification within the CLM. And that's drawing on some of the capabilities we've built up over the last few years to be able to really have a really fast version of CLM, which allows us to run large ensembles. And then we're using a history matching approach to kind of iteratively walk through and throw out parameter sets which are not matching up with our observations or not consistent with observations, and we can kind of iterate and focus in on the particular regions. I will say here we're getting strong evidence. I've seen this every time I've seen somebody try to take on the parameter estimation. Problem is it really requires not just all the smart math and machine learning based capabilities, but it needs the domain expertise of someone like Linnea or even the whole land model working group to really understand how to approach this. It's not just you throw math at the problem or you're going to solve it. It really needs to have this really in concert, the development of these technologies. So this work is going well. We're actually using it to calibrate CLM6 right now, of which we're going to CSM3, so the one machine learning based piece that's going to be in the CSM3 hopefully. And then on the CAM side, the work is kind of building off of work that was done originally with the GIST model to use 30 or 35 different, mostly reanalysis type data sets as calibration targets, and they have a set of methodologies to work on that. And then we've been adding to that in ways that I probably can't characterize very well here, but using this thing called the additive Gaussian process emulator, which is having nice features and trying to build that into the CAM structure. And again, we are using this not the full-blown set of tools yet, but we are using some of the capabilities in the sort of tuning and calibration of CAM. And I like to I think Linnea actually coined this first, machine learning assisted hand tuning. So we're still back in the Stone Ages, but we are at least using machine learning a little bit to assist us. So these are two nice activities that we're building these capabilities in. And one I'd like to show this slide is sort of saying one of the features that they're coming up with is they learned with the GIS work and is showing up in CAM too is that, when you first do a parameter sensitivity assessment of your model, you might find that there's some insensitive parameters that don't look like they're important, but actually they can either be cumulative important as you kind of look at when you add them together, or as you kind of zero in on the actual correct parameter space, you find that a whole bunch of parameters that weren't originally important become important. And we're also finding that some parameters are only locally or regionally sensitive, which is interesting, and that allows us to be starting to think about how you can target specific regions if you have a problem in CAM or a problem in the climate simulation with a bias. You actually have the possibility of, if you have a problem over Indonesia, we have a parameter here which can just target Indonesia, which would be kind of nice. So this is nice work. On the CLM side, I just want to emphasize this thing about we're using this for uncertainty quantification as well, and so you can sort of progressively bring in new constraints, observational constraints, to constrain, in this case, the land carbon trajectory, which is a really important uncertainty in the climate system. And so we can find out, go from this really unconstrained situation to a relatively constrained, and then we can then consider doing a few things. One is publish an observationally constrained perturbed parameter ensemble. So when we publish CLM6, we're going to publish 100 parameter sets for the community to use if they want to try to explore uncertainty. I think that'll be a kind of a new and unique and innovative thing that we're doing. And also we could consider a future CSM3 large ensemble that is, spanning across this uncertainty with, all these things being reasonable parameter sets, and we can, especially in emissions-driven mode, you could see really different behavior as you go from one of these that's, has a low carbon sensitivity to a high carbon sensitivity. So kind of excited to think about that. We could also span, using the CAM ensemble, different, ECS or TCR values. Okay, moving on to ML-based parameterizations. There's a lot of activity here, and so one of the activities that we started with is this machine learning warm main microphysics, an activity that was led by Andrew Gedman a few years ago, and now we're bringing it fully into CAM. And what we're seeing is that when you bring it fully into CAM, we can replicate some of the improved tail behavior that we're seeing in extreme precipitation, which is nice to see when you sort of replace this so-called tau microphysics, highly resolved tau bin microphysics scheme with a machine learning based one and put it into CAM, you can get good behavior. So that's showing that we can do this. Now in this case, we hard-coded this neural network into the model, and I'll get to this in a moment about why obviously that's not the way you want to go in the long run. Now it's work that DJ helped out. Well, I'm going to see him here in the front row. So and Adisu, who's in the audience somewhere as well. So, but one thing I want to point out here is that it's good to have these capabilities, and what we're hoping to see is a big step change in things. And so the model is going to hopefully, in some sense, look really different than it used to. And we know that in the past we've had to then calibrate it back, get all the things that we've calibrated, spent years, decades even getting the model to look right. If you make a huge perturbation to it, then it's going to take all your time is going to be spent getting the model back into some sort of a shape that you can use for. So I think it's really important to have this. This is an example. This is just an example. It's not an actual result, but just say maybe we've tuned our shortwave cloud radiative forcing really accurately in CAM. Then you throw in this new thing, and it all looks totally wrong. Cloud radiative forcing is again, and then you have to have the two experts in the world who know how to tune that back, and then you're stuck, right? And so the idea of having this machine learning auto-tuning is a really critical piece here. They need to go in concert. If you don't have this, I think you're going to be spending all your time recalibrating your model. So we're really trying to bring this, accelerate and push on this part of the problem as much as possible at the beginning, so that we're ready when all these new machine learning based parameterizations come in. Okay, in terms of those machine learning-based parameterizations, this is another figure from Veronica's paper, just sort of highlighting some of the possible ways. And everyone here in the room can come up with ways that you can potentially think about using machine learning to enhance a parameterization, replace a parameterization, either from a high-fidelity model or Earth observations. It kind of spans all different aspects of the Earth system. It only, this is only restricted by our creativity, in my opinion. There will be situations where it's not going to be useful, but a lot of situations where it could be useful. And so within the M-squared lines especially, and the LEAP projects, we've now have a set of parameterizations that are being worked on. And these are what I'm calling candidate parameterizations and tools for the CSM3 MLE. So what you can see is we have 10 to 15 different activities going on across the CSM community or outside the CSM community, which we think are possibly candidates for being included into this CSM3 MLE configuration. And so I'm not going to go through all of them, but just show that it's spanning the full gamut of the Earth system. We're sort of doing that intentionally, right? We don't want to necessarily just focus in on one aspect of the system. And at the same time, we've also built in these capabilities to use FTorch to couple between the machine learning based technologies that you have in a PyTorch package into the Fortran code. And so again, we're trying to make it easier for any of you out there who wants to bring a machine learning based parameterization in. You can do that relatively straightforwardly. And last, I want to mention that this cloud cover one is actually coming from the ICON group, and they're going to be working with us this summer to see if we can translate an activity that was going on in a whole different model and bring it over into CSM. Okay, so one thing that's happening though is as we looked at these 15 or so different projects, is that a lot of them were not making it, not making their way into CSM. And so why was that? Was because we didn't have these interactions with the CSM core development team that we needed. And so what we've done then is created this new layer of people, which is go from the LEAP and the M-squared line scientists, largely grad students and postdocs who are working on these activities, and then coupling into the CSM developers with this integration team. And Linnea and Will are on the integration team, and they're the ones who are really trying to make this really happen. And then we also have project management to sort of track what's going on. And one of the first things that this team is doing is going out there and asking each one of those groups in a lot of detail, like, a lot of these groups are saying, yeah, my parameterization's ready to go. And then you go, okay, is it ready to go? And say, what does that mean? And you actually say, okay, we have a little bit of conversation with them and realize that maybe they're not actually training on something that CSM is producing. So they've trained on something external, and and they say we're ready to go, but actually CSM isn't producing that variable, or so it's not actually consistent. So this team is going through and asking these detailed questions. We have survey responses for all these different 15 activities that really trying to get at the nuts and bolts, like where are you really in this process of being able to ready to go. So then, then we can start thinking about towards this machine learning enhanced CSM3 MLE, and I'm really careful about defining success. I'm an optimist, and I'm also a realist. Like, this is going to be harder than we say. It's really easy for me to get up here and say we're going to produce this. The reality is going to be harder than that, and the ICON group, who's a little bit ahead of us, is experiencing some of the challenges that we're going to run into. But we can define success however we want, right? And so we can define success as if we get a few ML-based parameterizations into CSM, and we can call that CSM3 MLE, and that'll be our first version. It's just our first version. We keep building on that. So it might be 1 to 2 in the atmosphere, 1 to 2 in the ocean, 1 to 2 in land. It could even be 1 in each one of those. I'd still call that a success. We have the capability to machine learning-based parameter calibration, so that'll be a feature, so that'll be cool to have. We won't have tackled the coupled calibration problem, which is intensely difficult, I think. And we're excited to think about that. And if anybody has good ideas about that, we want to know about it. That's going to be hard. We know that, but we will at least be able to do this calibration offline. And then hopefully we're going to have reduced biases, significantly reduced biases in critical fields, especially extremes. So here's the final slide. Push forward to the next 18 to 24 months to test this hypothesis that ML can build better, more accurate ESMs. And we're going to hear a lot about emulators. I think emulators are awesome. We're going to use emulators to do a lot of things like filling out ensembles, really fast simulations. But if you don't have a high quality and improving underlying core Earth system model, all that work isn't really going to be able to really make the most benefit. So we need these sustained team interactions, more coordination, and then anticipate there's going to be challenges. Machine learning parameterizations in and out of training climates is an obvious one. That's something that everyone is thinking about. There's probably going to be new instabilities when you add these in, unanticipated interdependencies, substantially new simulated climate that may degrade orthogonal aspects of the simulation. Almost for sure that's going to happen. And there may also be new tuning challenges as some of our traditional tuning knobs are removed when we've gone to this machine learning-based parameterizations. That's just another thing we may have to overcome. So I will stop there and take any questions. Thanks.
Any questions?
Extremely exciting progress there, Dave. I'll come back to the point, or an alternative approach that might be worth considering at some point, which is you've got a system which has got well-known fluid dynamical equations, the Euler equations, and then a gigantic sea of mystery meat on the right-hand side of those equations with a very long list of processes that have to be tackled one after the other after the other. And I do think it is worth considering hybrid models of a second kind, which is where we emulate the left-hand side, the fluid dynamics, and use traditional physics. It is worth perhaps exploring both. And we're very open to doing that in concert with other people. The advantage of doing so, there are two advantages. First is you skip going through this laundry list of mystery meat of physics parameterizations. And the second is that because high resolution is totally dominated by the dynamical core in terms of the computational performance of the model, this allows you to very quickly get to ultra high resolution with emulation of the fluid dynamics. And the fluid dynamics is something we can tell if you're getting the right answer for the right reason. Much of the stuff on the right-hand side, God only knows. So just that's more of a comment than a question, but I'm really excited to see CESM pursuing this direction. It will be one of only 2 models in CMIP7 that has taken this step. So I think it's a very bold step for CESM.
Yeah, thank you for that comment, and of course you gave this comment at the advisory panel, so we heard you. I have not yet adapted my slides to reflect that comment because we don't have any real activities on that, but I totally agree with you that that is an opportunity that we should try to pursue. I don't think we necessarily want to drop the machine learning based parameterizations as well, because that could still be added on top of that if you really can improve on the physics which is underrepresented or understood. You know, on land, for example, we just don't know equations for photosynthesis or whatever, fundamental equations. But yeah, absolutely, and LEAP is dabbling in this. The LEAP phase 2 is dabbling in this, exactly what you said. Probably not enough to bring it all the way to fruition, but yeah, but thank you, appreciate that.
Last questions before we move to discussion? Okay, great. Thanks, Dave. So now we have about 20 minutes for a general discussion. We have a question that we have for all of you. And I think what was clear in yesterday evening's session is that the community in CESM is what's really important. And as we move forward with our AI roadmap, we want to continue to engage. Your question that we have for all of you is what can NCAR do for you in terms of using machine learning in your own research or with CESM going forward? Nothing? Absolutely nothing?
A lot with machine learning. I'm wondering from a diagnostic point of view, we're trying to understand how our systems work, how the Earth system model works, how it responds to forcings. How can we build tools that are available to the community that really capture the best machine learning processes that are available out there? Like, so the barrier to getting into machine learning and understanding how to use the tool sets is quite large. So from a community perspective, how can we include these tools in the diagnostic tools that we're building right now?
Yeah, thanks for that point, Peter. I think, one thing that's been done a lot is thinking about how to share basic tutorial materials for getting started with machine learning, but I like your point about the barriers to entry, and maybe we can also think about providing tools for folks who don't necessarily want to build the machine learning parameterizations themselves, but use tools to evaluate their science and do that as part of a standard diagnostics framework like Cupid. So it's a great question. We should think more about it. And we should really think about the usefulness of tutorials. Sometimes there's an overwhelming amount of material out there and it's hard to really know where to start. So pointing people to the right places for what they actually need is a challenge.
And it's a bit in response to Dave's talk. Thank you so much. I only want to partially re-invoke this discussion about parameter error as opposed to structural model error, because we know parameter, which, for example, mass flux, right, which can be a parameter. Obviously, if you perturb it, you're going to change the whole vertical structure of the atmosphere. So in a way, parameter uncertainty can be structural uncertainty, but I think it's a pity that we, again, focus on parameter estimation as opposed to structural model error. And there's a few efforts really that are focusing on structural model error, both in the atmosphere and the ocean. And I really would like to see them more included, because I think this is where the frontier lies of really coming out of this regime where we have convection parameterizing models that really miss out a lot of the high resolution aspects that might interact with things like sensitivity to response to an external forcing. So let's focus more on structural model errors. Thanks.
Very big barriers to entry in this field is the some of the computational demands, right? So training, not cheap. That's typically thousands, tens of thousands of hours on a GPU, not accessible, to many groups, especially, well, to many groups in general. One thing, but the emulation is fast, and if you can get that off of a supercomputer, then you're good to go. I do want to point out that, this machine I'm holding in my hand has 30 GPU cores on it, right? So one thing that would be interesting to try is to port emulators onto laptops. And CUDA has been ported onto the M3 on the Apple M chipset. So, why not, right? This would be game-changing if people could run emulators on their laptops. And there's no reason why we shouldn't be. So, just a thought. One more thing for the software engineering working group to do. I'm sure they're welcoming that as a thing, as a to-do, but just a thought.
DJ, do you want to comment on credit and our ability to put it on a laptop or not?
Yeah, I can. So a couple of these points. One, I was able. So you have a relatively new laptop. I got one of our credit models to run on my 2019 era 8 gigabyte GPU laptop. So it's certainly possible. I haven't tried Camulator on my laptop yet, but I need to work with Will on that. I mean, it should theoretically work fine, because this was like a quarter degree 1 hour time step model that I ran on there. I think in terms of other barriers to entry, I mean, I think one thing I see kind of maybe coming from not of the climate community necessarily, but coming from the weather/machine learning community, is there's definitely I mean, some of it's a language and understanding, like, what are the, like, different variables and important things, how they relate to each other, and kind of also the history of all the different experiments and ways things are run. So I think in addition to, I think, teaching climate scientists about machine learning, there's also a lot of room to be teaching machine learning and other people about climate science and kind of some of the history and, like, why are things done a certain way, or why are these fields important? Because one of the problems you run into is it's easy to fit a ML model to data and not really and get a halfway decent result. But if you're missing certain variables or like not running it a certain way, that's where you get into some of these weird failure modes that show up. So I think that's where we need to improve our dialogue. I think some of the efforts LEAP has done with, like, their Clemson data set is a good step in the right direction, but I'd like to see more from the community. And it may also help us, like, reevaluate some of our assumptions and maybe see new opportunities in the process. So it's not just we're doing it for one way or the other, but I think there's joint collaborations that could come out of it that could be very useful.
Yes, I was a little confused by your comment, because I think that's exactly what we're doing, is addressing structural error while also having the capability to recalibrate the model after you address the structural error. So, like, we have several projects on replacing convection schemes, learning from high resolution, ultra high resolution simulations or LES simulations within LEAP RAM squared line. So I guess maybe we just need to have a conversation, but I feel like that's exactly what we're doing, is trying to tackle the structural error, and all I'm trying to do is prevent us from than spending all of our time trying to get the model back into a reasonable place. A model that's structurally correct, but like totally wrong in its climate simulation isn't going to be totally useful. So, but yeah, hopefully that I want to make sure that point is across. If we're not addressing structural error properly using these methodologies, then we need to be reconsidering what we're doing, I think.
I just want to comment on a slightly different topic. It goes back to Bill Collins' question about the right-hand side and left-hand side. I'm working on an ultra-high resolution project. The thing I worry about is that we do 1 kilometer runs, but the answers depend on microphysics. Depending on the microphysics, you get different answers. So you could train ML on an ultra-high resolution model, but if you get different answers with different microphysics, then you have different, the structural uncertainty is gone from the kilometer scale to the microphysics scale. So I don't know if the microphysics couples, I mean, it's difficult to completely decouple fluid mechanics. I think that we're not there yet, but I'm worried that's a possibility.
Hi, yeah, for that question, how NCAR can help us, like as grad student, I would say, like a lot of times happen, like I really like to know how can I use machine learning in my, like answering my research question. So I was thinking, yeah, tutorials or like kind of having like, if I can have like a big picture of which research questions like machine learning can answer. First, I think that would be good, like a lot of online like resources, tutorials, and also the second one would be like, how can I do it? But yeah, first I would like, first and most important, I like to learn is like, it's like machine learning is like unfamiliar for earth system science. And I think if there would be any way to facilitate that, like, to like more like accessible for us and like answering more research questions, that would be cool if we know what applications we can use that and why we should use this, or as like kind of more like a statistical method that we know, being a little bit more familiar with machine learning, that would be cool. Yep.
Yeah, thanks, Ali. I really like that point about guidance on what research questions can be addressed with machine learning, because it kind of flips the narrative a little bit in the traditional sense where maybe we have these tutorials where we're overviewing a wide variety of machine learning methods, but in this way maybe it starts from the reverse, which is to say, here are some research questions that can be addressed with machine learning instead of just putting a whole set of machine learning strategies out there. So thanks for bringing that up.
And then we have, sorry to interrupt, Monica has a comment online that's related to this as well, about helping to train users about what responsible and reliable AI looks like in the climate modeling system, especially with respect to workflows. And then how do we determine the appropriate use of the data and models, and how can we add that into our training the community with these tools? So just building on that, is how can we provide some guidance on using these tools reliably?
I was just thinking, while everybody's mentioned those perturbed parameter ensemble simulations are really expensive to run, and the value of it is obviously you can integrate observations to help improve parameterizations, but as we collect more and more observations, I feel like a barrier entry for general users could be, how do we find those simulations, those perturbed parameter ensemble simulations? They mentioned CLM is going to publish this 160 parameter ensemble simulations. That's great, but it sounded like there are a lot more of those simulations out there. So, like better documentation, not just like the simulation set, but also like the parameters. What do they mean? It's really, really hard to find those informations, and sometimes it's just like very short description. And when you read it, what do you mean? And the other thing is, as we seeing from paleoclimate perspective, some of those cloud parameters, when they perturb to simulate past climate, then that can actually provide a lot of additional insights in the couple system, although they've said they're not looking at it. But sometimes those simulations really hard to set up. You have to ask specific people and what to perturb and how to set them up. So the other thing is for this new CESM3 MLE, is it possible to like develop some kind of configurations that people can run like perturb parameter ensembles out of box? So that would be useful. So that would be my suggestion.
And maybe also, because you're asking like, what can you do? I think we're all talking about tools and how you can help with tools, but one of the most important things from machine learning is the learning part. So we need good data sets that we can train on. I think often we forget like training data, what we put in, we are gonna get out. So if we don't have what we put in, we cannot get it like out of the machine learning. And if we put in garbage, we're gonna get out garbage. So it would be good to know what is out there, what is good to train on, what are the downfalls on training on one data set versus another data set. I think that would be very helpful, for, at least for me.
I just want to respond to Rand's question or comment. Absolutely, I think that's the point. And what our goal is for, we'll get some of the way there for CSM3 is to release, the ensembles as well as all the scripting, all the tools to run your own ensemble, as well as hopefully some parameter estimation tools as well, so that you can try to do this yourselves. And we're really trying to, again, reduce the barrier to entry for this, and also to reduce everyone repeating all the steps. So we've done a lot of the hard work of identifying all the parameters, parameter ranges. We have a giant table, which nobody would want to look at, terrifying table. With all the information we're tracking, as we learn stuff about parameters, we're tracking that, so it's in that table. All that stuff we're going to release to the community. On the CAM side, it probably won't be quite as far along by the time of the release, but the same goals will be on the CAM side to have that capability. So 100%. My feeling is, with everything, parameter estimation is a science, and there's no like answer about how you do it, right? You need to build a flexible system that allows users to explore and learn on their own and test out their own new methods. So that is the goal for 100%. I feel like that's one of our responsibilities is to do that. So it's coming, hopefully.
Hi, thanks a lot for this forum. I got lost on the question we are trying to answer, but I think what came to mind, I don't know how much of this is an NCAR or a CESM thing that we can do, but I think someone beat me to it about data. I think we can try and advocate for more quality observation data over especially data sparse regions, because I mean the weather is connected and we don't expect things to work in isolation. So if we have quality data over corners and then we have bad data over Saharan Africa, what do we expect the weather model to do? Because we are using this data to train our model. So it'll be good to advocate for some quality observation data. And I don't know how much CESM can do on this, and I don't know how much NCAR can do on this, but I think it's good to put that out there. The second thing is to have more target-focused workshops. I know this is actually a good thing, like we are having one here at NCAR, but it will be probably nice to have other hotspots, maybe in South Africa, in South America, in Australia, in Europe, where people can actually have hands-on experience and practice on some of these things we are talking about. Because I don't think NCAR as a building or even as a body can host all the scientists who are interested in working with CESM. So having more hands-on tutorials and workshops would be very helpful. Yeah. I hope I answered the question.
Okay, great. It is 10 o'clock, so it is break time. I just want to mention that we will be talking about Camulator and credit after it. So if you're not familiar with those, which have been mentioned a lot, that'll be after the break. So. Okay, everyone, we're going to get started. Our first speaker after the break is Xavier. He is remote, and I'll just let you go ahead, Xavier.
Hi, thank you, and I'm very pleased to be here and to be able to present our work, which is the implementation of a neural network scheme to represent deep convection in CAM6. And I would like to acknowledge the funding, which is M Square Lines, as well as my team of wonderful collaborators, which are all listed on that slide, and many of them are actually here today with you. Okay, so I think that all of you are familiar with the fact that convection is one of the most is one of the hardest problem in atmospheric science, and also it is associated with many of the well-known biases that you find in atmospheric circulation models. The convection relies on representing a large array of physical processes. Some of them are poorly known or represented, and others are challenging to represent because of the scale at which they occur. The recent advances in computing power and algorithm makes it possible now to improve convection using a machine learning approach. And this is what I'm going to present today. This is ongoing work, and not all of it is perfect, but I think it shows promising results. So there are basically broadly two approaches you could take to look at this problem. One would be to use a existing convection scheme and improve the parameters values to be used. The other approach is to create a new scheme that where you basically use like a neural network, and there is no per se underlying physics in the model, but there are constraints, and both approaches have their advantage and limitations. It is complicated to implement a new convection scheme since there are other schemes in climate models that may overlap and also you may have to retune the model potentially if you do so. So what we want to achieve today is to first produce a data-driven scheme that captures key processes in deep convection, try to port it to CAM6 CSM with minimal tuning or alteration, and shows that it can reduce biases in climatology and climate variability. So I won't do all of that today, but I will show you some of the steps that we've taken to fulfill these three goals. The first goal is to produce a convection scheme. So to do so, we've used a set of high-resolution SAM simulations, which have an effective resolution of 4 kilometers. And we coarse-grain those simulations onto a 96-kilometer grid. Using this coarse grid, we computed the grid scale and subgrid scale fluxes and tendencies, and we then use a 5-layer neural network to predict convective flux and tendencies based on the grid scale, temperature, and moisture. This is a very simple schematic. So as an input of the neural network, you have the temperature and moisture profiles. And you have a series of outputs which represent specific processes that drive the moisture and temperature tendencies due to convection. The way we implemented it in CAM was to retain the neural network as we trained it on SAM and regrid the CAM input into the SAM vertical grid, essentially, run the neural network forward, and then grid the SAM-like output from the neural network onto the CAM grid. This allows us to retain the weights that we've computed with using the SAM data, and hence not have to retrain the model every time we have to change the vertical resolution of the model. We implemented this scheme by replacing the Zhang-McFarlane convection scheme, which is the traditional scheme used in CAM6, but keeping all other schemes active. We also were very careful at making sure that we only presented subgrid scale processes linked to convection. And also, we made sure that convection occurred only when we diagnosed a vertical extent of convection that is deep enough to really be significant. We tested this convection scheme in 3 configurations of CAM, which I will show you today. First is a single column CAM, the SCAM model, forced by the Toga core forcings. Then we'll move up into an aquaplanet run, and we'll end up with some results on using the full CAM LAN ocean. I have to also to mention that we train our neural network on an aquaplanet configuration of SAM, and hence the current version of the neural network is only applicable over ocean regions. So later we will adapt this scheme to include land, but today's presentation will be showing you results on the convection scheme only applicable to ocean regions. What we want to achieve here is to improve or resolve climatological biases, or at least you don't want to make things worse compared to your traditional scheme, and also address well-known biases in precipitation intensity distribution, in diurnal cycles, and also hopefully improve aspects of the synoptic to subseasonal timescales, in particular tropical waves. So the metric here is to do a better job than using Zhang-McFarlane with CAM, with a similar to lesser computational cost. So this is the run based on the SCAM model. As you can see, the left panel shows the precipitation over a 22-day time period. And there are 3 lines here. The blue line is the observed rainfall from the Toga campaign at a very specific site in the Western Pacific. The red is using the SCAM model forced by the large scale of the Toga campaign using the Zhang-McFarlane convection scheme. And the green line shows the YOG scheme, which is the name that we've given to our neural network scheme. And as you can see, we're doing a comparatively good or bad job compared to observation as ZM. So we're, I think, doing the implementation of our scheme into the SCAM model is reasonable. There are suggestions to say that we're actually doing somewhat better than ZM in certain aspects. So for instance, if you look at the right panel, it shows the time in relative humidity versus level. And as you can see, one issue with the Zhang-McFarlane convection scheme is that it tends to oversaturate, meaning the relative humidity tends to be too high. When we implement our neural network scheme, our relative humidity tends to be a little lower and perhaps more in line with what it should be when looking at observations. We now move up to the aquaplanet runs. So the left panel shows the total precipitation distribution versus latitude from the south to the North Pole. As you can see, you have your storm tracks around 45-degree north and south, and also you have your large precipitation maximum in the ITCZ. And as you can see, we're doing a comparably good job compared to ZM. There is suggestions that we precipitating a little more than ZM, but overall, we are able to port this neural network into CAM6 aquaplanet. It is stable and it gives us reasonable climatology. I'm also showing you the relative humidity, which shows pretty reasonable relative humidity distribution with your dry zones around 30-degree latitude in both hemisphere and more humid areas toward the mid-latitudes and polar region. The cloud distribution also is comparable with ZM. So far, I think I'm able to show you here that we're doing a decent job. Where I think we improve things significantly is in the precipitation distribution frequency. This is the y-axis of this figure is the frequency distribution of precipitation versus precipitation rate. And you already heard in previous talks about the drizzle problem. So you can see that compared to observation, which is the blue line, the Zhang-McFarlane version of CAM6 tends to have too much low frequency, low magnitude precipitation. So that's your drizzle problem. And while the extremes tends to be not as strong as they should be in their frequency. You can see that the Yock scheme improves things substantially. It reduces your drizzle, and also it gives you more extreme rainfall events, more in line with observation, although perhaps here we've done it a little too much, but it is, I think, closer to observation overall. So that's a good sign. Now, for the last part of the talk, I'm going to show you briefly our full CAM6 simulation. So what we've done here is that we've turned off our convection scheme over land since it is not applicable to land regions. So we're running the full CAM with our convection scheme over the ocean, no convection scheme over land, and we're comparing that with your traditional scheme on over both land and ocean. This is the precipitation distribution over the ocean. Broadly speaking, it looks reasonable. You can see, however, that we tend to predict too much precipitation, a little bit too much precipitation over the deep tropics and some subtropical regions. Now, if you do a zonal mean over ocean regions only, you can look at the precipitation. So the green line is our CAM6 with our neural network. Red line is the Zhang-McFarlane CAM6. And then I have also showing you GPCP in magenta and ERA5. You can see that we're definitely over precipitating over the subtropics, let's say, but also we're doing not too bad of a job in the mid-latitudes, polar region. So there is work still to be done to resolve this issue of over precipitation. But what's promising here, I think, is that the statistics, like for the aquaplanet, is improved. So you can see that we have less drizzle problem. When you look at the right panel, we have less of a drizzle problem and greater amount of extreme events, which I think is more in line with observation. So in summary, we've tested a neural network convection scheme and implemented it in CAM6 in 3 different configurations. And we found that it does reasonably well, but there are still some issues that we need to address. What we'll do is in the next few months will be to think about how to lessen this over precipitation bias that we see in the tropics. Also evaluate whether we're really improving things on shorter time scale, like diurnal to seasonal. And at last, but most importantly, perhaps, will be to make it active over land. And this is work that is currently done with Griffin at MIT. Thank you, and let me know if you have any questions.
Just on the last plot that you showed, I mean, it's a significant increase in precip compared to the base case. And I'm wondering, is there anything happening in the near surface that is, you have to have much higher latent heat flux as well to kind of accommodate that. And I'm wondering, if I remember from your single column plots, there was quite a bit of drying near the surface.
Yes, so that's a very good question. We're not fully sure about the source of this overprecipitation, but it is linked, we think, to a bias that we see in our cloud cover. So we tend to have two little clouds with our new scheme. And so that indeed drives more evaporation and more rainfall. And our preliminary analysis suggests that it's mostly ice clouds that tend to be primatic. So yeah.
Great, thank you, Zave. Oh, sure.
Question makes sense. So a convection scheme moves stuff around basically, and then you generate the tendencies. So it's sort of inherently conserving moisture and heat and those kind of things that we need. Is that a property that just drops out of this neural learning, or is that something you have to force in?
So yes, we were careful about that actually, and our neural network does conserve heat and water, and it is done so by predicting the vertical fluxes, specifically of moisture and temperature instead of the tendencies themselves. And like that, you can, when integrated vertically, fluxes being zero at the top and lower boundaries, you will conserve your energy and moisture. So overall, we do conserve water and energy. Yeah.
We are going to move on now to our next speaker, Jio Wei.
Hi everyone, my name is Jia Hui. I'm currently a postdoc at Riddle Aeronautic University. Thank you for providing this opportunity to present our work today. So I will be presenting an AI foundation model named CamNet for whole atmosphere, thermosphere, and ionosphere predictions. And here I would like to thanks to my advisors, Wenjun Dong and Alan Liu. So before should I? Top button? Yeah, move to the next slide. Yeah. Oh, big middle. Gotcha. Thank you. So before I get into the details of the model, I would like to introduce the fundamental driving force of this development. So our research focus is gravity waves. As some people probably not know about the gravity waves, if you can imagine a stone being thrown into water and the wave of the water just propagate outwards, this is similarly to the atmospheric gravity waves. From the Earth's surface, the mountain waves and the volcanoes and the thunderstorm will generate some disturbance, and it will carry the momentum and energy to propagate to upper atmospheres. And the waves will be modulating the thermosphere dynamics as well as the ionospheric causing the disturbance. So it's quite essential to know the small scale gravity waves. So some of the high resolutions can definitely help to predict those motions, but the limits is it needs the high computational cost, and it takes excessive time to make those predictions. So that's where the AI-based model comes in. We like to develop the AI-based model to quickly to predict the atmospheric dynamics. Of course, the training process takes highly computational cost, but once it's being trained, it can generate the prediction in a very fast manner. So right now, let's dive into more details about the AI foundation models. So the best way to think about it is to connect the ChatGPT, which is a very popular large language model. So it is being trained on vast data, including the audios, text, and the pictures, and it can be doing the downstream task based on user need. So you can probably send the ChatGPT a code package, and it will use the learned informations and to output the information you wanted. So extending these applications to the weather forecasting side, we like to use the AI foundation models to predict the atmospheric behaviors. There are many of the models out there, such as the GrabCast, the Climax, and the Pangu, and the ForecastNet. Those models are based on different neuron architectures, such as graph neural networks and the vision transformers based on the visual informations. Here I would like to highlight the Fourier neural operators, which training the inputs in the frequency space. The available training data set would be including very popular the ERA5 data and the MARI version 2 data. So I will be highlighting the Fourier neural operator in the last slides is because we are using extension of the Fourier neural operator, the spherical Fourier neural operator here in our model. So the spherical Fourier neural operators are specifically for, it respects the geometry of the Earth, and it is transforming the physical variables into the frequency space using the spherical harmonics compared to the faster Fourier transformation in the FNO. So the spherical neural operator has been, there are some code packages developed by NVIDIA, and the mathematical theories are published in Bonovo papers in 2023. So the most advantage of the spherical FNO is it has a long-term predictability in the in the weather forecasting. As you could see, the animation on the right bottom side, NVIDIA did a study to compare the AFNO and SFNO. So as the prediction time progress, the AFNO will accumulate a lot of errors, and the model will crash eventually after 10 days of predictions. But the SFNO will possess the stability and to predict the wind patterns. So it has a big advantage of the longer predictability. Also, it is more efficient at using the L filters compared to the L square. So it's more computational efficient as well. And also the SFNO can be generalized to new resolutions as compared to the AFNO has to be fixed grid resolutions. So the reason I compare AFNO and the SFNO because we, before Dr. Dong has already built the ChemNet based on AFNO, and it's being published in the paper of 2023. So in his paper, he simulated the nonlinear atmospheric gravity wave dynamics using AFNO. And this model is being trained by the CG1 model. So it's a very high resolution model. And here in this work, we substitute the training data with the specified dynamics of YCAMX in the CESM community. And then we substitute the AFNO structure with SFO. And also, besides that, the other change is we put the inputs into the small and the large scales to resolve the issues of spectral loss, spectral bias, which is a common issues in machine learning that the machine learning trying to get rid of the small scales learning. So we tried that in our model. Also, we couple the backbone model of SNO training with the tracer variable predictions. So we get the training weight of the backbone model of the atmospheric variables, such as wind, temperatures, and the vertical winds. And then we get the tracer variables, such as dioxide and neutral oxygen. We got those features and concatenate them together to do the tracer predictions. So to be noted here, for the tracer prediction, we're just using less layers to train, so it's faster and just less computational cost. So, so here, so as we now know, we are using the data from the specified SD YCAMX data set. Here, let me introduce a little bit about the YCAMX data in the CESM community, which is an extension of the CAM, which is a block in the CAM part, and it can simulate the atmospheric variables from the Earth's surface to 700 kilometers. And the reason it's called specified dynamics is because it's not the more realistic data from the MERA version 2 data. So it constrains the lower atmosphere up to 50 kilometers, so it will have more realistic information in this type of data sets. So these data sets used in training, we have the resolutions, horizontal resolutions of 0.9 times 1.25 degrees, and the verticals is variant from 1 kilometer to 50 kilometers. To be noted here, the data we used to train this model, we didn't use the full vertical profile, we just take every 5 of vertical resolutions. And the time resolution is 3 hours. For the data partition part, we use 10 years of data into the training process. And during the testing of the model when calculation, we use 2 years. And for the inference part, which we just using 1 year for validation purpose. So here is the flow chart of the whole model. Given the time, I probably could not get every detail into this, but the key development is so the scale separations, also the change of the frames, and also I would like to mention the other important step is we use 2 stages for training as well. So for the first stage, we just train 1 time ahead and calculate the loss and update the weights based on the loss. But on stage 2, in the fine-tuning process, we calculate 2 times or even more training steps to calculate the sum of the loss and update the weights. So by using the stage 2, it is expected the model could learn more longer time of structures. So after we train the backbone data, we couple with the tracer fine-tuning approach. We also get the tracer variables from the SD YCAMX, and then we feed into the encoder to get the features, also concatenated with the features from the backbone model. And then we use less layers of the SFNO and to fine-tune the data to get the tracer variables. So this is the tracer variable part. As for the result, so here is the inference result. Inference means we use the validation data set of 1 year, which the model never seen before. So we predict the variables of the zonal wind, meridional wind, vertical wind, and the temperatures. So on the left-hand side, it is the animation of 18 epochs. As you can see, for most of structures, they align pretty well. And also, I zoom in views to give some details at the height informations, which we mostly interested in is the 90 kilometers height of the meridional wind. So, and every column of the result is showing between 2 epochs. So, because our time resolution is 3 hours, so the top row is the target, the second row is the prediction in small scales, and the bottom 2 are in the large scales, and the last row is the arrows. So, so the large scales align pretty well. For the top rows, as you can see, the target still has quite some of the small scales that cannot be resolved by the models, but there are still some small scale waves resolved being there, as you spot on the second row here. So to get more statistic analysis, we also did the energy spectral analysis compared at different height. Top row is compared at 20 and the 90 kilometers and the 250 kilometers. So the X bar shows the frequency, and the Y bar shows the normalized spectral energy. So the larger frequency will associate it with more frequent wave or small scale waves. As you probably can see, the alignment for the large scale aligns pretty well, but for the small scales, there's still some deviations, especially at the height of 90 kilometers. The reason we think that is because 90 kilometers, there's a lot of small scale waves out there, so the model will treat the small scales as noise and filter out those noise and not capturing the structures. So from this work, we have tried the ChemNet to predict the whole atmosphere. It has good alignments with large scale and also, but slightly off on the 90 kilometers, and it is compute really fast than the traditional model run. So it did approximately 5 days training for 10 years of data, and it lasts 12 hours for simulating the 1-year data once after we train the model. So the next step, probably the most important thing, is to resolve the small scale, as we want to study more variations of atmosphere. So we will be trying to use the diffusion model, which is also a popular model that tend to not treating the noise as not to treating the small scale as noise, but will be showing more small variations. So, and also we're going to couple the physics in the loss functions to make the machine learning model not just only based on the numerical calculations of the MSE loss, but also showing some deep insights of physical loss. So that's how I'll propose the next step. So here's the reference, and thank you for your time. Let me know if you have any questions. Thank you.
Impressive results.
Thank you.
I was curious about the tracer part. So what tracers are you learning? Are those the major species of dry air, or?
Oh yeah, we currently we're trying to use the tracer variables of dioxide and the nitrogen oxide. So we are feeding those data into our model.
Because the most expensive part, since Bill mentioned dicores and any application with aerosols in chemistry, is tracer advection, so that would be very nice to machine learn that to speed up the model.
Yeah, thank you.
Very much. In the past, a lot of the emulators had problems with emulating stratospheric dynamics, and I was wondering if you have some insights why your model or your emulator is doing so well in the stratosphere and upper atmosphere. Thank you.
Oh, for the, sorry, so you mentioned why emulator is doing better in stratosphere and the ionosphere?
In yours, yeah.
Oh, I see. So I cannot say the results since we didn't do a comparison study. We just did the model to compare to the truth, to the ground truth, which is the SD WAC-MX. But it would be very interesting to compare the emulator with the AI foundation model to see what's the gap there and to see how could we further improve our model. Yeah, thank you.
Nice talk. So
Thank you.
My personal feeling with ForecastNet that it lacks of the seasonal cycle. So I want to know if you have better results in your emulator.
For the FNO, based on FNO forecast?
No, Sapphire for Sapphire for the neural operators. Version 2, ForecastNet version 2. The seasonal cycle is not that great.
Yeah. So you mean if you've seen this slide,
days or 20 days round. So if you run for 3-6
more days.
Years,
yeah.
So it lacks of seasonal cycle.
Yes, so I think that's one way to improve the predictability, as is also an issue in the models. I think currently we are trying to extend the prediction to maybe just a couple days to a month, but I think there's still some improvements to do that. And the reason that we update with the AFNO with SMO is also for the long-term predictions. So I think. Thank you.
Okay, we're going to move on to our next speaker. This is Iris.
Yeah, hi. I'm standing in for Mengze, who couldn't be here. This is really mostly his work, and I hope that I represented well. So the title is Generating Large Ensembles of Precipitation Extremes from CESM Simulations Using Spore-Based Diffusion Models. Both Mengze and I are part of a project at MIT called BC3, which means bringing computation to the climate challenge, and the goal of this project really is to use emulators to democratize access to climate data. So I wasn't here in the morning, so I don't know how much like general emulator contextualization has been done. But I think the word emulators is used for many different things, and I just wanted to sort of put into context what type of emulator we are talking about in BC3 mostly, or at least in this talk. So this is a flowchart from a preprint by Claudia, who is also an external collaborator in our project. And this sort of shows, I guess, the whole world, right? If we want to model the whole world, then we would have human activities that influence emissions, that then influence the climate and impacts and risk, which then feed back into political and social processes, which change, again, how we emit, etc. And modeling all of this is, of course, a very big effort. And the climate part of things, so that's the green arrows in this flowchart, can do only that many possible scenarios, both social scenarios, but also just emission scenarios, right? Like that would be the SSPs or the RCPs. So the emulators that we are talking about in BC3 mostly are emulators that can maybe replace or fill in part of these arrows, albeit dependent on models that have been run, so model data is needed to train these emulators, but they can maybe replace some of these arrows to then represent a larger magnitude of possible futures or outcomes or realities, and maybe also model some things that we have a hard time modeling physically, so really like data-driven emulators. And in this talk, I'm really focusing on the smallest green arrow. I don't know where the pointer is here. The smallest green arrow that really goes from concentrations or radiative forcing towards impact-relevant climate variables, or sort of the output climate variables that climate models also produce. So most of the emulators that have done this little green arrow, so going from emissions to climate variables, are, maybe I'm misrepresenting it a little bit, but at least until a few years ago, these really used to be mostly pattern scaling emulators or sort of mean state emulators. So going from one-dimensional time series to patterns. But of course, in reality, most of the things that are socially relevant, climate impacts that are relevant, are not necessarily related to the mean only, but also really need to take into account natural variability and, for example, extremes. So what we are trying to do is to emulate the distribution of climate variables so that we can say something about the mean, but also about extremes, frequencies, intensities, and how these might change in time, and also how they might look in scenarios that we have not run with our full CMIP ensemble. So that's really going from this mean Q or mean quantity to a probability of Q given a certain climate state. So in this case, it's global temperature. The emulator that we use, or that Mengze and Andre Souza developed for this, and this is not my expertise, so bear with me here, is a score-based diffusion model. So I guess the process that we sort of went through in this project was to go from emulating distributions with more like normal Gaussian type emulators, which works quite well for mean temperature variables, but then as we wanted to go to more nonlinear types variables, such as daily precipitation, we obviously needed more flexibility in what kind of distributions the emulators could produce. And so we ended up with these score-based diffusion models for now, which work by iteratively adding noise to a snapshot of precipitation, to the variable of interest. And then in so this is really not my expertise. The machine learning aspect then learns how to go back from the noise to the initial input, which is climate model data. And in that process, we generate this reverse diffusion process that then can generate the variable of interest from plain noise, so from random stochastic noise, which allows us to basically generate, if you like, infinite ensembles of the variable that we trained the model on. So we applied this procedure to CESM mesoclip data. We only did it for the low resolution now, but we started using the mesoclip ensemble because that would also then maybe enable us to go to the higher resolution ensemble and emulate that, which is arguably even harder for the emulator given the smaller scales and the higher variability, but potentially also more useful given the goal of emulating extreme precipitation in a larger ensemble and maybe for different scenarios. So we trained the emulator on daily precipitation June, July, August, and only on one member, mostly for computation limitation reasons. So we trained it on one member, and then we generated as much data as the full ensemble. So we generated 10 members of daily precipitation. And the evaluation that I will show you now of the performance of our emulator focuses on the extremes. So we've emulated daily precipitation, and then I extracted the yearly or the seasonal extremes, so the daily maximum in every year of emulation and also in every year of reference data. And then we ask, can our emulator produce this most extreme, basically most far out till of the climate distribution? And I guess there are two questions that I'll focus on in the remainder of this talk, and one is whether the statistics of precipitation extremes are well reproduced by the emulator. And the second is, if we zoom in on individual extremes, does the map also look, so the spatial pattern, does that also look representative? Because it's of course also relevant from a impact point of view. So first, let's look at I'm just checking the time, at the statistics of the extremes. So these are maps of generalized extreme value distribution parameters. Those of you who've heard me talk before know that I like GVs. The top row shows the location parameter, so that's sort of like the mean of the distribution of extremes. The middle row shows the spread, and then the bottom row shows the shape, which is about till property. So really this bottom row shows most non-Gaussian aspect in it, and also shows that our emulator can in fact produce non-Gaussian distributions. What we see is that the general maps look quite similar in a general point of view, but if we look at the difference maps in the rightmost column, so emulator minus the reference data or the training data, then we see that the differences are really quite large. So all the color bars are 10% of the total color bars. So those are really quite big errors, you could say, or biases, which are probably still also quite tunable because this is a quite preliminary version of the model for the CSM data. But we do see some structure also that's interpretable in the differences. Mostly it's smoothed gradients. So wherever the reference data is dry, the emulator is a bit too wet. Where the reference data is very wet, the emulator is too dry. And this is in line with the emulator type that we use. So with the score-based diffusion model, it's not uncommon that you would see such sort of smoothing effects in the emulator output. Yeah, this is a similar plot, but if we look at more impact-relevant variables, so the 20-year return level of precipitation, sort of taking together not these statistical parameters, but taking like an actual output impact, then we see similar things. So general gist is the same. The pattern looks relatively similar, but the differences are sort of lower gradients, smaller gradients in the emulator compared to the reference data. Then I hope that this looks okay. Then if we look at these physical characteristics of individual events, so I chose 3 regions, Brisbane, Boston, and Mexico City, and for both the emulator and the reference data, I selected 3 top 10 precipitation events in those cities and just plotted here the day, so the way the precipitation pattern looks on that day of maximum precipitation. And as you can see, they're all different because they're different events, but we do see features that are similar. So the emulator produces features that seem to correspond to what the actual model also produces, especially here in Mexico City. You see very clearly this atmospheric river, if you like, that then comes from the west and hits the coast. And it's cool that we can see that those features are also represented on a daily scale in the emulator. And if we look at the composite of the 10 most extreme events, these also look similar. Of course, they're not so surprising. It's just a blob of rain around the city, but you see some structure that suggests that the meteorological features are comparable. So that's already the end. So we see that these score-based diffusion models do reasonably well at capturing nonlinear climate variables and also the spatial characteristics of individual extremes. I put an asterisk there because there's still some tuning to do for the model to really say, okay, now we can use it as an emulator for extreme precipitation, because the biases that I showed today were still too large to say that. And I think what's really next steps, like in this whole process of emulating extremes or impact-relevant climate variables, is to go more into this scenario interpolation. So this was all just dependent on global mean surface temperature, which is a very coarse representation of a scenario, right? It doesn't give you that much more flexibility. So I think including more predictors that really increase the scenario space that we can emulate is a priority for these types of efforts. And then also, of course, extrapolation. If we talk about large samples, it would make sense if those samples also included events that weren't in the training data, because then we can actually learn something new. Thank you.
So thanks for using our Metacritic datasets. So I'm a little bit puzzling about your training strategy. So what's your input variable?
The input variable is daily precipitation, June, July, August. So it's daily fields
output
of
is also precipitation.
Output as well. So the input and the output are the... Okay, so the covariate is global mean surface temperature. And it's trained on daily precipitation, and then it also outputs daily precipitation. So it's a stochastic model that generates plausible representative precipitation fields as a function of global mean surface temperature.
Just using a precip to emulate the extreme precip.
Yes, because the daily precipitation, so it's daily precipitation the whole distribution is generated, and then in the post-processing, I extract the extreme precipitation from the emulator. So we emulate daily precipitation. And I now showed an evaluation of the extremes in the daily precipitation sample that is emulated.
Thank you.
Okay, we're going to move on to our next speaker, which is now DJ.
All right, good morning, everyone. So today I'm going to talk about our community research Earth Digital Intelligence Twin, or CREDIT, which is our new AI weather to climate and whatever scale in between AI model emulator framework that we've been developing at NCAR for the past couple years. This has been a huge joint effort among a lot of people here. So I know a few of you are in the audience, so if you've been involved with CREDIT, can you stand up real fast? Yeah, so I want to thank them and a lot of other folks here for their efforts, and please go talk to all of us during the discussion and during the lunch break today. So why did we develop CREDIT or why did we decide to go down the path of developing CREDIT? As people have been following in the news, but maybe going back a little bit further than that, a lot of AI weather and climate work was focused on kind of a lot of sort of single variable kind of problems, more post-processing. A little bit of parameterization was happening back in 2018, 2019. But a few folks were bold enough to think maybe we can emulate the entire model. And so basically the weather bench data set was developed, and like it came out at the same time as Error 5. We saw a number of groups starting with kind of individual grad students, and then growing to large tech company efforts like at NVIDIA and Google and Huawei. We saw steady improvements to the point where eventually, in terms of individual variables, we saw Pengu and GraphCast outperforming the ECMWF model on single variables. This led to an explosion of other groups jumping into the fray and trying their own approaches. What we haven't seen with this, like tons of other groups trying lots of different modeling approaches, is that performance has kind of leveled off. There's been some marginal improvements in different aspects, but we're not really seeing, I would say, like that continued upward trajectory. And so it's possible that the scale of the models and the scale of the data, I mean, it's possible that that's one of the limiting factors, but I think one of the other issues is not getting the physics entirely correct. So there was a study by Slavinsky et al. Kind of down the road from us at NOAA that ran a number of these models with basically assimilating surface pressure and doing cycle data assimilation, kind of like you would with the traditional NWP model. And the problem they ran into is that eventually all of these models would go numerically unstable after a certain point, except for deterministic neural GCM, which is a hybrid model. And none of them outperformed the UFS in kind of this more realistic setting. So this is telling us that while, like in terms of global skill scores, we're getting good performance, there's some other inherent issues in how the models are propagating data around that need to be addressed before we can really, say, want to deploy these in all kinds of different applications. And to solve this problem, I think it's not just like kind of come up with a new architecture sort of problem. It's really thinking through the data, the models, and the physics. And so in order to do this, and to help the community do this, because after all, we're at the CESM workshop, and the community is kind of the key part of this and a key part of NCAR. We developed CREDIT, which is, we call it an open foundational platform. So rather than a foundational model, we have a foundational platform that you can use to develop and deploy AI weather and Earth system prediction models. We've added kind of a pipeline to handle different data sets. We started with Error 5, we brought in CAM, we brought in CONUS 404, we're starting to bring in GFS, and we're looking at other models or other data sets already. And then we've implemented multiple modeling frameworks. Some we've adapted from other groups, others we've kind of cooked up ourselves. And then we've added ways to conserve physics, at least at the global scale for now, but
kind of in a more modular framework to enable mixing and matching all of these different pieces. We have some scientifically validated cases, but we also want the whole community to be involved in trying this out and running this on your own use cases, not just in the atmosphere where we're starting, but thinking about the ocean, the land, the ice, and how these all interconnect. So the basic components of this is first we have to process our input data into AI-friendly chunks. This turns out to be a very important thing for not breaking the supercomputer, which we did a few times in the training process. In terms of our variable types, we support kind of prognostic or input and output variables, static and dynamic forcing, which are input only, diagnostic variables that are output only, and then we can do derived variables and interpolate on pressure and height levels. To train your model, you start with creating a PyTorch data set that loads in your data from disk. You run it through a transform to normalize or otherwise rescale your data, feed it through your model, feed it through what we call post blocks that apply physics corrections, and then you calculate your loss and then update your weights using backpropagation. You do this until you get decent convergence, and then maybe you want to run it out further in time and learn from a longer range trajectory. So we support multi-step training where you basically do the same thing, except the difference is now you have to cycle your model a few times and then take the loss over that trajectory. And we have some ways to scale this on the supercomputer so that you're not basically balancing that memory and computation challenge. And finally, we have prediction, where we actually want to launch our model on new data it hasn't seen, and we can run it forward. And then we can do post-processing on that and calculate both metrics and outputs and save it all as CF compliant .cdf files that you can then feed into all of your favorite diagnostic packages. Our first version of credit focused around a model we called WEXFormer. For this, we took Era 5, but instead of using pressure levels, we used hybrid sigma pressure level data on a 0.28 degree Gaussian grid, so the native grid of Era 5 plus filling in to a full Gaussian instead of reduced Gaussian for those who care about those details. We like kind of use different years for training, validation, and testing in line with a lot of the weather bench models. In addition to kind of our prognostic variables, we have some forcing variables, and then we also output, use as prognostic some 500 millibar and surface variables to allow us to more easily diagnose how well the model is doing without having to do all the pressure interpolation every single time. In terms of our model architecture, it's not I would say not particularly complex or revolutionary. We use some short and long range attention in the encoder part of it, and then we have standard convolutions for the decoder part, and in between we have basically send data across. So it's basically a unit architecture. Nothing fairly like revolutionary on that part. The revolutionary part, though, was a discovery that John Schreck made that you could use spectral normalization, which is a trick from the GAN community, where you rescale your weights during, basically, when you update your weights, you take the spectral norm, which involves sort of a singular value decomposition. And when you do this, you rescale the weights by the first principal component effectively. And this helps prevent both exploding and vanishing gradients, and we found it generally improves model stability. So a lot of other groups, so like Pengu, Fuxi, Fengwu, all have like these cascading models where they switch to a different model a certain number of steps into the process because their model is blowing up or getting too smooth. We don't have to do that. And we can also run at arbitrary time steps. We have a 1 hour model and a 6 hour model, and both can run out quite long and don't go unstable. They're still artifacts, so it's not perfect, but we've applied this both to WEXFormer and to Fuxi, and we're seeing similar results. In terms of our overall verification, I picked a number of the 500 millibar in surface fields to kind of show as an example. The blue line is ECMWF, IFS. The green line is Pengu, and WEXFormer is the red line, and Fuxi is the yellow line. We also have our 1 hour WEXFormers on there. It's like kind of the maroon line. What we're generally seeing is that our 6 hour models generally outperform IFS and are competitive with Pengu with some slight improvements at longer lead times. We're also seeing the 1 hour model is competitive and maybe a little worse, about the same as IFS, but it's stable out to that long range, and no one else has been able to pull that off to this point. In terms of our kinetic energy spectra, like a lot of these other systems, we're over smoothing the data. at the fine scales. And there's a few like wave artifacts we're seeing that also show up as little spikes in the data, and seem to be more prominent once you get out to like 10 days in the 1 hour model, but also show up in all the other models too. So not a unique problem for us. In terms of what this looks like across different vertical levels, so we are generally pretty sharp in the lower atmosphere, but as you go higher in the atmosphere, especially once you get above the tropopause, we start smoothing things out quite a bit. We capture some of the very large scale waves in the stratosphere, but a lot of the smaller scale gravity waves aren't showing up. And so that's something where there's certainly room for further improvement, and we're kind of thinking about ways to do that, and interested to see what the previous talk focusing on the stratosphere learned from that. So this was our first go at it. Didn't have any physics conservation built into it. So Kyle Shaw, who was a postdoc with our group and is now a project scientist in the Research Applications Lab, decided, hey, what kind of physics conservation can we put in? How does that affect the model? So we took a 1 degree version of it, created a 1 degree version of Era 5, added precip, evaporation, radiation fields. Also, sea ice cover, which turned out to be really important for surface temperature, and some other information about the land surface. And then trained a version of the Fuxi model, which the architecture is shown up here. It's a variation of what's called a Swin transformer. And then we added some kind of model agnostic blocks that basically don't have any trainable parameters, but just run a conservation based off of the initial conditions of the model. So first we do a non-negative correction to get rid of any negative precip or humidity. Global dry air mass conservation to fix the dry air mass budget, moisture budget conservation, which adjusts the precipitation evaporation, and then total atmospheric energy, which adjusts the temperature. We do like a multiplicative adjustment to these fields globally, so nothing is moved around. We just like kind of multiplicatively scale everything based off of the ratio of training of like the initial conditions and current conditions. We do this during both training and inference, which turns out to be important. I'll show in a second. And then from there, what we see is so one thing that has come up in the discussion is you're only as good as your training data. Well, it turns out if you add physics, you can actually fix things about your training data. So IFS and Era 5 have issues with what's called drizzle bias. And if you train with it, you actually get an even worse drizzle bias. But if you have the physics correction on the non-negative correction plus the moisture budget correction, we get rid of the drizzle bias. So if you look at Antarctica and at the Sahara in particular, you see it's a lot whiter. There's none of that pink that you see in the other fields. We also see improvement, and this improves our precip scores overall. We don't sacrifice performance at extremes. We also get better performance in terms of other variables, especially after 4 days, thanks to all the physics corrections. How far does this benefit us? So if we run this out for a whole year, so now we're starting to get into closer to our longer term scales here, we see that we're able to basically conserve the physics in terms of our drier mass, global precipitable water tendency, and atmospheric energy tendency. It's not perfect, but our tendencies are much smaller and much more balanced over the course of the year. Even though Era 5 itself does not balance these things, it is not conserved, we're able to enforce that and get good predictions. We also did some ablation studies. How much do different things affect the model? What we see is if you run it during only inference, all the conservation during only inference, your forecast gets a lot worse because now you're showing it predictions that look a lot different from what it had seen in the training data. Whereas if you do it during both training and inference, you get a much more robust result. The model doesn't have to compensate as much for differences from physics. We see the drier mass has the biggest mass conservation is the biggest influence, but energy conservation does help a bit on some of the variables. So it's hard to make it a little bit better. It's easy to make it a lot worse. We also show some other physics constrained fields. So we have precip field and total atmosphere net thermal radiation. They're fairly smooth because this is at 1 degree, but we're seeing steady evolution of different fields. We see tropical cyclones in the figure. That's compression from the video, not from the AI algorithm. So it's looking very promising. And Will's going to talk more about the climate side of this. But want to kind of like from a bigger picture perspective, how can we potentially use, or how could you use credit in your research? So if you're a grad student, I think one of the big advantages is one, being able to quickly generate large amounts of model output, and since it's all in Python, you can easily add other diagnostic packages into the flow and run online while you're doing this, and so save out the things you only want to save out, and maybe even do some of the analysis and plot generation with one script rather than having to compile a bunch of Fortran and then they kind of have a much longer pipeline. And we can really speed up you can do more iterations potentially of your model runs. If you can do this, like generate your models in a day rather than a month, that kind of changes the way you can spend your research time potentially. Same with if you're thinking about risk modeling, we can look at compound risks much more easily and generate lots of ensemble members. But of course, I think part of this is still we need to validate these that they're doing all the right things before we go completely hog wild with this. So some future directions, we're currently working on ensemble generation. We're testing a few different approaches, some that like everything from diffusion to different kinds of noise injection approaches that kind of, the noise injection seems very promising so far, and we'll hopefully have more to speak about that in a few months. Looking at new model developments, how do you trade off data volume, model size, input data size, physical constraints to get a accurate but also fast model. I think the vertical exchange of information is a very important thing that we need to work on. It seems the models are underdoing it right now pretty consistently. So what can we do on the ML side to address that in terms of how we represent the vertical scales? I think some of this is we just under-resolve the vertical in our current generation of models, and hopefully either add more levels and more explicit attention in the vertical might fix some of that. And then there's, I think, a question of like this end-to-end approach is much more efficient to train. Component models are more interpretable. What's the balance to strike to get that scientific understanding, but also not have to spend years to do that? So I think it's still a very open question, and I think open to the community to kind of figure out what they want, what works well for their different use cases. We're getting more software engineering support in terms of next steps. Regional model we're training and evaluating right now. It's looking very promising. We're also looking at S2S and longer scale rollout evaluations. We can clearly roll out to S2S scales and do it stably, but is it actually performing well? That's an open question. And we're working on our next generation weather model for the globe and looking at some different data sets that could be promising for that. And so that code's open source. Go check it out. We have our papers online. Our initial credit paper is just accepted to MPJ, Climate and Atmospheric Science, so that'll be coming out soon. It's already on archive if you want to take a look, and we have docs and developers here if you want to ask us lots of questions. So with that, thank you.
Thanks for the overview. This sounds really valuable. Really specific question about introducing the mass fixer. It sounds like a really traditional, like old-time climate modeling approach. Has anyone considered trying to have a learned mass fixer that redistributes the mass in some sort of learnable way?
So Kyle did look into things that were more localized and could redistribute stuff, but it started to get really complex to actually pull this off and add a lot of computation. So he decided to go with the global and call it good. But if anyone wants to try more local approaches, we're certainly open to collaborating.
Okay, we'll move on to our next talk, which is Will Chapman.
Awesome. Yeah, so I am the thing that stands between you and lunch, so we'll try to move this along super quick. So DJ just introduced the credit system, which was developed by a whole bunch of folks in this room. The development really started about a year and a half ago when John and I locked ourselves in a room and started really hacking away on the code. And then since then, there's been just an unbelievable amount of folks that have joined this effort and really all the work that you see today is building off of a lot of stuff that has been added here in the past. And we're really, really excited about the project, and we really want to treat this like a community platform, very much in the vein of CSM. So if you want to get involved, you saw the folks that stood up before, please come talk to us. We are actively trying to get people to use this system. So you are going to recognize this first slide. To set the context of what DJ just told us, we're going to be talking about one of the data sets that we are currently actively supporting here. So this is the community atmosphere model. And in our development branch, we have now supported much more components within CSM. So we have data sets in machine learning ready format for different parts of POP simulations, CLM, and some of the CIs fields also. So we are actively moving towards a more active model state. I'll also note that, as DJ pointed out, we have capability for our WEX-Former model now to do diffusion-based emulation, which will handle a lot of problems for some of the smoothing fields that we see, though we don't know if that's going to be our ensemble-based system yet. So today we're going to be talking about emulating just this data set here, the community atmosphere model. And the model that we're doing it, you might recognize this figure from what we've just seen. So this is the Camulator architecture, which is very similar to basically uses the WEX-Former backbone. We changed some of the upsampling blocks in our most recent version of that model. We then pushed that through similar physics conservation blocks that you've seen before, slightly adjusted so that we're exactly conserving rather than getting close. And then we then push that through the training loss scheme so that everything is updated based on the forward model run. So what this is a one input, one output kind of system. So we take the current state of the atmosphere, we just predict the next state of the atmosphere. We're not doing tendencies, we're doing that full emulation process. So when we have released one paper on this, or put it out for preprint called the Camulator paper, so this is trained on over 30 years of this observed record forcing, and the throughput of this model is we can get about 480 simulation years per day as we're marching this thing forward. So what is the actual data that we're training on here for this Camulator project? So what we've done is we've created an FHIST run for our version 1.0. So we conduct this 35-year FHIST run from 1979 to 2014 of CAM6 in CSM version 2.1.5. We then collect 6 hourly data. So our time step is a 6 hourly time step. We compute total water and convert to some flux form so we can ensure that we are conserving energy in and out of the model, and then gather the static and forcing data. And we have our static data here, which is the land surface geopotential height and the land sea mask. We then force the model with solar incoming radiation and observed SSTs. And this is the suite of variables that we are predicting here. So we have prognostic variables, so UVT and Q-tote, which is the sum of all the water in the column, and then surface pressure and surface temperature as our prognostic variables. We'll note that we are operating on every model level, so we don't do any vertical coarsening. We felt this was important for some of the reasons that DJ talked about before, how we're losing some information. Additionally, CAM is used for a lot of other things in terms of basically interfacing with other processes broadly in the community. So we want this to be as easy to use as possible. So the output from this model should be easily plug-inable to any process that you're currently either evaluating them on, or say you're doing something like supermodeling where you're connecting model states. You don't have to do any interpolation. We're in the exact model resolution that you see with CSM. Additionally, we have a bunch of diagnostic variables here, including precip, some cloud variables, surface stresses, surface wind speeds, evaporation, things we need to close budgets, and also gives us the ability to couple to some other components of the model as we move forward. So these are the data that we are attempting to emulate. So I got to name this model. So we're emulating CAM, and I called it Camulator. I was told yesterday that was maybe a mistake because now we are trying to do a CL emulator and a momulator and a populator, and it's getting out of hand. So this is the promo video that I made for it. And what we're looking at here is the surface specific humidity, or that Q-tote variable. And really what you can see is it passes the eye test. So we see atmospheric rivers as they're flexing and hitting different west coasts. We see a little bit of a diurnal cycle as it pulses in the tropics. And this will run out for indefinite time periods. We don't see any major model instabilities. We also don't see a lot of the model smoothing that we have observed with our other system, because essentially during the training process, we have ensured that we're not doing long rollouts, because we don't care as much about the prediction task, we care more about the generalization task. So the smoothing is not really a huge issue with this modeling system. So I'll show you one more pretty visualization, and this is the precipitation climatology as it develops within our model. So essentially we're averaging precipitation. You'll see the ITCZ develop in the southern ITCZ branch, along with flexing into the Asian monsoon region, development of some atmospheric river fields. So this is a 5-year climatology as it builds, and you can see the nice precipitation fields. So how are we doing in terms of just biases? So we want to be able to ensure that we are representing our CSM 2.1.5 system to the highest fidelity as possible, so that then we can turn around and use this for potentially either model development or some sort of ensemble creation, and trust that it's representing the fields. So these are the biases that we're seeing at present. So we have in purple CAM, in teal CAMulator, and then I've also put the GPCP product on there on the top left, and that's a zonal mean. You can see it's representing the field fairly well. CAMulator has a little bit of, struggles a little bit, especially over Central America is where we see our largest precipitation biases. In terms of temperature, the big error that I can't seem to knock down is over Greenland. So this is sort of my Labrador Sea. I go in every day and try to ensure that this bias goes down, and I'm trying to knock it down and I can't quite do it. I think it's linked to a 2-week NAO right now. So I'm thinking about ways in order to try to encode some more of the low frequency variability into this. Overall though, these biases are much in line with what you would see with various model tuning runs as you go through the tuning process of a traditional model. And I'll say the epoch to epoch variability of the biases is fairly low, but you do see different biases pop up as you run out of epochs. So our training strategy was really to pause at every training example loop, run the model out for a year over our validation suite, and take statistics over that year. The model that minimized sort of the bias in that validation year is the one that we have sort of frozen for now for our version 1.0. So in terms of stability and long-term rollout, on the top, I am forcing the model with historical SSTs, and I have 24 ensemble members. And what we're looking at is the total heat capacity in the atmosphere. In purple, you see CAM6. What you'll notice is some year-to-year interannual variability, particularly around ENSO years. I can say we are a little under-responsive as we move out into the later time period. But importantly, this is a 24-member, 35-year ensemble that we completed in 8 hours on a single GPU. So to do a similar run, this would have taken 4,000 hours of a CAM6 run, or 166 days, giving similar compute. So it's really a step function if we can figure out if we can trust this model, trust the model fidelity. On the bottom, what you're looking at is a 250-year rollout in which we force the model with climatological SSTs. We get a stable rollout. We get a really nice annual cycle, and it runs indefinitely and stably without any major grid artifacts. So what we've done next is a series of tests just to take some first-order approximations at are we getting correct model responses to some different forcing scenarios. So what we've done is we've taken that 2000 year, or year 2000 climatology, added 2K of uniform warming and 4K of uniform warming. And what you're looking at here is 3 different model levels. So on the top panel, you have the lowest model level, or sort of the surface representation of temperature. Middle panel is the 1000 hectopascal to 850 hectopascal integrated heat content. And the bottom panel is the 200 to 850 hectopascal integrated heat contact. And in dashed line, that is CAM, and in solid line, that's the camulator. I'll highlight that these are temperatures that this model has never been anywhere near. So this is well out of distribution. What we would expect is the model to completely freak out. What we see is a stable run, so it doesn't blow up, but we do get a certain amount of biases introduced into the system. So the lowest model level does fairly well, but that model level is driven by SSTs, so you'd expect that to do fairly well. The integrated heating profiles, especially in the lower levels for the 2K heating, is represented fairly accurately. When you get up to the 4K heating, or that green line, you see that definitely during boreal winters, we're witnessing some sort of bias there. So the model is not getting warm enough. And essentially what this is the model has never seen a state where the sea ice is that low or the temperatures are that hot in the Arctic. I'll point that out here. So these are the biases in the 2K runs and the 4K runs compared to what CAM is doing. You can see that the major biases are really happening in the Arctic regions. And we speculate that adding more sea ice information and getting some more of those physical processes in there will help to improve these biases, and I'll show you some quick results on that in just a second. So that was our version 1.0, and that's the paper out on arXiv. What we've done since then is we have run a coupled simulation, and now we are training on this model data. And I got these results all just prior to the computer going down, so you're going to see some quick results with a model that is not fully trained yet. But I wanted to show you some fun new stuff. So what we've done is we've taken a coupled run in the CMIP6 suite. We then branch a hybrid run off of it, or we do a hybrid run off of it, run that forward in time to 2014, and then do an SSP 245 foreseen scenario out to 2050. So what we'll do is we will use our pre-trained model from before. We will then switch over and train on the coupled simulation, and then we are going to test the simulation from 2015 to 2050 to see how it responds in a future climate warming scenario. Some things that I've added and switched between version 1 to version 2 is I've added surface temperature as a variable, added some sea ice information, so adding sea ice fraction, CO2 volume mixing ratio, forcing from the coupled oceans, and now we have a coupled ocean rather than an interpolated observed ocean. Remove some redundant variables. For example, we had cloud total, but that was just a sum of the 3 other cloud variables, so I've taken that variable out. And then altered some of the technical aspects of the machine learning layers themselves, particularly the up convolutional layers were causing us some problems, so I've adjusted some of our machine learning suites to improve some of the representations there. So now what you're seeing is 2 runs of Camulator and CAM. Again, we were just trained in that first period, and now we're validating, and this is the total integrated heating from 2000 to 2050. And you can see that for the total integrated heating, even in a sort of a suite of, or an era that Camulator has never seen before, it tracks the integrated heating very, very well. So we are getting that climate change signal in there. So I wanted to run some really quick and dirty tests to see exactly what's being, what really the model is looking out to get this signal. We know that we're forcing it with an SST that has that in there. So I held that SST constant at 2010 and just cranked up the CO2 to see if I could see any weird behavior here. And it turns out we see some massively weird behavior. So as I crank up CO2 and especially get to the end of that period, that's a CO2 level that it's never seen before. And it is, yeah, really going off the rails there. But that does tell us that there is some sensitivity to the CO2 forcing, it's just not the right one. So if you hold CO2 constant and you crank up the SSTs, yeah, it tracks it directly. So it's really just using the sea surface temperature information to get that total integrated heating. So not exactly what we want, but we have some strategies now that we are thinking to start to address some of these problems. So finally, we have, now that I have retrained the model, I forced it again with this 2K simulation, 2K plus SSTs, and I have essentially oriented that top right figure where whenever the colors on top match the colors on bottom, we're improving the biases in this simulation. So did adding the CO2 and adding the sea ice improve our representation of the biases in this 2K simulation? It looks like it did everywhere in the Arctic and over the sea ice regions, but we're sort of getting the opposite response in our Antarctic region. So there's still some work to do there, even for our version 1.1. But what I'll say is we're in active development here. We're treating this like a true modeling project. We want to find the highest fidelity field. So we've passed off these simulations to outside groups to do model evaluation. We're working with Senna to start to do some of the greens function evaluation. And we really want the community to take a good hard look at this, tell us where the biases are, because now we can start to address those things. And it was really encouraging to see the history of CSM talks yesterday and the long sort of model development framework. And I'll point out that the machine learning emulators have been going for 3 years now, really, 2-3 years. And there's been a lot of progress made, but we have a long ways to go. It's really going to be helped if physical modelers can be involved in this loop. Folks that know the systems and the physics really, really well and can start to help us iterate on these biases. So it's so encouraging to see CSM and this community really embrace this, and especially folks from things like the M² Lines project, which, as you mentioned, all of my time is funded from Schmidt Sciences here. So really, I will put up some next steps that you saw from DJ. I'll add that we are currently trying to couple to an active ocean. And working with some of the folks at M² Lines, we're hoping to couple to their ocean emulator here soon. So that's some of the work that is planned in the future. And I'll throw up that last slide that DJ had, and I'll throw my contact there for you. If you want to chat, use the system, please contact us. We really want to test this thing out. Thanks.
We have time for one question.
That's why I just run so hard. Yeah, thanks, Will. So I couldn't find like geopotential height as one of the output variables, and I'll be really interested if you can adapt that for the next versions, because it's such an essential component. So yeah.
Yeah, you can calculate it from the fields that we currently simulate. So we are working on basically an interpolation layer that kind of does that for you. So we'll take out the guesswork for you, and DJ has a nice mod that's already in our toolbox, so you can do those interpolations. It's really fast. It's really, it's slick. So yeah, if you want to talk to him.
Okay, good to know. Thank you.
Okay, great. And before you all leave, I just wanted to put in a plug. We have a CGD machine learning group, and if you're interested in joining to learn about progress that we're making in CSM3 MLE and other machine learning applications using CESM, please let me know. You can come talk to me out during lunch or whatever. Give me your email and I can add you to the email list. So, all right, enjoy lunch. Thanks to our speakers.
Yeah. Good afternoon, everyone. This is the Earth System Prediction Working Group meeting, so thanks for joining us. We're going to jump right into presentations, and then we'll have discussion at the end. A working group discussion. You can feel free to ask questions of the speakers for that kind of discussion around their science. We will start with the first speaker, who is Anisha Paul.
Hi everyone, I am Anisha Pal and I'm scientific ML engineer at Planet. And today I'll be talking about leveraging CSM2 data for machine learning based S2S forecasting. This work was done at Planet and each member of the Planet team has contributed to this project. So to start off, I would like to start by talking about AI foundation models. Like we have noticed in the past few years, AI has kind of become a household name, and majority of this success can be attributed to AI foundation models and their success in a lot of vision and language understanding tasks, as we can see here. And even though there's a lot of innovation in terms of the architecture that we see with these models, the main principle which has kind of propelled this advancement is this concept of pre-trained broad, but fine-tuned precise. And to briefly explain this, pre-training can be thought of as we have this like one machine learning model, and we have a large corpus of data. And what we do is we train the machine learning model on this large corpus of diverse data on usually a very simple objective, or sometimes an objective which is very similar to the downstream task. And through this kind of training process, we hope that the model is able to learn large-scale features, which helps it understand the downstream tasks, something like the foundational building blocks, which will help it understand those tasks that it needs to do in the downstream situations. And then because we have this model which learns these landscape features very well, we just need like very few data points for a task-specific application. We train the model on this and it converges really quick. So this is the entire concept which has kind of propelled the advancement of foundation models. And we have seen this in application with a lot of AI-based weather modeling as well, which is why we see that in the recent times, there are a lot of AI-based weather models which have advanced the skill in terms of weather prediction. And these models are mainly trained on ERA5 data, on hourly scale ERA5 data. And they are then able to perform a lot of multiple downstream tasks, ranging from downscaling all the way till storm tracking. So the question is, why can't we just extend what the AI-based weather models are doing to the S2S space? And the first problem is that of task complexity because of the interconnectedness between the multiple climate systems in the S2S space. And I won't go into this detail because this is a group of climate scientists, so I think I'll leave it at that. The next problem which we are mainly tackling in this work is the problem of data availability. So if you think about these AI-based weather models, then they mainly work in the hourly scale. But when we move in the subseasonal scale, we are either training on weekly or monthly data. And that means the scale of the data reduces by a factor of almost 100, right? Depending on what kind of temporal scale you're training on. And the final problem is that one can argue that since these models are doing so well in the weather scale, why don't we just extend them all the way to the subseasonal scale? And as these papers have also stated, that beyond a factor of like 10 days, there's a massive error buildup because they work on this auto-regressive rollout strategy. So to summarize, it's a much more difficult task because of these challenges that I just spoke about. So the one problem that we have tried to tackle here is the problem of data availability. And we noticed that this gap is basically kind of closed by Earth system model data. To give a basic one-on-one comparison, we have ERA5 data and we have CSM2 large ensemble. The first point is the point of the years that we have in ERA5 versus CSM2. And even though we have 1940 to 2024 data for ERA5, in terms of ML model training, we can only use from 1980 because of the uncertainty in the data before that time period. Whereas in CSM2, we have a large range of data that we are getting, and this also helps the model see a lot of different climate variations. Now, if we just do a basic calculation in terms of the number of months we get from each of these data points, then we can clearly see the difference over here. And then the number of ensemble members come in. So over here, just for the sake of one-on-one comparison, I've mentioned one ensemble member for ERA5, so please forgive me for any technicality. But when we do a basic maths, we see that in comparison to era 5 for S2S space, we have a much larger amount of data when it comes to CSM2 large ensembles. And now we can think about training these machine learning models to actually understand those large scale features on the pre-training kind of strategy that I spoke about in the earlier slides. So for our model, we used a very simple unital STM spatiotemporal model. And we did a deterministic quantile regression because our hypothesis was to understand how just increasing the amount of data can help break us into that S2S space. For our training data, we used CSM2 data from 1850 to 1922. We kept a separate test data, which was era 5, and we do comparisons between different model runs on this test data. We use a native CSM2 grid resolution, and we constrain the grid from -60 to 60 because for this simple modeling task, we do not want the complexities that CIs might introduce in this problem. For our input, we have 11 variables, and as our output, we have temperature and precip for like a lead time of 0 to 3 months. And the metric we use for comparison is something we calculated called anomaly R-square, where we basically calculate the R-square metric over the precip and temperature anomalies. So in this case, the higher the metric, the better. So the first run that we did was training our model on era 5 data versus training our model on the CSM2 data, and then evaluating both of them on the same test set that I showed in the previous slide. And as we can see that the performance improvement is much higher when we train with CSM data. And one simple hypothesis here is that even though I know there's a lot of contention around CSM2 and ENSO, we feel that the CSM2 data actually helped the model learn these kind of large-scale features similar to ENSO, which it was then able to apply towards predicting better temperature anomalies. But the question was that, like, as I mentioned, that more data is always better, but is it really the case? So we did a little bit of ablation experiment where we increased the number of data points from 10 ensemble members to 25 to 50. And as we can see from this image, we kind of have like diminishing returns after 25 ensemble members. And one reason that can be is because this model is mainly learning the large scale features. And with 25 ensemble members, it has kind of learned all the kind of large scale features it needs to learn. So additional members are not really helping it with that kind of aspect. But that does not mean additional members won't help. Additional members definitely will help with the smaller scale patterns, which, given the simplicity of our model, it's not able to pick up. So the next step will be to introduce a more complex model, which we are working towards with our foundational model, NEVA, to be able to understand the smaller scale patterns, which will help push the performance of these models further. We also did some ablation studies to understand how different data normalization strategies can help with improving the model performance further. So we had 4 different normalization strategies across spatial and temporal axes. The first one is a global all-time normalization, in which case each variable has one mean and standard deviation. The second one is local all-time, in which each variable has one mean and standard deviation for each lat-long location. The third one is a month-wise global normalization, where we have for each variable, we have one mean and standard deviation for each month. And finally, we have month-wise local normalization, where for each variable, we have one mean and standard deviation corresponding to each location for every month. And we noticed that the performance is really a lot better when we do month-wise local normalization. And there are multiple reasons, but the main reason is that we see a lot of variation in these variables, not only from a temporal scale, but also from a spatial scale. And given that the machine learning models work on the principle of a more balanced data, if we do not have a distribution which is more normal, if it's too skewed, then these models don't tend to do very good. So that is one of the reasons why we feel that having the right normalization strategy so that we can feed the right distribution to our model really helps improve the performance by a lot. And finally, I have this slide where we show for different lead times from 1 month to 3 months how our model does on predictions across temperature and precipitation. And as we can see from the graph over here, which is just a more quantifiable version of the slide I showed earlier, that our model obviously does a lot better in temperature compared to precipitation. And as everyone here knows, that precipitation is a much more difficult task, which we are also seeing with our AI-based prediction models. But what we do notice is that even though there's a drop as we go from like lead time 0 to lead time 3, the drop is not as sharply as we anticipated with these AI-based models. So that kind of gives us some kind of indication that we can extend them further to the subseasonal scale. So the major key takeaways is that CSM2 data can help create the next generation of AI foundation models for the subseasonal to subseasonal scale. And performance is very sensitive to the distribution of data, so picking the right normalization scheme might not be just normalization scheme, but ensuring your data is not very skewed when you feed it to the model is extremely important. And more data is definitely beneficial, but we need to scale the model complexity accordingly to be able to squeeze the maximum out of the model, out of the data. These are my references. Thank you, and I'm happy to answer any questions.
So we have time for questions. If you have a question, please come to the microphone. If you're standing in the back, there are seats in the front. Please come forward. And this is just like Southwest. If you have a bag sitting in the middle seat or the seat next to you, please remove it so someone can sit there. Thank you.
Nice talk. Thank you for that. I'm wondering what the ramifications are of training the data, or using the first 50 years or whatever, 70 years I think you used of CSM2 as the training data, and then validating it against a future climate period with like different radiative forcing, basically. Would you have gotten different results if you had trained, say, on the first 50 members of CSM2 in the present, and then tested against the second 50, for example?
Yeah, definitely. But then in the machine learning context, that would, like, we kind of get into the zone of this data leak, where we feel that the model has already seen those kind of patterns before. So it's not a very good understanding of how well the model understands the underlying physics to be able to predict what happens in the future. So
it doesn't matter if radiative forcing changes the patterns that are present.
So right now we are not seeing that. I think the concept is that, yeah, it'll definitely, like if I evaluate it on the exact same time periods, my performance will look a lot better because it has a more better understanding of the current time periods. But we also want to understand whether the model is understanding those large scale features, which do not change as rapidly, probably. So, yeah.
Wondering, you talked about the quantity of data, but not necessarily quality of data. How important is it? I mean, the reanalysis product can be garbage as well, but it might be more valuable than other products.
Yeah, definitely. Quality of data is extremely important, and I think just apart from quantity, the quantity has to be diverse as well. So that is something that we need to focus on. But when it comes to these, as we have seen with AI foundation models, because these models are given so much amount of data that at one point, the quality does not matter as much because they're able to pick those large scale features, and that's what we are focusing on. So even if the quality is a little bit degraded, as long as it's able to pick out those large scale features, we can then do a fine tuning on higher quality data, which we are doing here, where like we are fine tuning on ERA 5 to get that quality factor in.
Thanks. Since you're training on CSM data, I was wondering if you compare to the skill of the initialized CSM simulations.
Yes, excellent question, and that's something that's been on our mind as well. We haven't done that evaluation yet, but we plan to. So, yeah, thank you.
So I have a quick question. We have a little more time, so I'm going to take a little prerogative to ask a question here. So you're talking about the large-scale features, and that implies some sort of reduced dimensionality state. And I'm just curious if you've sort of looked into what are, I mean, you mentioned ENSO, but what are these large-scale features, and how do they differ from what we kind of already understand about large-scale features that might lead to S-to-S predictability?
Yes, that's also a very good question, and that's something that we have in the pipeline. Like ENSO is one, there's MJO, there are other modes of variability as well. So we have that in the pipeline, we haven't evaluated it completely against that yet. Yeah.
Our next speaker is Paul Diermeyer.
Thank you. So yes, I'm going to talk about fidelity of land-atmosphere interactions in CESM, since they are presumed to have a lot to do with subseasonal predictability. So just a review for those who maybe aren't so familiar with this part of Earth system and Earth system modeling. Our notion is kind of our starting point is this one-dimensional picture of a sort of a local vertical coupling between land and atmosphere through water and energy cycles. So we've got this sort of chain of arrows and processes that we show on the right that basically assuming that the downward arrows are given and known. When it rains, the ground gets wet. When the sun shines, the ground gets warm. It's the upward arrows that are more subtle that we're trying to get at, those feedbacks. And so any broken links, any arrows that are pointing the wrong way or missing in the chain will interrupt any sort of land surface impacts on weather and climate predictability. And so where and when is our question. Are these feedbacks in place in the real world, and how strong are they? And then, of course, do our models get this right? So in the context of CESM, it's the bottom row of arrows that is the domain of CLM, the land model, and then above the surface fluxes, the arrows to the near surface states, boundary layer processes, cloud physics, and precipitation. That's the realm of the atmospheric model. So in its sort of most basic form, we are looking at the land state of soil moisture as a potential driver or control of surface fluxes. So we have here a schematic diagram, evaporative fraction that's on the y-axis over here. So that's just the ratio of available energy at the surface that's going towards the latent heat flux. So nominally between 0 and 1, but it can go outside of that range. And the x-axis is soil moisture, and we talk about there being these different sort of regimes of coupling between land and atmosphere. So, well, actually, let me go back. So we have a dry regime below the wilting point where essentially you don't have any evaporation. The water is too tightly locked into the soil. Above some critical soil moisture, it doesn't really matter when the soil moisture varies. Evaporation is occurring at the potential rate, and any variability in evaporative fraction is from other sources of the climate system. But in between, there is this sort of sweet spot where there tends to be a pretty strong and fairly monotonic increase in evaporation as soil moisture increases. And that is where the land surface has control in this transitional range over the surface fluxes, and that's the first step in the race towards this connection between land and atmosphere. And so because of this, soil moisture can regulate energy, net radiation partitioning only within a certain range, and those boundaries are different in different locations in the world. And the ability of the climate to move into or out of those different locations is expansive or limited in different parts of the world, and also by season. So we're going to look at some runs that Meg Fowler has done with CESM 2.1.5. There's land model only runs, and then coupled land atmosphere runs, no ocean, not fully coupled. 26-year simulations at nominal 1 degree, basically to diagnose the behavior, sort of stress testing the model. And so this is not getting at the S2S prediction skill directly, but at the characteristics that are necessary to harvest the prediction skill at subseasonal timescales. We'll also be looking at, for comparison to ERA 5, as Gokhan said, you know, it may be garbage, but there definitely are problems with even ERA 5 reanalysis when it comes to things like diurnal cycle, which are crucial for land-atmosphere interactions. But we will compare to that on its nominal 31 kilometer original Gaussian grid. And also for fun, we'll also look at MERA 2, at least locally at flux tower sites. We will do global comparisons as well as local with ERA 5. So for these local comparisons, looking just over continental US, there are, around the globe, very unevenly distributed, a large number of flux tower sites where we have meteorological measurements, radiation, soil moisture, surface fluxes, carbon even, all co-located. And over CONUS, there are several hundred stations, but about 60 to 70 that have long enough high-quality time series that we can apply to this problem. And the number varies from season to season, actually. But these are the places where we're doing our point comparisons. And we're looking to start with specific coupling metrics. First, very simply, Pearson's temporal correlation, correlations between soil moisture and latent heat, soil moisture and sensible heat, and then soil moisture and this evaporative fraction. We're also looking at the variability, standard deviations of each of those terms. And then we also have a coupling index, which is just the product of that correlation between a driver, soil moisture, and its response, say latent heat flux, for example, times the standard deviation of the latent heat flux, which is combining then this magnitude of fluctuation as well as the tightness of the connections. And so you could do this on any of those arrows that I showed in the diagram, but we're going to start near the surface and see if we can chain these together. Now, this horrible looking plumbing diagram, it looks like when Robert De Niro takes the panel off the wall in Brazil. This is what's going on inside of our models. Oh, good. People got that reference. I'm not that old. On the left, we're showing, this is a single site, and in fact, locally, Niwot Ridge Forest, not too far from here. On the left, we're showing what says OBS, but it's really ERA 5. Actually, the ERA 5 is supposed to be on the second side. I don't know why it popped down there, but on the left column is, so this is kind of a wiring diagram or a pipe diagram of all those arrows I showed you before, that little schematic. From bottom to top is land surface up into the atmosphere. The width of any line is the strength of that coupling index. How strongly is it coupled? And the arrow tells you what direction this coupling is going. The color goes from blue, negative correlations, to white, no correlations, to red, strong, positive correlations. And then the darkness of the green of each box is telling you the magnitude of that standard deviation. So there's a ton of information packed into these things. But what I want you to basically look at is on left is observations. ERA 5 is actually the second box. And then CLM coupled with CAM. And on the far right is CLM. So just to draw your attention to a couple of things. What we see in observations is that net radiation has a very strong control over sensible heat. And that's really driving the evaporative fraction in this location. Whereas we see, both in reanalyses and in CAM and in the CAM CLM, that's really not what's being portrayed. So we have an issue. And in fact, if you look in the very tiny small print, what you have is you have evergreen needleleaf forest at this site, and ERA 5's grid cell says, oh no, we have broadleaf forest here. And even CLM has a mosaic that's mostly saying we have mostly grassland at this site. So land cover is something that can complicate and sort of mess up your simulations in these locations. But that's probably not all that's going on here. For instance, on the left side, though, you see something that's maybe more encouraging for the in-car crowd, is that we have this overcoupling of soil moisture to latent heat flux and evaporation in ERA 5, which we don't see in the observations, and actually CLM and CLM CAM, they match up pretty well in this particular location. So, you know, that's, you can really get into the weeds in this sort of picture, but we really want to back out and see what's happening on a larger scale. So Yoon Kim, my postdoc, put this together. This is actually showing across all of those individual sites in the US the seasonal cycle of the variation between soil water content at the surface, that's the x-axis, and down here, and evaporative fraction on the y-axis. And he has this weird sort of coloring scheme where March through August are the red numbers, and there's a line that goes from January to August, and December is a blue number. So you can kind of trace the seasonal cycle. And again, the labels got a little bit shifted for some reason here, but on the left side is what we see in observations, and we see that we have lowest evaporative fraction in February and the highest in late summer, and there's this little counterclockwise sort of hysteresis that goes on between these two, which is actually fairly well captured in CLM and CAM CLM. They both sort of reproduce that, and they have the seasonality phased right. When you look at reanalysis, it really is garbage. The timings are wrong, and in fact, ERA 5 is actually, the hysteresis goes clockwise, not counterclockwise. It's really not representing the process as well. Data assimilation might be messing with this in some part, and Mira too. I have no idea what's going on there. It's just crazy. All right, what we all call Yaga's paper, right? The Richter et al. 2024, where they found in CESM this lack of a response of atmosphere or even kind of ocean in terms of providing subseasonal predictability, matching the sort of infamous diagram here on the left, where we have this presumption that somewhere around 1 to 2 weeks, the land surface initialization impact should be quite strong. And we do see that in other models. In fact, even one that's really not all that great at land-atmosphere interactions, but it does show, CFS2, NCEP model, does show a kind of a peak around 15 days in terms of how the land surface is affecting, in this case, 2-meter air temperature. So what's going on here? Well, we can look globally now. We need to look at the big picture. Because and historically our notions of these coupling has come from looking at models. We haven't really had observations except at points like I've shown you, flex tower sites. So what we're trying to tackle is to produce a global picture of land-atmosphere coupling based on observations, or at least products that are as close to observations as possible, leveraging a lot of remote sensing data. And we'll be focusing only on this one arrow down here, what I've been talking about already, the soil moisture evaporative fraction, and see what's going on. So first of all, just to show you what the models look like before we bring in the OBS, on the left is this offline CLM run. This is this coupling index between soil moisture and evaporative fraction. On the right is CLM plus CAM, and on the bottom is the correlation part of the metric. So just the correlations of daily values in time during June, July, August is what's being shown here. So you kind of see these reddish blobs in places like the Great Plains of the US and the Sahel and India. Those are those hot spots, the Randy Koster famous hot spots, Ukraine, Eastern Russia, so forth, like that. So, okay, fine. We can compare to ERA 5. We already know this is model to model. It's not really telling us much about reality. So what can we do to validate these models globally and properly? Well, graduate student of mine, Nazanin Tavakoli, has been working on this, looking at 3 soil moisture data sets that are all primarily satellite-based. They're not fully independent of each other, but they are based on daily observations. SMAP, the NASA product, CCI, which includes SMAP and many other satellite products, and then this SOMO.ml, which folds in a bit of machine learning as well to try and do some training on that. And 3 different surface flux products, which are, again, using satellite data and things that are not fluxes, plus various sort of machine learning regressions onto flux tower sites to infer surface fluxes. Fluxcom XBase, the Gleam 4.1, which actually in our test validates the best against in situ data, and Camille, which is kind of a multi-product ensemble. Everything interpolated to a quarter-degree grid, 3 times 3, 9 ways to combine these. Because they're not totally independent, it's not 9 degrees of freedom, but we can get some picture at least of uncertainty by going this approach. And amazingly, oh boy, the lettering shifted again. Amazingly, there's a tremendous amount of agreement, a lot more than I would have ever expected. So this is showing our certainty about whether they're portraying all of a particular region in the same regime across all combinations of products. And any place where you see the cyan color, that's where there's a lot of agreement. So we think that we genuinely have things portrayed correctly. And the little red strips, which are only mostly a couple of 100 kilometers wide, is where we have uncertainties between this boundary between where the moisture limited versus the energy limited domains are. So you can come in and then say, well, gee, if your model has its transition zone somewhere near this line that's kind of running around maybe 95, 97 degrees west and sort of across Canada, and then along to the east along the Gulf of Cuba, then you're doing pretty good. So this is what the correlations now look like, just the correlation part. So SMAP, CCI, and SOMO on the top, everything correlated with the Gleam product that we think is probably the best. You see they all look very similar in patterns. It's just basically shifting where the 0 line is. SOMO tends towards lower values and more negative values in the tropics. SMAP has the least negative values. CCI, they screen out the very high LAI, so the rainforests are kind of masked out in that particular product. And then below that, we have CLM and CAM, CLM and CAM plus CLM. Very strong agreement on pattern among the observational products. And actually the models, not too bad. We seem to have quite good agreement with CLM. When it's coupled to CAM, then we kind of get too much positive correlation spreading out over too much area and too strong as well. For instance, look at Southeast Asia and China, which everybody, every model, every observational product says there's no positive feedbacks there, but CLM CAM is giving positive feedbacks of land and atmosphere in Southeast Asia. So coming back to the regimes, if we try to define these regimes now, so you know, we have our sort of 3 legs in our sort of linear diagram here, and so we can characterize that between, is any location occupying 1, 2, or all 3 of those regimes based on its sort of climatology. And this is This is based on the SMAP versus GLEAM. So the colors tell you, are you in the wet regime only, in the transitional in the wet, et cetera. And the little bar chart tells us from observations what we feel is going on based on those products. And what we see is that as long as you have anything that's on the left of the critical soil moisture line, that means the land surface has an ability to give a feedback. Through the moisture and energy cycles in the transitional regime or in the dry regime, that's where we have extreme heat cases where we get this really positive heat wave feedback can occur, even though the water is maybe not playing. And we see that more than half of the globe seems to have some sort of a land surface feedback connection going on. And if we look at the models, not too bad, but one thing that we do see in both CLM and CAM is that, one, they have too much of the area that just sits always in the transitional zone and not enough area that ever gets into a dry regime. You don't see the red and the yellow and the cyan showing up, which would mean this model maybe is going to struggle with forecasts of extreme heat. And zooming in on North America, you can kind of see, oh, do we have that boundary in the right place? CLM, not too bad. CAM, the blue is too far to the east. And anyways, but it gives us something we can really start to validate our models with. So summarizing, we're beginning to look at these coupled feedbacks in CESM. There's still a lot that we can do. And a really key resource is going to be these observational estimates. Something I haven't mentioned, but it's sort of another elephant in the room is vegetation, which can exert a lot of control and is not typically part of this water and energy cycle view, but carbon plays a role as well. And so we know CESM does a lot of carbon. So I'll leave it there. Thank you, Kathy.
All right, in the interest of time, we will not take questions right now. Please do ask Paul questions when you get a chance after or during discussion. If you'd like to talk more about the land-atmosphere interactions, we can do that. Our next speaker is Judith Berner.
Hello. It's great to be here. I'm going to talk about benefits of online bias correction versus post-processing. So subseasonal to seasonal forecasts have generally very little skill, except so-called windows of opportunity where temporary skill emerges. Here we study the impact of an online bias correction on forecast skill and compare it to a posteriori bias correction. The problem we have with our S2S system here at the CSM S2S suite is that we don't initialize it from reanalysis that have been generated by the same model, but we initialize it from foreign initial conditions. And so we have a drift in our system. And to deal with this, we need to remove the lead time dependent bias, which typically requires a large set of hindcasts. Systematic biases reduce forecast skill, so Abby will talk, it's the next talk, which maybe would have been much better after Paul's talk, but that's fine. So why do we need an online bias correction? So here sort of is my attractor. This is actually a attractor of CSM, but the idea is that if we have systematic biases, let's say the SST is just too cold, let's say over the North Pacific or the North Atlantic, it's systematically too cold, then we can never spin off a hurricane. And so there are certain things where we cannot do a posteriori processing to get at the right skill. So the idea is that you need to be on the attractor, you need to move the model to the right side of your slope so that the dynamics which is in the model can spin off and produce the right results. The experiment setup, so this is a version of the S2S suite here at NCAR. So it's the coupled climate model, it's 1 degree horizontal resolution, follows the SubX protocol, which means weekly initializations from 1999 till 2022. We initialize from NCEP CFS. So this is basically we take one reanalysis, and then we use anomaly initialization, so typically January 1st anomaly on top of January 1st initialized forecasts to come up with an ensemble. Here is my portray of the lead time dependent model bias. So here we see a model error. So here we see different weekly initializations. We see the observations. And as we initialize, the model can fill the model attractor, which is sort of here schematically by the red line. And so in addition to the forecast, the model drifts towards the model attractor. And so this is one reason why we have this lead time dependent bias. And so this happens in S2S forecasts, and it's even more extreme if we have initialized decadal forecasts, where it can be really 10 years or more before the system is done with this spin up and actually makes a good forecast. One reason why we do have skillful forecasts is that we remove this lead time dependent bias, and that makes our forecast a lot better. And this is great. We want to have very skillful forecasts, but there is a big part of model error that we never see because we're systematically removing systematic biases by looking at correlations. That's the point of the talk. Okay, so just to quantify this, here is week 1, 2, 3, 4, and 5, 6 forecasts for 2-meter temperature. This is just a global mean. And so in blue is shown the model after removed the lead time dependent bias, and in red, the original raw data. And so we're getting like about a 30% reduction of RMS error if we remove the lead time dependent bias. This is great, but this is model error we have that we should address if we want to improve our models. Here, this is some work by Will Chapman and myself, where we came up with an online model error correction based on nudging tendencies. So we were nudging the CSM towards error 5 data. We took a big library and came up with a systematic effect. We did a number of simulations based on nudging, stochastic and deterministic versions, and also using data assimilation increments. Those are these different colors. It's stratified by the season. But what we found is that the RMSE is improved globally by 10% for 2-meter temperature and up to 40% for sea level pressure. This improvement was there in all surface variables, but also if we look at the free atmosphere, most of the things are improved with the exception of a few things like the moisture profile. So this is published, and so now what we wanted to do is, so this was done in climate simulations, in 30-year simulations of a free-running climate system. So now we wanted to see, well, if we put this into our forecasting systems on the S2S timescale, by how much can we improve the skill? So here, this is root mean squared error, and so here in the shading, the light shading is the root mean squared error for 2-meter temperature left and sea level pressure on the right side. If we remove the lead time dependent model bias, then we get the solid contours. So again, we see sort of this roughly 30% improvement in RMS error if we remove the lead time dependent bias. And if we look at the difference between the red and the blue, it tells us how much more having an online model error correction improves skill. So these are small numbers, but we can further improve the skill by having an online model error correction while we run the model. This is the ACC. So we see here the anomaly correlation. Again, in solid, we see the improvement by having an online bias correction out to weeks 5, 6 for both 2-meter temperature and sea level pressure by about 10% or so. So it is beneficial, but it is small in comparison to removing the lead time dependent bias. This is the end. So I just wanted to show you some pictures of this. So the bottom is the difference with and without removing the bias. And we sort of have the same problem, which is that we can look at the pictures and maybe make some assumptions. For example, it seems something is going wrong over the warm pool. Obviously, the southern oceans are not well captured, and so this is where introducing that model error correction is really helping, but more work is needed to then really feedback and make the model better. Thank you.
How much of a cost does it add to do the online bias correction, and do you think it's worth it for those changes?
Yeah, so it's very cheap. So what we're doing here is basically reading from a library, and so these nudging increments are stratified by time of the day, and there's a seasonal cycle, and you can do it deterministically or stochastically, where you can put in a typical January 1st anomaly on top of it, so it's very cheap. But Will has done some more work where we actually go a step further and rather have the nudging increments. We're machine learning those. So then we have a state-dependent online modeler correction, which, for example, helps with the MJO. And this one is also pretty cheap. So we can run this really fast thanks to the great collaboration with the software engineers.
So one benefit of having the online would be, I guess, if your errors are non-stationary, do you see like times or places where the online correction is maybe contributing especially well, or is it mostly this kind of blanket several % improvement?
That's a great question, and I haven't done the analysis to say this, but we know that the state-dependent version learned on the nudging tendencies is much better than just putting the nudging tendencies back in. So I would assume there is a state dependence, and this is exactly what we hope machine learning to do, is get that state dependence in.
The question is, do you have to still do the de-drift post-processing even when you use the online nudging?
Yeah, so those are these plots. So the light versus the solid tells you how much removing the lead time dependent bias gives you. So this gives you 30%. It gives you a lot of skill, both in, this is RMSE, but also in ACC. It's the next plot, also in ACC. And then the difference between the online bias correction or not is blue versus red. So what we're doing is really, really small in comparison to removing the lead time dependent bias. And so there's still lots of work to do in our initialized forecasts, and Abby will address some of these issues in the next talk.
Well, it's clear that our next speaker is Abby.
Hi, I am Abby J. I'm an associate scientist in M-Cubed. So this is my first CESM workshop. It's very exciting. Yeah, even though I didn't stand up yesterday because I was lazy, let's say. All right, I will be talking about looking at sources of subseasonal prediction skill in CESM within a perfect modeling framework. And in a perfect modeling framework, instead of comparing to verification, like observations, we're comparing to a member of the model, just an ensemble member. So this is based on work that Richter et al. Did. It was published in 2024 that investigated the sources of subseasonal to seasonal predictability from initializing the ocean, atmosphere, and land components. So they did multiple different runs where each component was taken out, and you can see like what the impact of the initialization was. So they did see that initializing the ocean adds limited predictability on the S2S timescale. We need more time there. And then also initializing the land deteriorates the scale on the S2S timescale, which is not great. These results pointed to some possible problems with the initialization drift or spin up and coupled model drift. So again, here we're going to repeat the analysis, but in a perfect model context, where we can eliminate the model error, but not the initialization drift. So just quick, this is the same kind of setup that Judith talked about. We're using CESM2 at 1 degree horizontal resolution in the atmosphere and ocean. And we have weekly initializations, 1999 through 2022, initialized each Monday for each month. And they follow the sub-X protocol with 11 ensemble members initialized from CFSV2 using an anomaly initialization. So prior to verification, the lead time dependent bias is removed, and then model error does arise from shortcomings in the parameterization schemes and in the interactions between the model components. So you've seen this before, just a few talks ago. So this is adapted from Diermeier's paper, but it was in Jager Richter's paper in 2024. It's a hypothesis on what the impact of the atmosphere, land, and ocean, initializing the atmosphere and an ocean is on predictability. So, but here we want to quantify the value of these initializations. We quantified it by replacing the land, ocean, atmosphere with their climatological counterparts, and then we verified it against the fully initialized simulations to see exactly, like, just like removing a variable and then seeing what impact that variable has on the model run, on the performance. So this is from Yaga's from Yaga's paper as well. So this is annual temperature, 2-meter temperature, ACC over the northern hemisphere mid-latitudes, so it's 30 north to 60 north. So on the right, we're comparing the CESM hindcasts to CPC temperature observations. And we can see that the hypothesis did not come to be. The atmosphere has the biggest impact, obviously, in weeks 1 to 2. But after that, we see that the initializations of the land and the ocean don't really have much impact and can be detrimental. So in this figure, I'm showing ACC for weeks 1 and 2 and 3 and 4. Those are the columns. And the rows, I have CSM2, like the original run at the top. And then the one, the Climo land without the land initialized from climatology. And then I have a difference plot at the bottom. So that's the original run minus the Climo land run. And it is somewhat hard to see with these projectors, which is unfortunate, but it is mostly blue, which is not great, which means that initializing the land is detrimental to the performance of our model run. So to address this and kind of like get some more information about what's happening in these runs, we're going to repeat the verification in a perfect model framework to eliminate the model error. So here I added one more figure on the right. So this is looking at it where I say that the observations are just like ensemble member number 10. I just chose one at random. So we can see that the atmosphere does play a similar role as in the previous ones, but the land plays a much larger role. It does increase the skill significantly, and the benefits grow throughout the S2S range. So the benefits from initializing the land are markedly higher than in the ocean and the S2S range, looking at it in this way. And this can point to a coupled model error between the atmosphere and the land as an essential problem in these simulations. So here we're looking at the 2-meter temperature ACC scale in the perfect model for JJA and DJF, so 2 different seasons. And then again, I have CESM2, the Climo land, and then the difference in the bottom. So we can see that initializing the land is beneficial when looking at it from this perspective. Scale is added, especially in the tropics and the summer hemisphere in the bottom left. But in general, there's more red than blue in these figures. And just to like hammer it home here, comparing the perfect model to the verification with observations, you can really see the differences here, and that initializing the land is important when looking at it from the perfect model framework. So I made this talk for EGU, and the talks were much shorter, and I needed to add some content, so I just looked at precipitation as well. So the scales on these figures are different. So it is still really red, but the scale is much lower for ACC. So looking at seasons again, this is JJA and DJF, and the same rows. But we can see that, again, initializing the land helps precipitation, but on a more regional basis. Looking at northern South America and kind of northern Europe, especially in JJA, but it's a more regional basis. And then also, I'm not quite sure what's going on in Africa in DJF. That's something to look into as well. And then comparing these to the verification with observations again, you can see that there is a very large difference when looking at it from the perfect model. And then if anyone's curious, I also made these like line plots for ACC. So looking at it, comparing to observations, we see that everything is quite low, including the atmosphere, which we know. But in the perfect model framework, there is some improvement when looking at the land initialization. And this is like this is the best performing area I tried. I looked at a few different mid-latitudes all over the world, but this is over the tropics, 30 south to 30 north. And then also with the ocean, not surprisingly, initializing the ocean doesn't help early on, but it does improve after a few weeks. And then in conclusion, I'll just summarize what I talked about. Yaga in 2024 investigated the sources of predictability from initializing each of the 3 components. And it was found that initializing the ocean and land is not as beneficial as we thought when verifying against observations and reanalysis. So here we repeated the analysis, but verified against an ensemble member instead of observations. And in the perfect model, we saw that initializing the land does add significant skill, and the benefits grow throughout the S2S range. So again, this points to coupled model error between the atmosphere and the land as an essential problem in our simulations. And that's all I've got. Thanks.
Oh, that was very interesting to see. I mean, kind of hopeful in a way.
Yeah.
I don't quite understand why you come to the conclusion that it's a coupled atmosphere land model error problem as opposed to an initialization problem, because it seems like by doing the perfect model simulation, model against model, how do you come to that conclusion? Let me just ask that.
I'm gonna ask Judith to answer that because I don't know. I think she would have been better.
Okay, well, there might be yet one more set of experiments where we could separate those two, but yeah, we can talk about that. Yeah, with this framework. Yeah, okay, thanks.
Yeah, that'd be a super interesting talk. Trying to figure out or think through what properties of the land surface might be responsible for this. Do you think it's, for example, getting the soil moisture and the moisture in the soil system correct, because so much precipitation is due to recharge the atmospheric moisture from evaporation from the Earth's surface, so that could have a big impact on storm systems over land. Do you have a sense of which properties of the land surface are there some that are more important than others in this context?
I mean, I would definitely say it's soil moisture, at least with my perspective, is the most important. And I'm doing some tests with Meg on this data right now, where we're kind of doing some state-dependent work based on different states just over North America of how wet and how dry it is, seeing how these perform in those respects and how big of a deal it is.
Does initialization also affect evapotranspiration rates? Do you know?
I don't know. I would think, but I'm not sure.
Thank you. Very interesting results.
Thank you.
I have a question. I tend to think of this perfect model stuff in the context of getting the signal and the noise correct. So I'm wondering if maybe you can help me think about this in the context of a signal to noise. So if the model's very good at predicting itself, does that mean it's misrepresenting the signal? Like if it's much better at predicting itself than it is in predicting the real world, does that mean, is that in itself a sign of model error, that the model has is sort of maybe too persistent, or there's some error that makes it really good at predicting itself compared to the real world? Or is there some issue of not getting the noise correct that sort of is affecting that signal to noise ratio as well?
I have no idea. Again, Judith, I don't know if you have anything.
CSM is very under-dispersed in the topics. This is why we need to So, yes, it gets, I mean, the reason that the skill is so good in the topics is because the ensemble is
Yeah, I mean, I think that, to me, that points to some sort of model error in itself, that when the model is really good at predicting itself, and I think, I personally feel like we have to be careful about this perfect model assumption, because making conclusions on this perfect model assumption when we know, in fact, our model is not perfect always makes me a little nervous.
Question about the perfect model approach. I think I read that when you compute the model scale in the perfect model setup, the choice of whether or not to include the member that you choose to verify against makes a difference. Like, I'm curious, like, in your approach, did you include or exclude that member for verification?
I just chose a member at random.
Yeah, but then when you verify against that one member, for example, you have 11 ensemble members, right? You choose one as verification, and then when you calculate the scale, do you use the rest 10 or use the 11 total?
I removed that member.
I see.
Yeah.
I'm just curious about that.
Mm-hmm.
Really cool work. I was wondering, it looked like the anomaly correlation coefficient was increasing as a function of lag time with the atmosphere initialization, even in the perfect model.
Mm.
Can you comment on that? So that's a kind of a difference from what you might expect in the theory picture. Yeah.
So can you explain your question again?
Yeah, so on the far right, this is the perfect model experiment. And so if you look we might hypothesize that the predictability is highest at the shortest lead times when you initialize in the atmosphere. But in fact, we see that we have higher predictability a few days out.
Mm-hmm.
And I'm just wondering what might cause that.
Yeah.
In a perfect model.
Yes, because so a verification against an ensemble member, but it's still initializing from how CSM is initialized.
Oh, okay. Yeah. Okay. Thank you.
Yep. Great, thank you.
Our next speaker is Isla Simpson.
All right, thanks. So this is going to be about the impact of vertical resolution on seasonal prediction skill in CSM2. So this is a project in collaboration with CW3E at Scripps. They had the computing time that made this project possible. So here you're seeing the vertical grid for the standard version of CSM2. This is the grid that was used in the original SMILE ensemble that was led by Steve. And what we're doing here is going to compare prediction skill in simulations that use this grid with skill in simulations that use this red grid, which is the new grid for CAM7 almost, except it doesn't have changes in the boundary layer. So CAM7 is going to have a higher model top, an 80-kilometer top, and enhanced vertical resolution in the troposphere and lower stratosphere. And so we're looking at the impacts of this new grid on seasonal prediction skill. So we have two new seasonal hindcasts, one with the original 32-level model and another with this 83-level configuration. These are both using CSM2 with no real physics changes. They're following the same protocol as the original SMILE, but one difference is we're initializing from ERA 5 because it goes high enough up. And here I'm just going to focus on the November 1st initialization and compare the skill between the 83 and the 32-level model. So I'll show some skill metrics. In each case, we're going to remove the lead-dependent climatology. I'll show the anomaly correlation coefficient, so a value of 1 is perfectly correlated, 0 is not correlated. That doesn't necessarily tell you whether you're getting the magnitude of the signals right, so I'll also show the mean squared skills score relative to climatology. So a value of 1 is there's no error, value of 0 is you're not better than climatology. So if we're going to have skill on seasonal timescales, it's going to come from slowly varying boundary conditions on the troposphere that are predictable. So ENSO is an obvious example. But the QBO is also a slowly varying boundary condition. So this is an oscillation of the equatorial zonal mean zonal winds in the stratosphere with a period of about 28 months. And if we can predict the QBO, and if it has impacts on the troposphere, we might expect that predicting the QBO would lead to some skill on seasonal timescales. So first of all, here's the skill of the QBO. So this is showing equatorial zonal mean zonal wind. We've got anomaly correlation coefficient on the top and mean squared skill score on the bottom. So this is for the 32 level model. And so it has skill in the lower stratospheric winds, but it kind of falls off pretty rapidly with lead time. This is with the 83 level model. And so you can see we have way more skill in the QBO with this new vertical grid, and that's the difference between them. And that becomes very clear if you look at QBO composites. So here's the composites of westerly and easterly QBO in ERA 5 reanalysis. That is what it looks like in the low top model, and so you can hold on to the lower stratospheric winds for a bit, but you're really not capturing the structures with the low top model. And then in the high top model, the 83 level grid, we do a way better job at capturing this seasonal evolution of the QBO. So now that we can predict the QBO, how does that impact on skill and things we might care about? So here we focused on features that have been argued in prior literature to be connected to the QBO. So there's been argued to be a connection with the northern hemisphere polar vortex, the North Atlantic oscillation, Madden-Julian oscillation, tropical precipitation, tropical easterly jet, and the subtropical jet in the Pacific sector. In the interest of time, I'm not going to talk about these three other than to say there's no skill improvement. In general, this is going to be a talk that is filled with disappointment, but I'm actually more interested in the role of the QBO and potential predictability than I was before we started. So hopefully I'll convince you of that by the end of the talk. So let's start with the northern hemisphere polar vortex. So the Holton-Tan effect says that during westerly QBO, the northern hemisphere polar vortex is stronger than during easterly QBO. And you see that here in this observation-based composite. So now that we can predict the QBO, do we see that manifest in enhanced skill in the northern hemisphere polar vortex? So here's the skill in DJF average zonal mean zonal wind in the low top model, and you can see that we have no skill in the northern hemisphere polar vortex. So does this look better now that we have prediction skill in the QBO? This is what it looks like with the 83 level model, and you see we still unfortunately don't have skill in the polar vortex, and that's the difference between them. So even though we have this much improved skill in the equatorial zonal winds, that doesn't seem to appear as skill in the polar vortex. So why might that be? Is the Holton-Tan effect just not a real thing, or are we not representing it correctly? So here I'm focusing in just on January, which is the month when in the observational record, that link between the QBO and the polar vortex tends to be the strongest. So you've got here in ERA 5 a correlation of about 0.5. In the low resolution model, we have a correlation of 0. The nice thing about these initialized hindcasts is we can do some sampling. So for every initialization date, we have 20 members. And so we can just randomly select individual members from each initialization date, string them together, get a single member time series, and ask what is the range of correlations you can get between the QBO and the polar vortex with these single member samples. And so when you do that with the low top model, that's the range of correlations that you can get between the QBO and the polar vortex. And you can see that you don't reach the value in reanalysis saying that something is going wrong in this low top model. So what about the high resolution configuration? That's the range of single member correlations you get in the high res configuration. And so it's a little bit more positive, but you still don't encompass ERA 5, again, suggesting we're not doing something right. But if you look at the ensemble mean correlation in this high top model, you do get a correlation that is as high as what you get in the reanalysis. But we've had to average over 20 members to get that. So it's kind of pointing towards maybe a signal to noise issue. And so if we have that correlation, why don't we see that as skill in the polar vortex? And I'm still, I think, trying to get my head around this fully. But I think it's because this is a small signal. There's a lot of unpredictable variability in the polar vortex. But it's also a smaller signal in the model than it is in the reanalysis. So if instead of doing a correlation coefficient, we regress the polar vortex winds onto the QBO, you have a much higher regression coefficient. So kind of the slope of that relationship is bigger in reality than it is in the model. Again, maybe suggesting that we have a signal to noise problem in this relationship between the QBO and the polar vortex. So now I'll move on to the MJO. So this has been argued to be connected to the QBO. This is showing a metric of MJO activity. It's the standard deviation of MJO filtered OLR. So in the climatology, you've got a bunch of MJO activity here. And then this is the difference between easterly and westerly QBO. So in the observational record, easterly QBO is accompanied by more MJO activity. Here's what that looks like in the low top model, and we don't capture that signal. And so now what does it look like in this high top model where we have good skill in the QBO? Unfortunately, we still don't have the QBO MJO connection. But we can do our sampling game again, and we can pick out this maritime continent region. Here are ensemble mean differences in the MJO between easterly and westerly QBO, and there's era 5, and we can ask, do we get any individual member samples that give you as big of a difference as you get between easterly and westerly QBO as you get in era 5? And the answer is no, there's not a single one of these 1,000 bootstrap samples that does that. So this is just building on, I think, what we already know, that models seem to be failing to capture this connection between the QBO and the MJO, but doing so in this initialized framework where, of course, all the ENSO aliasing and things is, you don't have to worry about it because these are initialized. Okay, I'll finish up with the subtropical jet in the Pacific sector. So here you're seeing in era 5 the difference between westerly and easterly QBO, and of course there are many other factors like ENSO and things could be going on here. I've always been a bit skeptical about whether this is really a signal related to the QBO. But if we average over the longitude sector of the Pacific, this is the latitude height structure you get. And it's definitely tempting to think of these as kind of being tendrils of zonal wind anomalies coming out of the QBO and teleconnecting to higher latitudes and lower altitudes. So now that we have this good skill in the QBO, do we see improved skill in the upper tropospheric winds in the Pacific sector? And so here's the skill of upper tropospheric zonal wind in the low top model. Here's the high resolution model and the difference between them. And again, we do not have improved skill by representing the QBO. That's because you don't see this difference between westerly and easterly QBO in either of these configurations. But if we look at our latitude height cross-section, I'm kind of struck by how much more similar to reality the 83 level model looks. It just is kind of a lower amplitude. And so is there a chance that this observed signal is really a real QBO signal and the model is kind of trying to do it but just doesn't have the amplitude right? And so what we could do is take out the QBO part. We have a pattern correlation of 0.75, so that's pretty high. And we could regress this era 5 pattern onto the model ensemble mean. And then we can do the same with all of the individual single member samples and asked, is that pattern regression coefficient higher than what you can get by regressing the model against itself? And so that's kind of maybe like a signal to noise paradox metric, but in the form of kind of a teleconnection pattern. So here's the regression of era 5 onto the ensemble mean. So it's kind of saying that the pattern is like 2.5 times higher amplitude than the model ensemble mean. And now we can look at individual member samples, taking the model and regressing it onto the ensemble mean, and that's what you get. So there's a very small chance in the model of getting a pattern that is as correlated and as high amplitude as era 5, but it's like a 1% chance. So I'm kind of 99% confident that the model, that maybe the real signal is bigger than what we get in the model. So I'm probably out of time. I will leave my conclusions up and take any questions if there's time.
Hi, Isla. Thank you. That was really great. I'm wondering if the connections between the QBO and these other places could not just be limited by the vertical resolution, but also the horizontal resolution of the model. Have you guys thought about kind of a high resolution version of Wacom?
Yeah.
Or high top, I guess.
Yeah, I think it would be really nice to try that. Now that I'm a bit more convinced that there maybe really is a stronger connection going to higher latitudes, I think it would be good to see if in higher resolution, like, do you get the wave breaking and its response to the QBO more correct? Maybe gravity waves, like, do we need to resolve them to get this correct? Yeah, I definitely think it would be good to look into when we have higher resolution CSM3 with this high vertical resolution.
Thanks.
Thanks, Isla, for the talk, and kind of following up to what you just mentioned with gravity waves, I wonder how these different vertical resolutions differ in resolving Rossby waves and gravity waves in general, and whether they're propagating more downwards or they don't have that propagation to have these types.
Gravity waves or Rossby waves or both? Or?
No, you mentioned gravity, but I was wondering about Rossby waves. That was my original question. Like, are they different in this when you add the vertical resolutions?
Yeah, they definitely will be. Like the polar vortex is, a lot of it is in the sponge layer in the 40-kilometer top, and so that's definitely messing with the planetary waves and their interactions with the polar vortex. Whereas in the 80-kilometer, they can freely go up and interact more. Yeah. Yes, I think it's probably the model lid is the biggest impact of this, the change in the grids on the Rossby waves would be my guess.
If you could do a similar dynamical statistical correction that you did in your earlier paper where you amplify teleconnection and see if you get better polar vortex skill just from sort of the predicted pattern that you amplify.
Yeah, I think that's a good idea. Yeah, I guess, I guess how confident we are in the magnitude of the connection and reality, I think, is a question. But if it does give us more skill, then we might as well do that. Yeah, that's a good idea.
Thanks so much. Great talk. So now that you thought about the signal-to-noise paradox in this context, how do you think about the classical one with the NAO and the North Atlantic? How do you think about it now? Is it sampling, or do you think it's more than sampling? Thanks.
I think in the UK Met Office model, it's not sampling. I think they've kind of done that test that we don't have a signal-to-noise paradox in the NAO because we don't have much signal. But I do wonder if it's related to this. I mean, I think there have been papers from the Met Office that have argued for a role for the QBO in the NAO signal-to-noise paradox, and I do think there's potential for that. Do you not agree that we don't have a signal-to-noise? Oh, okay, not like the DJF, the seasonal DJF predictions from November don't have a signal-to-noise issue.
Next talk is Evan Meeker.
Hi, everyone. My name is Evan Meeker, and I'm a graduate student at the University of Wisconsin-Madison. And for anyone that was expecting a marine heat wave talk, come talk to me afterwards. I got some cool plots. But today I'm going to be talking about a relatively simple way to test for prediction skill differences between models while accounting for the correlation between them, using Smile's predictions of the PDO as an example. And I've already seen a couple talks today where I think this test could have been applied to give you some significant skill. So I hope folks here find this useful. Thanks to my advisor, Liz Maroon, and to my collaborators for their support, and thanks to NSF and NDSEG for funding this work. So this presentation is based on work from my first paper, which is currently in revision at GRL. And one major takeaway from it is that there's a seasonal dependence for PDO prediction skill in SMILE. So here I'm showing SMILE's ensemble mean PDO prediction skill for each of its initializations, February, May, August, and November. And on the x-axis, I'm showing lead time, monthly lead time, and on the y-axis showing prediction skill calculated with anomaly correlation coefficient. You can see that the SMILE predictions for the PDO are skillful at fairly long leads, staying above 0.5 for all initializations out to lead 13. And you can also see that there's some seasonality in the PDO predictions, which becomes even more apparent when I add an offset to these lines. And so this is now the same thing, but I've added a 3-month offset to the May line, a 6-month offset to the August line, and a 9-month offset to the November line. And the thing I want to point out here is that for the February initialization, you have about the same skill the following February as you do for the November initializations, even though the November initializations are only at a 4-month lead. In the paper, we also used a suite of linear models. To dig into the relative influence of local initial conditions and tropical Pacific forcing on PDO predictability. The simplest of these models is a first-order autoregressive model, which is also known as a damp persistence model or a red noise model because it generates time series with red noise spectral properties. So this equation's easy enough to understand. The value of my modeled PDO at time t is equal to the value at t-1 multiplied by a regression parameter alpha. There's also a white noise coefficient here, but for the deterministic prediction, that's zeroed out. So for the best fit AR1 model, alpha is estimated by the lag1 autocorrelation, which in the case of the PDO is 0.91, which is quite high. So for example, to predict the PDO for comparison to SMILE's February initialization, I would start with the February PDO, multiply it by alpha to get the March PDO, multiply it by alpha again to get the April PDO, and so on. And then I can calculate the ACC in the same manner as for SMILE, and this is what it looks like. And this is what the comparison to SMILE looks like. So the blue line here for the February initialization is exactly the same as I showed earlier, and now we can compare it to the AR1's model prediction skill. We see that the SMILE PDO predictions perform substantially better than the AR1 from leads 4 through 13, and then fall more in line with the AR1 skill at lead times beyond the following spring. Unfortunately, substantially better wasn't quite good enough for reviewer 2, which is fair enough, because this line plot's kind of begging for some confidence intervals. So how do I quantify the uncertainty on my prediction skill? Well, calculating the confidence interval is pretty much stats 101. Any package in Python or whatever your coding language of choice is that can calculate an R value should be able to calculate the uncertainty right along with it. So for a 95% confidence interval, here's what that looks like. And those bounds are a little bit wider than I was hoping for, and that's only the uncertainty on the SMILE predictions. So when I add the AR in, this is making substantial sound a little bit silly. And to be clear, what I would like to see is the confidence intervals for the SMILE predictions and the AR1 predictions either not overlapping or overlapping by a very small amount to be able to say that they're significantly different. And an explicit test for the difference in correlation isn't exactly the same as looking at these confidence intervals, but I've also run that test, and it comes up insignificant for all lead months. But this doesn't feel right. My intuition regarding prediction skill is that even small improvements are meaningful, but this seems to be saying otherwise. So am I doing something wrong here? Well, it turns out my intuition is correct, and the problem with the standard significance test and with the way I was interpreting these confidence bounds is that they assume that SMILE and AR1 predictions are independent samples. But because the models are both verified against the same observations, the predictions are not independent. That is, the predictions from each model will be correlated with one another, leading to biases in the standard test. So what test should we use? Well, we'd like to use a test that explicitly accounts for the correlation between models. And luckily, people have been thinking about this problem for a long time. So this equation that I'm showing here is a test for significance difference between two correlations, which depends not only on the correlation between each model and the observations, but also on the intermodal correlation, which is RAB here. The test statistic, T2, has a student's t-distribution with n-3 degrees of freedom under the null hypothesis of zero correlation difference. And the way that this is different from the standard test, so we have, let's see, we have RAB in the numerator here, which would go up as your intermodal correlation is higher, but we have a cubed RAB term in the denominator, and then another squared RAB term in the determinant of the correlation matrix here. So as your intermodal correlation goes up, this value, or the value in the denominator goes down, and so your test statistic would get higher for the same correlation between each of the models independently and the observations. That is to say that a higher intermodal correlation leads to a smaller, you need a smaller difference in skill to have a significant difference in skill. Okay, so this test was proposed specifically for the purpose of evaluating weather and climate model predictions in Siegert et al.'s 2017 paper, but the test itself is actually much older. So originally it was proposed in 1940 by Hotelling, and the version I'm showing here is a modification from Williams' 1959 to improve behavior over a wider range of input values. The test was recommended for psychological studies by Steger in 1980, and then suggested for basically the exact conundrum I've been having by Stefan Siegert and co-authors in 2017. And Siegert et al. Have done the hard work for me of showing that this test, which they labeled the Steger test, outperforms the standard test, which they labeled the Fisher test. So this figure, modified from their paper, shows that the rate of false rejection for the Fisher test essentially drops to 0 as your intermodal correlation gets higher. That is, the standard test becomes far too conservative as intermodal correlation grows. The Steger test, on the other hand, closely matches the false rejection rate for all values of RAB, which is the desired behavior. So, to test whether or not the SMILE and AR1 PDO predictions are significantly different for each lead, I can follow these steps. First, calculate the correlation between each model and the observations, which I've already done, and then calculate the correlation between each of the models. Then, with those values, I can calculate the test statistic and go get the critical t-value for whatever my significance level and number of samples is. So here, alpha 0.95 and 50 years for the SMILE ensemble. Then for a two-tailed test, if my test statistic is greater than the absolute value of the critical value, I reject the null hypothesis. I have a significantly different correlation skill. And this is what that looks like for this case. So here I've filled in circles for every lead at which SMILE predictions are significantly different than the AR1 predictions. And the results agree much better with my initial interpretation of this plot. So now I can say not that SMILE is substantially better, but that it is significantly better than the AR1 model from leads 4 to 13. And how does this look like for the other initializations? So starting with May, you can see that from leads 4 to 7, we have a significant improvement over the AR1 model. And this is in the boreal fall following initialization. In August, you have those same months showing up as significant, but they're at leads 3 and 4 rather than 5, 6, 7. There's also this period towards the end of the August initialization where you get significant improvement, and I'm not entirely sure what that's coming from, but it's in the spring, so it might have something to do with reemergence. Jury's still out on that one. But for the November initialization, there are 0 lead times where there's a significant improvement in SMILE predictions of the PDO over the AR1 process. And this is of particular note because the decadal prediction large ensemble is only initialized in November. But these results indicate that, at least for PDO predictability, November is actually the worst of these initialization dates to start at. And this result kind of reinforces what I was showing at the beginning of the talk. So not only does the November initialization struggle to predict the spring PDO index better than predictions initialized in February, but it also fails to outperform an AR1 model at all lead times. So in conclusion, today I showed a simple and effective test to look at to look at intermodal correlation, and that it's important to account for this model correlation when you're looking at skill differences between models. On the science side, I showed that the SMILE PDO predictions outperform an AR1 model in February for most of the first year, but that it never outperforms, for the November initialization, it never outperforms an AR1 model. Pending a second review, these results will be available in my paper at GRO. These are my references, mostly for YouTube. And with that, I'll take any questions.
Ask a naive question since I'm not an expert in the PDO. Do you expect to be able to predict the PDO beyond an AR1 process? As in, is the PDO more than an AR1 process?
Yeah, I think actually just from the line that I'm showing here, you can see that it's more than an AR1 process because your expected prediction skill would fall as an exponential, and it's not doing that. So there's some seasonality there, and that's because there are more processes that are predictable that go into the PDO index. And that's kind of the reason that I was looking at this, was because the PDO, as the first pattern of variability in the North Pacific, it's kind of encoding a lot of that information. And so this was kind of an idea to use this as a sort of proxy for North Pacific predictability in general. And yeah, like for the February initialization, as you can see, like it does better for quite a long amount of time.
Done a very, very careful job with looking at the correlations, and if I understood correctly, in space. Is that right?
This is the correlation of the PDO index. So I calculate the PDO index. Yeah, so I have the value, and I can project the PDO pattern onto each of the initializations, and then I get an index value at each lead time. That I have a predicted index value at each lead time, and then I can compare it to the observed value of the PDO index at each lead time.
Question.
Okay.
If you looked at the temporal correlations or just the spatial one. But thanks.
Yeah, this is very highly temporally correlated, which I'm showing by that alpha value there, which is part of the reason that you have predictability at such long lead times. So I haven't explicitly looked at that, but I think you could do that with an AR2 or AR3 model where you're including additional lead times and seeing how that improves your prediction.
And I'm just wondering if you think there's any reason to believe that a February initialization would give us better decadal skill. So November was chosen because but maybe PDO is more relevant for the United States. You can see that in February you have higher spring skill in year 1, comparable skill in year 2. Like, give us better decadal Pacific skill on multi-year lead times or decadal time.
Yeah, that's a really good question. This is mostly speculation, but if you are starting in February, you've basically given the model a whole winter to take whatever anomalies the atmosphere gave and have the ocean integrate that. And then you start at about the same time that the atmosphere is starting to put less information into the ocean at high latitudes. So I wonder if that is part of the reason you get such high prediction skill through the following winter. Versus November initialization, you're basically initializing at about the time where the mostly random atmosphere is getting strongest, and so the ocean is going to be integrating random information rather than the information from the observations.
All right, we now have a break until 3 o'clock, so please come back at 3 o'clock for a few more talks and some discussion. I have a regular check of the front page of NPR on my phone so that only I can see the picture, and I'm just checking to see if there's a mushroom cloud, and if there's not, then I'm like, okay.
Read on.
Yeah. Yeah, we got some campaign.
Yes. Which thing? Oh,
So you can
yes.
use this button to point. You can point at that screen actually.
Oh, okay. Oh, and it reflect. Oh, okay. That's great. It's not a real laser. Okay.
All right, in the interest of getting started on time, hopefully they'll also come inside. All right, our next speaker is Dylan Oldenburg.
Do you want me to already start? Oh, okay. Hi, so I'm Dylan Oldenburg, and I'm going to be talking about AMOC predictability in CMIP6 models today. Oh, the microphone. Can you, is this good? Do I need to lean in like this?
You might have to lean a little or move it up a little so it'll catch you better.
All right, is this okay? All right, great. And so the goal in this work is really to analyze the AMOC predictive skill in different CMIP6 models. So the AMOC predictive skill in CESM DPLE has been linked to Labrador seawater thickness, propagating at depth towards the mid-Atlantic ridge, where these anomalies accumulate and then drive predictable decadal changes in the gyrocirculation, the sea surface height gradient, and the near surface circulation, accounting for skillful prediction of the subpolar North Atlantic upper ocean heat content. And so the question is, does this mechanism found in the large ensemble decadal prediction of CESM1, does that hold in other CMIP6 models that have similar decadal prediction systems? And then of all these models, do the models that have high AMOC predictability also show high predictability in the subpolar North Atlantic? Oh, whoops. Do models, with high AMOC predictability also show high subpolar North Atlantic upper ocean heat content predictive skill? And so the goals of this work are to determine the subpolar North Atlantic upper ocean heat content predictive skill in CMIP6 decadal prediction models. And so there are many models that have data here. These are from hindcast runs, run from about 1960 onwards. So there are runs that are initialized each year and then run for 10 years each, freely run. And they're initialized from assimilation runs or observations. And the data sets they're initialized from also vary based on the model. And so we determine whether, as I said before, the high subpolar North Atlantic upper ocean heat content skill can be linked to predictable AMOC variations. So does the mechanism found in Jaeger 2020, does it hold in other models that also have high skill? And so to do this, we compute the AMOC either at 45 degrees north in density coordinates, or if we can, so for some models, if we can, we will compute the full AMOC stream function in density coordinates and use that instead. And then compute the subpolar North Atlantic upper ocean heat content scale in the CMIP6 decadal prediction simulations. And then we'll do that skill based compared to relative to EN4. That's going to be our observational data set that we'll compare skill based on. And then do an EOF decomposition of the AMOC. So is the upper ocean heat content, subpolar North Atlantic upper ocean heat content linked to the leading modes of AMOC variability in the models that have high skill? And is that differing in the ones with low skill? And then also, do models with stronger biases in the North Atlantic have lower upper ocean heat content skill? So some models may be initialized from data sets that are not very good, And so that might just lead to the variability also being wrong. And so we use all the models that have available data for all the variables we need. So we have quite a few different models here. CAN ESM5, for example. We have some medium resolution models like HAD-GEM3. And then we have a lot of low-res models. There are some other models, but they don't have quite the length of the simulation that we need. Some of them are just have simulations that are run to like 3 years rather than 10 years. And so the subpolar North Atlantic upper-ocean heat content skill varies greatly across these models. So there's a wide range of skill amongst the models we use, which is what we want. So this will allow us to more easily determine whether ones with better predictive skill and the upper-ocean heat content. So the definition of the subpolar North Atlantic region is this box here. And let's see, I can point at the box. And so yeah, we can more easily determine whether ones with better predictive skill and the upper-ocean heat content also have better Mach predictability. So these show the anomaly correlations, and that's the mean of the anomalies of the hindcast relative to the model climatology. And so this is just distilling those into dots. So basically the upper-ocean heat content skill in those boxes for each of the models for leads not 5 through 9. So smoothed over a 5-year lead time after the model simulations are initialized relative to EN4. That's our observational data set. And so we have a few high skill models. So the high skill models in this case are CMCC, CESM, CESM1 and CESM2, and then HAD-GEM3, the medium resolution. And then we also have some low-skilled models. We have CAN ESM5, and then FGOLS, F3L, and then BCC, CSM2, medium resolution. And then we have a bunch of models that are in between. So ones that have, I would say, are still fairly low skill, but some are kind of middling. Some of them actually just show the reverse of what we'd expect to find in terms of the variability, so that's interesting. And so another way to look at this is to look at the time series, so looking at leads 5 through 9 years, in this case for one of the models that's considered to be one of the better ones with predictive skill, so 0.5 anomaly correlation, yeah, so this is one of the good models, this is CESM2, the DP, the decadal prediction of that, the large ensemble. This one has, I believe, 40 members. And then this is one of the low quality models, CAN ESM5, which has variability that just doesn't have any alignment with EN4, with the observations. It's similar if you look at SST and compare it to Hadley SST, for example. It just does not align with the variability at all. Even at low lead times, if you just look at like the year that it was even initialized from, it's already quite poor. So in terms of trying to link this to Mach, the question is, so is the skill linked to predictive AMOC changes? So unfortunately, we don't have the full Mach stream functions for every model, but we can compute it at 45 degrees north. But the problem is that first of all, we don't have a great observational data set to compute the skill relative to. I mean, we can compare it to high-resolution FOSSI simulations, but it's tricky because the structures are quite different. The maxima are located in different places, so it makes it a bit tricky to just compute the skill. So the maxima are not co-located, for example. And so because of this, we can do an EOF decomposition. So rather than computing the skill for Mach relative to the FOSSI reanalyses, we can determine the leading modes of variability and then see whether that's linked to the upper ocean heat content, the predictive upper ocean heat content variability. So this is one of the high skill models. So this is CESM1, low resolution. And so this is the first EOF for pretty much all the models is just a broad strengthening of AMOC. But what we're really interested in is what Steve Jaeger talked about in his 2020 paper, which is this mode of variability that's linked to densification of AMOC. And so that's what's shown here, EOF2, which represents about 15 to 20% of the variance in the data. And then so in CESM2, we can also see that this EOF represents, EOF number 2 also represents a densification. And then when we look at a poor quality model, so this is one of the few poor quality models in terms of the upper ocean heat content that show, what was I saying here? This is one of the few where we have the full stream function, I meant to say. So this shows a similar mode of variability, except this is actually the first EOF. So it represents about 75, it represents a majority of the variance in this model, which is sort of interesting. And for the low skill models, unfortunately, we just have, for now, hopefully in the future, we'll have the full stream functions, but we just have it at 45 degrees north. And they also exhibit a similar, some of them also exhibit a similar mode of variability where you have, let's see, can you see? Oops. What's happening here? You have like a densification, so a strengthening at the denser areas and then a weakening. So you see that in some of the models. And so what I need, the next plan is to try to correlate these, see whether there's a correlation between this mode of variability and the upper ocean heat content variability. But I haven't quite done that yet. I'm still working on that. And in terms of the biases, this is the upper ocean heat content subpolar North Atlantic bias. Leads 5 through 9 years versus the upper ocean heat content prediction skill over that same lead time. And so there isn't really a clear, oh, whoops, sorry. Hang on. Yeah, so this is what I was talking about. But there isn't really a clear relationship. There are some that have fairly good anomaly correlations, fairly good predictive skill, but have quite large biases in that region. So the question is, and it's the same if you look at the upper ocean salinity. So basically, the bias in the upper ocean salinity versus EN4. And so the question is, maybe the control of the predictive skill is actually just linked to biases in a different region rather than the actual local bias in that subpolar North Atlantic box. Yeah. And so the next step is to determine the link between the leading EOFs and the subpolar North Atlantic upper ocean heat content predictive skill, and then to look at different regions, try to determine whether biases in other regions are really causing the problems with the predictive skill of the upper ocean heat content. And that's it.
The EOFs are going to prioritize maximizing variability in the overturning stream function, but it could be that there is some strong correlation between upper ocean heat content and some other structure that maybe is a mixture of the EOFs. I was wondering if you tried just like regressing upper ocean heat content onto the stream function to try to discover structures that might be predictable.
That's a good point. Yeah, I will also consider doing that. I'm still working on how exactly to, I was still working on how exactly to do the correlation. But yeah, that's a really good idea. Thank you. Hi.
Yes, as I remember Steve's paper in 2020, there was a whole line of processes in the mechanism to get you from upper ocean heat content to gyre spin up to predictability. And I was wondering, do you have any plans to look through the rest of those pieces beyond upper ocean heat content and
Yes.
trace that out? And what would the next pieces then be in that mechanism?
Yeah, looking at kind of the propagation of that deep dense water, and then also looking at the Labrador seawater thickness. Yeah, the plan is to kind of see whether that full mechanism is. This is just kind of the starting point of that. But yeah, to look at that full mechanism, just as you said, and see whether that holds in these different models, at least the ones with high skill. Yeah.
I was wondering, it seems to me like you're trying to find patterns that maximize skill. And it came to mind to me that maybe canonical correlation analysis might help. It's basically, I'm not sure if you're familiar, it's okay if you're not, but it's like UF analysis, but instead of maximizing variance, you're maximizing skill, and so you get leading patterns associated with skill, which might be useful for what you're trying to do.
Thank you. Okay, yeah, I'll look into that. Thank you.
Our next speaker is Jerry Meal.
Thanks. This is a title is a little bit different from what's in the program, but the topic is pretty much the same. So this all starts with a very large wildfire event in eastern Australia. Started in late 2019, went into early 2020, produced massive amounts of smoke that made it across the Pacific. And John Fasulo had a paper in 2023 where he showed that this smoke could actually affect the onset of the subsequent La Nina event. And just to recap those results, basically it starts here with the smoke in Australia. It makes it across the subtropical Pacific, doesn't get rained out, brightens the clouds off of South America. The brighter clouds reflect more sun. That means less sun gets to the surface. The SSTs cool. The cooler water makes its way up into the eastern equatorial Pacific. And Bjertnæs feedback spread the cool SSTs out to the central equatorial Pacific. So that was kind of the starting point of this. And what I'm going to be talking about today are what processes and mechanisms sustained that La Nina event for 3 years, because it went on for 3 years, which was kind of interesting. So we did 2 sets of initialized hindcasts in a little bit different ways. We did these initialized hindcasts as a sensitivity experiment. So we ran one set, the standard SMILE hindcast for 3 years, initialized in August 2019. Then did another set, initialized at the same time for the same 3-year period, but just included the effects of the observed Australian wildfire smoke from GFET. So the set without the Australian wildfire smoke, we call these standard SMILE, or the no smoke experiments. And the set with the observed Australian bushfire smoke emissions from GFET are the smoke experiments. And the thing about doing it this way is that you can look, because you're only changing one thing, you're only changing these smoke emissions. By differencing these 2 hindcasts run over the same period identically, anything that's different in those 2 are from the effects of the wildfire smoke. So you can actually try to isolate, at least in the model, what the effects of the wildfire smoke were. And the other advantage is by differencing these sets of, the same set of hindcasts over the same time period, by doing the difference, you remove the drift identically. It's the same drift over the same time period, so you don't have to worry about drift adjustment. So what happens is, if you look at sea surface temperature anomalies going for the CSM2 on the left and the E3SM version 2 on the right, years 1, 2, and 3 are the 3 rows there, starting in August 2019 to 2020. These are annual means. And you can see that in both the models, in the first year, as was documented in John's paper, you see this cooler SSTs forming. Then in year 2, in CSM2, you can see that the cooler SSTs are spread across the Pacific, same thing in E3SM. And by year 3, it's even maybe even stronger in CSM2, and also maybe a bit stronger in E3SM. A couple interesting things. First of all, both models sustain this La Nina event, just associated with the effects of the wildfire smoke for 3 years. But of course, the wildfire smoke is gone by March of 2020. So something else is keeping this going in the 2 models. The other thing is that you can see just by eye that the amplitude of the anomalies in the CSM are about twice that in the E3SM. And the reasons for that are several possibilities. We're still looking at exactly why that should be. Okay, so what's doing this? So hang on, we're going to go through a couple of feedbacks pretty quickly here, and it's a little bit complicated, but it hopefully will make sense, and I'm going to recap it in a couple different ways at the end. So we can start out, these are year 3 differences now, CSM2 on the left, E3SM2 on the right. The top row is precipitation for year 3 differences, and you can see, as you can expect, because this is a La Nina event in year 1, you get reduced precipitation over the cooler water, and because during La Nina events you're pushing, the stronger trades are pushing the warmer water over the maritime continent in the Western Pacific. That's warming things up over here and producing stronger precipitation over the maritime continent. You see that in both models. And of course, associated with those changes in surface temperature and precipitation, you'd expect to see lower sea level pressure over this western Pacific area, which you get here. The blue colors here are lower sea level pressure in the smoke experiments. That's in both models. Again, stronger amplitude in the CSM. And because you're getting the stronger precipitation over the maritime continent, that means you're getting stronger upward vertical motion, stronger upper level outflow. That stronger upper level outflow is going to descend in the eastern Pacific and strengthen the subtropical high. And so you see this, and looking at the 200 hectopascal velocity potential, indeed you see these negative velocity potential values means stronger upper level outflow in both models. And this upper level outflow that comes down and descends, and you get these upper level convergence over the eastern Pacific, and those are the positive values over here. Okay, so that's kind of the starting point of what maintains it, but then the question is, what is causing some events to make it to 3 years and other events not to make it to 3 years? So it turns out Bjerknes feedback is the big story that maintains it, and so we thought that was the case, obviously, because we saw that with the spun up Walker circulation, it's very strong. Once you get the Walker circulation going, it's going to keep going unless something makes it stop. And so we wanted to figure out if any of these ensemble members actually stopped after 2 years and didn't go on to 3 years. So what we did is we came up with the indices. We had a Bjerknes feedback index, just zonal surface wind stress anomalies across the equatorial Pacific, and a west-east SST gradient, basically western Pacific SST anomalies minus eastern Pacific. Plotted those in this top plot here as a scatter plot, and as you can imagine, it lines up pretty good for both models. In other words, when you get the stronger Bjerknes feedback, in other words, stronger trade winds, you get a stronger west-east SST gradient because you're piling up that warm water in the west. It's going to be cooler in the east. But the interesting thing that came out was we thought that we'd have that almost all the ensemble members, and each dot is another ensemble member. We thought they'd all be kind of clustered down here, and that the weaker events that were kind of fading out would all be kind of just weaker La Niñas. But actually, there's a number of events that actually transition to El Nino, and that's these events or the ensemble members up here in the upper right-hand quadrant. So when you look at the distributions across these, as you can imagine, because the ensemble average of the 30 ensemble members gives you this multi-year La Nina, when you do this binning based on Nino 3.4, these are La Nina events to the left here, El Nino events to the right, you get a preponderance of ensemble members that are giving you a 3-year La Nina event compared to El Nino, but some of these are actually transitioning to El Nino. So the question is, what's producing this transition in some of these ensemble members, and why do some of the ensemble members keep going into a 3rd year? So what we did was we composited the 5 strongest sustained La Nina events from that scatter diagram, and the 5 strongest curtailed events, or in other words, the El Nino events that ended up transitioning after the 2nd year. So in this plot, we've got these 2 boxes. The CSM2 is at the top, E3SM is at the bottom. This column on the left is the sustained events that went on for 3 years. The column on the right is the curtailed, or the ones that transitioned to El Nino. And we're looking here at year 2 and year 3 in both models. So year 2, the first thing you see that's different between the two is this area here in the north central Pacific. The events that transition to El Nino have a positive North Pacific meridional mode, and the ones that continued have a negative North Pacific meridional mode. In other words, these negative SSTs are kind of arcing down here from the North Pacific near Hawaii and getting into the central Pacific north of the equator. And you can see this in both models, right? So in both CSM and E3SM, you see that the ones that transition have this positive North Pacific meridional mode, and the negative for the year 2, and the year 2 then stays as a La Nina, and year 3 then they transition to El Nino. So that's kind of interesting. So that's apparently something going on there in the North Central Pacific with this North Pacific meridional mode seems to be playing some kind of a role. So what role could it be playing? Well, let's look at precipitation now for the 2 models, and this is for year 2. This is the curtailed events, and of course, as you'd expect, when these warmer SSTs are up here from the positive North Pacific meridional mode, you see enhanced precipitation. These red colors are enhanced precipitation, and the events that transition, the events that don't transition, you don't really see that, and you see it in both models. See in E3SM, you also see this enhanced precipitation over here. And of course, if you get enhanced precipitation over the warmer SSTs, that's going to be stronger upper vertical motion, stronger upper level outflow. And you're going to have some effect back over to the west, and you're probably going to get some descending motion over here in the west in the maritime continent, and that's kind of what you see. So if you look at 200 hectopascal velocity potential, you can see these negative values here over the warmer water and the stronger precipitation where the positive NPMM is, and you see a negative, still negative over here in the ones that are sustained into the third year. And you see that you're getting some anomalous descent, which you're weakening the anomalous low pressure north of the equator here, while it's really still strong here. And same thing over here. So you're weakening the sea level pressure, you're getting more descent over the maritime continent there just from this anomalous Walker circulation that's instituted by this North Pacific meridional mode. And of course that then has implications for sea level pressure, as you can imagine. So the sea level pressure, when you get this kind of stronger precipitation, lower and positive SSTs, you get anomalous low sea level pressure here, which are the blue colors. And of course then you're going to get some anomalous westerly anomaly winds to the south of it. You can see these little vectors kind of turning around there. And you see this in both models, right? You see this anomalous low with the kind of weakening of the strong trades. That's the one thing that happens. The second thing that happens is because you've got this kind of anomalous descent over the maritime continent, you're weakening this anomalous low pressure on this side. It's still strong over Australia. We still have this strong Walker circulation going on in the southern hemisphere between Australia and the southeast Pacific. But now you get somewhat weaker low pressure, anomalous low pressure, and that gives you an anomalous meridional sea level pressure gradient, which will give you anomalous westerly surface winds, which I've highlighted here with this black arrow, because the little arrows are kind of hard to see. And you see that in both models. And so, of course, when you get westerly anomaly surface winds, and especially weakened trades, that means you get downwelling Kelvin waves, you deepen the thermocline, the SSTs warm up, and you get the transition. And you don't see that in the ensemble members that are sustained. So let's go over this once to summarize it, and I'll say it again in a minute. This is now a schematic. So the top here is the kind of the onset, which I was talking about with the wildfire smoke that gets this going. In the ensemble members that are sustained to 3 years, you basically get this Bjerknes feedback, coupled feedbacks going, where you get this stronger trade winds, get stronger upwelling, push more heat into the Western Pacific. That warms up the maritime continent and Western Pacific area. That gives you stronger precipitation, lower sea level pressure. Stronger precipitation gives you stronger upper level outflow, stronger descent over the Eastern Pacific. Subtropical high strengthens. That gives you stronger trades. Stronger trades push more water over, and it just goes in this feedback loop, the Bjerknes feedback loop. And this can go on indefinitely in theory unless something happens to make it stop. And in the ensemble members where it stops, this is what's happening, at least in the models, is you get a positive North Pacific meridional mode. You get positive SSTs over here with anomalous low pressure, stronger precipitation. Anomalous Walker circulation gives you some descent over here over the maritime continent, which weakens the anomalous low pressure. Low pressure is still strong over Australia, so you still get the strong Walker circulation between Australia and the southeast Pacific, but now you get this kind of anomalous weakened Walker circulation coming the other direction. This gives you an anomalous meridional surface pressure gradient, which contributes to westerly anomaly surface winds, as well as the anomalous westerlies that would come in from this anomalous low out here in the central equatorial Pacific. Okay, so let's skip that, and just to summarize this one more time. So it's been shown that smoke from the Australian wildfires contributed to the initiation of this multi-year La Nina event. The main process that sustains the event is Bjerknes feedback. It connects strong trade winds across the equatorial Pacific. That acts to cool tropical Pacific SSTs. That warms sea surface temperatures to the west, increases precipitation in the Western Pacific, and that gives you stronger vertical motion and stronger descent in the subtropical high in the Eastern Pacific through the Walker circulation. And that just kind of is a sustaining feedback set of processes. But then processes that can end this, that can change this, break this kind of chain of coupled feedbacks, is if a North Pacific meridional mode forms in the North Central Pacific. That results in anomalous low pressure in the North Central Pacific with westerly anomaly trades, as well as this altered Walker circulation with a weak and low pressure north of Australia. That gives you an anomalous meridional surface pressure gradient, westerly anomalous surface winds in the Western equatorial Pacific, triggers downwelling Kelvin waves, and transitions to positive equatorial Pacific SST anomalies. So I hope you got all that. Thanks.
Thanks, Jerry. That was awesome. Did you say why for the members that did not have a sustained La Nina in the third year, why they had the warm PMM in the first place, or is it just chance?
Well, you know, you look at the literature on this, these specific meridional modes, and you may have looked at some of these too, and the best you can get out of it is that it's kind of randomly generated. There isn't any evidence that these meridional modes are generated by any kind of tropical teleconnections. They seem to be somewhat stochastic in nature, and that seems to be the case here, that some ensemble members just get them, they start out, and but more ensemble members keep it going out to 3 years. So I think the nature of and I didn't say anything about the South Pacific meridional mode, which is actually helping to keep it going, because you see that is really strong in the South Pacific. So I think the role of these meridional modes, there's literature that shows how they are connected to ENSO in various ways. But I think that's a real interesting area of research that it'd be interesting to kind of learn more about exactly what causes them, how they set up, and what sustains them.
The E3SM versus CSM results look quite different.
Yep.
Even in the local features that you were saying that they are similar, they are actually different. And then given the larger scale differences, aren't they going to actually impact all of these mechanisms differently in both models? And then, I mean, I guess, have you done a budget analysis of some sort to verify that mechanism is actually going on?
Well, I think the thing that was, when you look at the ensemble averages, you know, the signal in the ensemble averages in E3SM is so much smaller than E3SM is smaller than CSM. When you look at these composites of the 5 strongest and 5 weakest, that's when you really see that they're really similar between the two models that are transitioning to El Nino versus La Nina. Both of them have these positive North Pacific meridional modes. Yeah, they're local, but that causes these large-scale features, because once you start changing something in the tropical Pacific, then that affects precipitation, water circulation characteristics, and that can really change the way this works. And so that was when we were looking at why some of them transitioned, others didn't. The one thing that seemed to be different was that North Pacific meridional mode. So I think that's a really important part of the story.
Nice talk. Maybe I missed it, but what are the wildfires' role in the multi-year event? Like, all the mechanisms later made sense, but that's probably a chance for any La Nina event to sustain itself, right?
It could, yeah. Yeah, and there's, of course, multi-year La Nina events. There's been previous 3-year La Nina events, but I think there's been a lot of literature trying to figure out what sustains some of these La Nina events for 2 or 3 years. And this case was interesting because it looked like one of the triggers was this wildfire smoke, but then the wildfire smoke goes away, and then once it's going, then it kind of keeps going. And so that was kind of what led us down this road to see. And that's, you know, these are sensitivity experiments, right? So you're just looking at the effects of the smoke. So definitely without the smoke, the model wasn't getting it. So, but I think once the model got going, and then it just kept going, and enough of the ensemble members sustained for 3 years that, you know, it came out in the ensemble average. But then looking at these ones that transition, because that's the thing that kind of surprised us. We thought, well, it'll probably be the ones that were weaker, you know, they'd all be kind of La Nina-like, but they kind of, some would be really weaker, but some of them really transitioned to El Nino. And that was kind of interesting.
A really interesting talk. And I'm really interested in the effect of the meridional modes into the far western Pacific through the outflow. I also know that they can have an influence when they reach the equator, which would be more in the central Pacific. So I was wondering if you have any plans to look at, like maybe looking at some Hofmahlers and see whether or not you see influence in the far western Pacific versus the central Pacific at that time, to see what, like, the relative importance of those two mechanisms that can feed back onto ENSO.
Yeah, and you're right about this Western Pacific connection. This has always been a thing about these meridional modes that I've never really understood, because, you know, they talk about in these papers you read, they're kind of coming down across Hawaii, but actually they just kind of set up all the way across to the Western Pacific. It's not like you can see them really propagating. So I think that's a really good point, to try to figure out, you know, how they connect to the Western Pacific, because that's what they're doing in the model. So if they're in the model, we should be able to analyze it. So I think that's a good point. Yeah. Yep.
All right, our next speaker is Steve Yeager.
Okay, so I'm going to follow up from Judith and talk about this elephant in the room that we all know is there, but we try to sweep it under the rug, which is drift in initialized Earth system predictions. And I'd like to thank all the people I've been working with on this topic. I really started thinking about this more when Xian Wu was an ASP postdoc here, and it's kind of the culmination of that effort. So model bias poses challenges for initialized Earth system prediction. This figure from Jerry's review paper gives a nice visualization of what we're talking about here. So models are initialized from some observed trajectory in the black line, and these hindcasts drift away, and that drift is a function of lead time, and it sort of asymptotes towards this systematic model bias that you can diagnose from a coupled model simulation. But it doesn't go directly there. There's some overshoots, right? And so this unrealistic drift signal complicates comparison of uninitialized predictions with observations. And there are a number of effective methods to de-drift, reforecast to enhance prediction skill, from simple to very sophisticated, right? So that's part of the calibration of prediction systems, is removing this, recalibrating the variance of your ensemble. And that's not really the topic of this talk. The topic of this talk is the significant expense of those methods. They inhibit experimentation. What we'd really like to be able to do is do initialized prediction case studies and explore this full kind of phase space of perturbations we could make to physics, resolution, parameters, initialization. Like, we want to be able to experiment with initialized predictions, not just recalibrate this expensive set of predictions. So that's the topic of the talk. And I just want to start with this, this simple example. This is taken from a decadal prediction system using CESM1. But it would apply to any time scale from subseasonal to decadal. So what we have here is observations in black, in quotes, with this very abrupt signal in the mid-90s, this famous mid-90s warming. And then we have some historical ensemble from a coupled simulation, in this case CESM1. And we compute anomalies, and that's how we compare our model with observation. So the observed anomaly is just subtracting a climatology, and the historical anomaly is subtracting the model climatology, right? So you can get rid of the bias, and you can compare them in terms of anomaly. So let's imagine that we wanted to do a prediction case study of this event with our brand new model. We wanted to see, is this going to be a good decadal prediction model? So what we might do is we initialize from observations, and we only have this one little case study. So what are we going to do? How are we going to compute anomalies? We could compute anomalies from observed climatology. After all, we're starting the model from observed conditions. So this is what we would get, and we would say, this is a crap system. Like, this is not a good prediction system, right? And of course, that's not true. Most of the signal you're seeing here is drift. So how do we get at that? So this is method one. I'll refer to different methods. Method one is you assume the model has no bias, no drift. And of course, a pro of that is it's a very cheap method. But the con is it gives poor results when you're initializing a biased model from observations. So what we normally do in the initialized prediction world is we conduct a large set of reforecasts to estimate the model drift. And that is computed in this fashion. We have many different reforecasts that are a function of lead time tau that verify at a certain time t, and we do this with many members. And then we take the average evolution as a function of tau, lead time, over some climatological window where these forecasts are verifying over our whole ensemble member dimension. And this is what we call the model lead time dependent climatology. And it's a function of tau, and that's what we mean by drift. When tau is small, this forecast climatology is like observed. And when tau goes to infinity, we're asymptoting towards the model systematic climatology. That's drift. How can we estimate drift is the question here. So we normally do it this way, or at least this is the most common method. As I said, there's more sophisticated ones, but this is what we do across time scales. We compute this model lead-dependent climatology from our set of reforecasts. We compute forecast anomalies from that climatology. And this is simple. As you can see here, it's effective. In fact, this is a quite skillful decadal prediction system. That case study does predict an abrupt shift in North Atlantic upper ocean heat content once you perform this de-drift step. But the con of this method is that it's expensive. We have to do all these reforecasts. It's very labor intensive, definitely not good for initialized prediction case studies. So let's talk about efficient drift estimation. As I said, one option would be to use a companion uninitialized historical large ensemble to compute forecast anomalies. This is take your forecast and subtract, your systematic model climatology. And Jerry has written on this. This is a viable method. It's definitely promising for decadal forecasts when the drift has asymptoted for a large tau, but it's not good for short time scales that are sort of mid-drift. And it's not good for sensitivity case studies because you don't have an uninitialized large ensemble anyways. You've got some new system that you want to test out. So another option could be to use method 2, do a reforecast set, but with a really small ensemble size, right? So the expense of this method 2 is going to depend on M here. How many members are you going to include? And you could decide to include only a very small number of members. And then another idea that Xian Wu used in her recent 2024 paper, where she was looking at these decadal prediction case studies with initial conditions only in certain regions of the globe, and we weren't sure, well, is that going to affect the drift? Well, let's run a CLIMO-IC ensemble where we initialize from climatology everywhere and kind of use that as a de-drift method. So that's the idea here, is we're going to initialize the model from climatological atmosphere and ocean initial conditions, but we can't do that with the land and ice models from CESM because they blow up when you try to initialize them from a climatological state. So what we did in this paper and what was also done in Yaga's paper is you pair climatological atmosphere and ocean with a collection of land and ice states from n different individual years. So you kind of got this mismatch, right? That's what we call CLIMO-IC. And Xian Wu showed that it works really well. It kind of gives you the same answer as you would get if you had a full reforecast set. So we didn't actually have to do the CLIMO-IC experiment, but we didn't know that. But the fact that CLIMO-IC kind of gives you the same answer as method 2 suggests that that could be an efficient drift estimation method. All right, so this talk is going to focus on these two ideas, small reforecast ensemble or CLIMO-IC. And we're going to leverage this large reforecast set that we have that spans timescales from subseasonal through seasonal, multi-year, all the way out to decadal with large ensembles. And we're also going to throw into the mix the E3SM V2.1 SMILE that we have. And here's kind of the key point, which is the cost. If you use method 1, so you assume the model has no bias, then there's no cost, but it's not very good. So method 2 is standard, and the cost of that method is going to depend on the M that you choose, the number of members. So you can do the multiplication here. For S2S, it takes about 220 simulation years to estimate S2S drift. And method 3, which is this ClimOIC method, is only a function of how many members you include. So it's already, you can see, potentially cheaper than method 2. And then this is how we're going to quantify it. We're going to say if this alternative drift or lead-dependent climatology is similar to what we get with method 2, that means we've got a good answer. But we need to quantify, like, what does similar climatology mean in a more rigorous way. So we're going to use this mean square skill score, where here we're measuring the distance of our anomalies computed using an alternate method compared to method 2 anomalies kind of normalized by method 2 variance. It turns out that if you do the math, this is the difference between the climatologies that you estimate kind of normalized by expected variance of a field. All right, so some results. So this is what S2S SAT, surface air temperature bias, looks like in the CSM2 system for winter and summer initializations as a function of forecast week. This is something that Yaga has shown in her papers. Clearly very rapid bias development even in week 1. There is some growth of bias with lead time, you can see by eye, and seasonality too, very different in winter and summer. And I was going to point out here the color scale, -5 to 5. I'm going to keep that same color scale. And now I'm going to show you the difference in SAT climatology using alternate methods compared to this best method. This is what we use in papers, right? Method 2. So method 3 is the ClimOIC, and what you see is pretty large differences that really start to pop out in forecast week 2 all the way out through 4. Maybe not such a good method for subseasonal. It's on the same scale, so you're getting errors in the climatology that are of the same order as your climatological bias. That's one initialization with 22 members. Method 2 with 1 member is the same cost, but we get a much better estimation of the drifting climatology. So at least for subseasonal, it seems like this kind of low ensemble method 2 could be a viable method. Of course, as you increase the ensemble size, you get better and better, right? So you can always do better if you add more members, but even with 1 member, you're doing a pretty good job of estimating climatology, and then that translates into differences in skill score. So method 1, assuming no model bias, is not a good method. Method 3, shows these problems, particularly over North America and Canada. Method 2 with 1 member is pretty good, and I would say that this is a viable method for subseasonal prediction case studies. And then, of course, it gets better as you add more members. All right, now we're going on to seasonal timescales, and we've got 2 systems now, and I'm showing you the mean model bias as a function of forecast lead time. Clearly very different in these 2 models, and it's also a function of forecast year, so it doesn't stabilize for some time, and that's something that Jerry has shown in his papers. If you try alternate methods, this method 2 with 1 members is showing quite good skill for both systems, suggesting that this is a viable method to do efficient drift estimation even on seasonal timescales. And then let's put this into practice. Like, what if we wanted to do an initialized prediction case study for 97, 98 El Nino? With CESM2, we've got this red curve, which is our standard method. It's quite expensive. And this is what we think of as the true forecast anomaly. Method 1, not giving us good results, but these alternative methods are actually giving us very good estimation of the forecast anomaly for this event all the way out through 24-month lead times. And they're also working in this other system, although this method 2 1 member isn't quite as good with E3SM, and that may be because it's got more ENSO variance. I'm not sure. So whenever you've got more variance, you need more members to beat down that noise. All right, and very quickly, it also works on decadal timescales. So you do this 30 initializations with one member, and you get a very good estimation of your decadal annual surface air temperature bias. So this is kind of interesting, though. To do decadal prediction case studies, it looks, quite viable that we can get the same result as RED, which, as I said, is our true current method, using this method 2 one member, which is 1/20th the cost of doing a decadal prediction case study, and we're getting, indications that CSM2 decadal prediction is good at predicting this rapid warming and this rapid cooling in the subpolar North Atlantic. It's also showing decent skill at getting these IPO phase transitions that Jerry has highlighted in his work, right? This change from negative to positive and then positive to negative, and we can do prediction case studies like that much more cheaply than we have in the past. So it looks like efficient S2, S2D forecast drift estimation shows promise here, benchmarked against conventional techniques using full reforecast sets from both CSM2 and E3SMB 2.1. Indications are that both ClimOIC and this one-member method 2 work well for S2D at a small fraction of the standard cost, but initialization shock makes ClimOIC problematic for S2S. I didn't show the shock, but I'm happy to share that if you've got questions. And so these results can inform the use of initialized prediction framework for model development, testing initialization methods, etc. And in fact, we're doing that right now with the CSM3 model. And I included this because I made this plot during the high-res session this morning, and I thought it was cool. So we've almost completed this full set of CSM3 initialized predictions using this one-member method 2. So what we did is ran 62 sim years in total, all run in parallel, so quite cheap. And what we see is for this 97, 98 event, CSM3, showing actually a really good El Nino decay phase. It gets into the La Nina, but it doesn't sustain the La Nina as much as we would like. And it suggests, maybe there's some coupled feedbacks here in the summer of year 1 that are to blame, that it's just not maintaining that La Nina to the same extent that, for example, CSM2 did. So potential, for using this in practice. Thanks. I don't know.
Maybe less of a question, more of a comment. Maybe a fourth method worth highlighting is model analogs here again. I know we talk about this a lot, but that's one huge advantage of analog forecasting is you don't have to worry about the drift part. It doesn't work for all contexts and all timescales, but it could probably be competitive to one of these methods on seasonal and decadal. Well, maybe not decadal, but certainly seasonal, and I think we've talked about that before.
But how could you use an analog to get the drift?
You don't need the drift. There's no drift. You're already in the biased model state, so you don't have to worry about the drift part. So you don't have to, there's nothing to fix because you're already in, you're at lag infinity.
You can't do analog unless you have a huge library. So what would you do with CSM3 that's in development? Like, that's the whole conundrum, right? We have a new system that we don't have all of these simulations to utilize, but we want to test the predictive skill of that system.
Yeah, when you don't have a library, then you have to lean on these other techniques. But there's a huge initial cost to the analog forecasting because you have to build the training data set. But yeah, thank you.
When you showed it, I think in method 3, big biases develop over the land, and I forgot what you said you were doing with the land in method 3, but does that have tell us anything about these issues that we have with the land not leading to skill?
I think so, but I don't know. So what we're doing is with these CLIMO experiments, is we're pairing a climatological atmosphere and ocean with a non-climatological land and sea ice. And as you might imagine, they're not in balance, and we get initialization shock from that, right? And, this was a plot I put in the extra, but, how do we quantify initialization shock? And I've tried to do it this way. So I was looking at this one grid point over Canada, and if you look at the growth of ensemble spread in these CLIMO IC experiments on S2S timescale, so as a function of forecast day, you get this huge growth in spread. So you've got this hugely spread ensemble, and the spread goes outside the bounds of the spread that you expect when you pair component initializations that are at least in better balance. So it's I think any signal that you're getting from a really spread ensemble is inherently uncertain. So I think, this settles down eventually, but I think on these subseasonal timescales, you could be getting initialization shock effects, basically.
I think we should move to the co-chair update.
Yep.
And we're going to be a little short on time for discussion. So Steve's going to talk about some of the different kinds of experiments that the Earth System Prediction Working Group has. And if we don't get a chance to talk too much about them, we would really appreciate hearing any feedback you have on which ones you find useful, how you might use them, and things of that sort.
Yeah, sorry for going long. As always, wanted to bring the working group up to date on data sets that we have that are available. We've got these S2S experiments that we've heard about from Yaga's 2024 paper that are available. We've recently backward extended CSM2 SMILE, so now all these initializations go back to 1958. So that's a new development. I've mentioned before in past meetings, we've done these SMILE, CLIVAR, TBI coordinated experiments. So these are hindcast pacemaker experiments that are equivalent to SMILE, but with regional SST nudged to observations in the tropics of each different ocean basin. And there's now a paper out in GMD describing those experiments. CSM2DP has been available for a while, but one new development is that we're processing the time series files and getting those uploaded to CMIP6+. So that will probably be the easiest way to analyze this data set unless you're sort of an expert, because these will already be in time series format. And then we've completed CSM2 multi-decadal predictions. So these are basically an extension of CSM2DP every 5 years, and these go out 20 years. So we can look at, do we get initial condition predictability on these multi-decadal timescales. So super briefly, ongoing and planned allocation usage. You can see the ones that we've already completed, and then a list of, kind of ideas for how we're going to use up our allocation in the remaining, I guess, year and a half that we have. So you can read through those various time scales, including now CSM3 case study experiments. And I just gave you an example. I think we're going to be doing more of that. Maybe once we get a configuration that we like, put CSM3 to the test on these short time scale predictions. And then I just wanted to advertise this this open workshop that will be happening in November in Italy, but a hybrid option. So if you're someone who's interested in annual to multi-decadal climate variability and predictability, please consider submitting an abstract. Deadline 15th of July. So I think that was it, and now we can open it up to discussion for maybe 5 minutes.
I'll highlight the S2S CLIMO initialized experiments. We've heard a lot about those today. I'm finding them personally very useful in understanding sources of skill and trying to get at predictability. So if there's others who are using that or want to use those, maybe don't quite know how to get access to them or what to do, you can feel free to contact me. Steve, if you'll put that last slide up, just because it has contact information on it.
The last slide?
Yep,
oh,
the last slide, yes. So, oops, that's the wrong contact information for me. It is kpjoan@ou.edu. I've changed institutions. But feel free to contact me if you have interest or you know, would like to get access to those and maybe don't quite know how to get into those. And we welcome any other thoughts about the data sets, things you'd like to use, obstacles to accessing them, anything of that sort, experiments you would like to see. Quick, you only have a few seconds to tell us your experiments you want to see.
I was wondering if you had any plans to, like given all the talk about AI/ML that's going on, are there any plans to try to use that in some way for prediction in this working group? Or is that happening elsewhere, or is it not happening, I guess?
I mean, that's happening definitely at NCAR, and Will Chapman and Judith Berner have sort of ML-based parameterizations that they're testing out in S2S framework, so I don't see either of them here, but yes.
Okay.
I think that's a fair question. I mean, I don't know the answer to this. Is there an effort around a machine learning version, AI version of CESM? I would love to see some of these machine learning emulators run like following the reforecast protocol that we could evaluate consistent with other reforecasts would be amazing.
All right, if no other, or Dylan, you want to take the last word?
I feel like I bring this up every year, so I might as well do it one more time. Any plans down the line for a higher resolution initialized prediction system in CSM3? Like, I think we've talked at some point about like nested high resolution grids with initialized prediction, or something in the Mesa Clip domain for very limited time periods.
Point 3, Mesa Clip decadal predictions. And in addition to what Steve led, so we have now 1980, filling it every single year, all the way to 2024, well, 2023, I guess. Ensemble members each, 62 months each, and 2 start dates per year, November 1st and May 1st. So the ones that in Steve's paper, all those simulations are available, but they're every other year and November initialization. So now we are doing it from 1970 or 80, I think, 80. And so they will be available as soon as the simulations are still running. So there is actually a decadal, 62-month equivalent of some of these simulations with CSM 1.3. And we have plans to run when the CSM.
All right, let's thank all our speakers and thank you.
Check, 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 check. Check, check, check.
enthusiasm on at the end of day 3. Yeah, so this is very informal. We've tried many things over the years to figure out what to do with this final session, but I think just an open question and answer session is the best. But I just wanted to do a few thanks and wrap up things before we get into that. Any idea why it's not moving forward? Okay. So first, I just want to again express thanks, and this is a more comprehensive and detailed list of who was involved. So, for the workshop organization and support, our administrative team: Elizabeth Fairclough, Daniel Sena, Kaylin Kampert, Kayla DeBellis, and Teresa Waltz have done a ton of work. You've seen them out there shepherding everybody around to the right place at the right time, helping people out, presentations, et cetera, and really organizing the event. Like the event that went last night was great. And everyone put in a huge amount of effort for that. It was, a special thing. And of course, UCAR Multimedia makes this all run seamlessly. It's not trivial to do that. So really thanks to them. And just again, a thanks to the U.S. National Science Foundation for providing support for especially some early career travelers, and for all the CAB and SSC and working group co-chair members who traveled. So thanks again to everybody. So let's have a round of applause. A couple of photos from the week, I guess. So I forgot to mention to thank the band yesterday, but there's the band, some great plenary speakers, all the good conversations, all the group, and especially the chief scientist. That was really fun. And well, there's Elizabeth and I being a little silly. So really, again, thanks to everybody who participated, and thanks for being here. It was a really fun meeting, I think, considering the circumstances that we're currently in. And this actually is now duplicative of that previous slide that Elizabeth put in since I said. So the last thing I just want to say before we move to question and answers is just a reminder about the CSM use and impact survey. A bunch of people have filled it out already. We have 60, 70, something like that. Our responses, including some from private industry, government agencies, and things like that. So this is super important. We're not going to ask you for any other surveys right now. So there's not going to be like a, how did you like this workshop? This is the most important thing right now. So please fill it out, or ask your colleagues to fill it out, or send it off to the people who you think might have some influence, and ask them to fill it out. So we're really going to take this information and try to bring it forward as we, try to find alternative ways to make the case for ongoing CSM activity. So please make an emphasis on this. So yeah, now, questions or comments. This is really an open forum for you to raise any questions that you have related to what happened during the meeting, or just in general what's going on with CSM. If you have suggestions for things we should be doing that we're not doing, or we could be doing better, those kind of things, or just general comments about, let's not go as far as the state of the world. That's probably too far, but general comments about what's going on with CSM. So please, anyone who wants to get up and also if you're online, use Slido to ask your questions. And who's monitoring Slido? I forgot to assign somebody to that. Elizabeth, Elizabeth will look at that. To break the ice. Here we go. Thank you, Ollie.
Yeah, just thank you for all for this amazing workshop. Just kind of a suggestion. I was thinking, I really like this, like opposite like AG or something. It was like really overwhelming, but that was very target and very nice. But still, I think that would be maybe. But if that would be like kind of introduction or kind of abstract at what gonna be discussed in that session, like in plain language, or like kind of, we're talking about open science, like science communication. Would be good practice maybe for us, like to have something like that in the beginning. And if somebody is like other field or not much familiar with that field, that would be good, little bit warm up. I would suggest that one, yeah.
Thank you. That's a really nice suggestion. We kind of forget, those of us who've been here for 30 workshops, and not everybody's up to speed with everything that's going on, and that's a really important thing to remind us about. That's a good idea. Let's try to remember to do that for next year, for sure. We want new people to be coming here and feeling welcome and engaged, and so that's an important part of it. And honestly, you know, I don't know what's going on in all the working groups, and I'm going to sit down in a new working group and be like, okay, what is really going on here? So that's really helpful. Any questions? Yeah.
I had a quick comment about something as well, because this conference we saw a lot of things about science communication and how that's important. I think it would be a really fun and interesting thing to have a small session where people can have a 5-minute talk, which is just layman language, explain your research in 5 minutes instead of science talks. I know that's not the purpose of the CSM workshop, but if SciComm is important, I think it would be a good idea to have that. Thanks.
Yeah, I think it came up several times during this workshop. Paula really stressed this in the opening plenary. Jeff stressed it yesterday. Science communication, super important, and you know, all of us have an opportunity to learn better about how to do science communication. I like that idea of having just one session that's focused on you know, people trying to play with their ideas a little bit to see how they want to communicate their science. A bunch of really short presentations. That's a good idea. So we'll try to write that down and think about it. And you know, in the same vein, you know, this year we changed the format just a little bit. We had the celebration, obviously, but you might have noticed the working group lengths were not all equal. And this year we asked each working group how much time they wanted to have, and we let each working group choose. And we'll do that again next year. And then we have these cross-working group sessions, which have been really good. And currently, it's the co-chairs who tend to put forward the ideas for the cross-working group sessions. This year they were sort of obvious. They popped out obviously, but sometimes it's not clear what we want to talk about. So we're always happy. You know, contact your co-chair and tell them an idea you have. You know, we can only come up with so many ideas ourselves, so it's really nice to have like a fresh idea like that to bring forward to next year. And I'm also open for ideas about how to, you know, revamp the conference even more significantly. I mean, I think this year was really nice. We don't have to keep the same structure every year, so that's. But thanks for that suggestion.
Think of something, you know. Obviously, from all these people here, there's lots of papers and publications in science journals and things like that. But I don't remember seeing something in a high impact place about CESM as CESM. And maybe with the 30th anniversary, it's time to do that. And maybe it's a good way to try and, I don't know, advertise to the world the value of the scientific collaboration.
That's a really good idea. I think we could do something like, yeah, that's an excellent idea. I really like that. I'm not sure of the venue, but you could imagine us describing this workshop, some of the celebration stuff we did, and the CSM Impact and Use Survey may really turn up a bunch of like things that would be worth covering in that sort of review. So we could maybe expand that to be a little bit of a history, and then here's what the impact of CSM is today. I like that idea a lot. So yeah, I'm glad you're going to take on the lead of that activity. Peter.
I thought Michael was going to say this, but he brought up the idea of societal dimension working group that we had previously. And, you know, we keep on talking about having actionable and, you know, useful science coming out of it. Maybe it's time to revisit, like, having that as like a theme that works through CSM, like try and have a way to coordinate the impacts analysis we're doing, how we're communicating with stakeholders, you know, making the model really responsive to those needs. And just throwing it out there, maybe time to rethink that again.
Yeah, thanks. And I'm sure you're aware, you know, we have had several cross-working group sessions over the last 2 to 3 or 4 years that have focused on this, but we haven't like formed something that's sort of lasting year to year. Yeah, I agree with you. It's important. Yeah, as you know, like getting everything fitting into this 3-day period already feels quite intense. But maybe we need to focus on doing that. Yeah, good point.
It would be helpful to have the posters out for all the 3 days rather than just the 2 hours.
Yep. Yeah. 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 This unfortunately, I mean, Elizabeth, if she's wherever she is, this is like I mean, it's nice to all be here together. It kind of works out, but this is really a terrible location for logistics for a meeting. But maybe not terrible. That's pushing it too far. But posters are hard here. But yeah, that's a good point. I think we could at least try to keep them upstairs. Down here, it gets pretty tight with everyone when everyone's here. But yeah, that's a good point. Thanks. And is somebody taking notes on this? All right, I'm going to try my mental notes on things that we might forget.
Maybe we could also think about lightning talks for the posters.
Yeah. Danielle.
Yeah, thank you. First of all, thank you, as always, for organizing. This has been great. I wanted to really support Michael's point. I think that this could be a good moment in which both the CSM community and the university community highlight the importance of CSM in the past, in the present, and potentially in the future with all new things. So normally, BAMS is the perfect place where to do something like this, right? A meeting report, but also like a very focused piece that makes a point that CSM is going to be relevant and important in the future as well, and the US needs to keep supporting it. That'd be really super supportive of something like that.
Yeah, I mean, BAMS might be a nice place. We might try to go for something even higher, you know, like see if we could get it into a perspective for something like nature. But yeah, BAMS is definitely an alternative. I like it. Yeah, the past, present, and future of CSM. Yeah, it's a really good idea. We should really try to make this happen. Yeah.
I was wondering whether you could shed light on the chances, concerning CMIP, whether, we as the CSM community can participate in CMIP this time around or not, and what are the considerations? Maybe you can shed light on that.
Yeah. Yeah, I'm surprised there wasn't a question yet on that. And anyone who was paying close attention might have noticed I didn't really mention CMIP in my overview, which was a little bit, which kind of reflects a little bit the uncertainty that at least I have, I think a lot of us have, about how to proceed. But I'll say one thing, where we've had no specific guidance from NSF, from NCAR, from anyone, as far as I'm aware yet, about whether to or to not participate in CMIP. So as of now, I think it's our decision. That could change, right? That could change. We could get specific guidance. So then it's our decision. So we are, John, myself, others are having conversations with people frequently to try to get the understanding of what people think about the potential risks, obviously, of doing CMIP and the potential risks of not doing CMIP. What I got during this meeting, perhaps not surprisingly, is that this community would like us to do CMIP, I think. The research community would like us to do CMIP. The value of CMIP continues to be high, especially, I mean, it may not be all of CMIP, but definitely, running the deck and the scenarios has such a big impact. So I've kind of knew that already, but I've heard that message at this meeting for sure. So we're going to talk about this more tomorrow with a joint meeting of the co-chairs, the CAB and the SSC, to get more opinions about this from a wider suite of people who can, be speaking freely. And I think we're still in the position that we don't have to decide just yet. And because, things are so fluid, things are changing so quickly, it feels like any decision we do make we're going to have to revisit it. So one of the things we're going to do tomorrow and over the next several weeks to month or so is try to put some timelines on ourselves to make the decision go or no go.
I guess related question, and is CSM3 ready by then when the decision comes?
Yeah. So we are proceeding as if we're going to run CMIP in terms of development. But yeah, we are trying to finish CSM3 to be able to be ready to run CMIP. Now we are clearly not achieving those goals, but but the philosophy is, we may. I have confidence in our team, but you know, as you saw, there's things that aren't going well, but I'm starting to feel like we're turning the corner. But yeah, what I didn't really talk about was too much was like the workflow stuff that we're doing a lot in the background. I didn't spend much time on that, but we're spending a lot of effort on CMIP kind of workflow, which is going to have benefits beyond us running CMIP or not running CMIP. It's going to make everything, the whole process easier. We're working on the CMIP forcing data so that, you know, we need to be able to do that so we can at the very least run up to present day, you know, with realistic forcing. So there's other reasons to do it. So we are taking all the steps to try to be ready. If that makes sense. And I'm happy to hear opinions from everybody. I'm not like doing a statistical analysis of all the opinions, but I do like to hear what people's perspectives are because it helps inform the overall picture, right? And I'll be honest, I think there's probably people in the room who want us to run CMIP and we're also scared a little bit about the potential impact of running CMIP if, you know, if it comes back around. So that's why the decision is non-trivial.
Just going to add one thing because it's probably obvious to you, but maybe not to everyone, that we will release a model and we will produce data sets with that model, even if we didn't do CMIP. And some of those might be very CMIP-like, even if we didn't do CMIP.
Yeah. And there is the alternative if we decide it's not in our best interest to run CMIP, that some other entity will run CMIP for us. That there's many people who have offered that. There's no way that's not going to be an effort that we're going to have to participate in at NCAR. I think it's almost impossible for external groups to run CMIP without our help. But Europeans have offered, several institutions around the US have offered. So I think that's another alternative that we're thinking about.
I'll just put my vote in. If they don't tell you not to, I really hope you go and run CMIP.
Thank you.
And I mean, I'm going to repeat what I said what I'm going to say tomorrow at the kosher meeting. I really think that the way to go is through a consortium of universities that can run what NCAR cannot, or maybe should not. But it really should, but two things. It should be both, not just one institution if it's not NCAR. And also I really think it would be an incredibly terrible signal to have this done in Europe with CSM, considering that all the other US models are in a worse shape potentially. So I would strongly advocate, and I will try to do that in any way possible, for a consortium of universities to do broader CMIP in any way possible. But it would be really important to have this done. So.
That's a good point. It's a fun topic.
But there was also the question if we run CMIP, if we don't run CMIP, as an institution run CMIP, where the data, the original output will be saved, and I don't know.
That's part of the thing you have to figure out. Yeah, for sure. This was the, you know, we've done surveys before. I don't know why I just thought of this, but, you know, how much do you guys care about whether CSM3 is a good model or not? You know, because we've done the survey before and they said, you know, what we really want is an easy to use model, and that was the highest priority. And then the quality of it was like the lowest on the list of so if that's still true, I think we're ready. No, we're gonna produce as good a model as we can, obviously. Any other comments or questions? How do you like the balance of things that were discussed at the meeting? And good. I do think this is a fun meeting, right? It's a model development activity, but there's a ton of science. I mean, the amount of science, and of course model development is a science in and of itself, is really impressive. It's really extremely rewarding to be able to sit up here and you know, be able to appreciate and see everything that's going on from the work that we're doing. So that's really exciting. It's very motivating. if we didn't already have motivation to get CSM3 done and make it a good model, this was motivation. Cool. Anyone else want to? Peter, go ahead.
I was just going to say, I really liked when we had the biogeochemistry and the polar working group together, like yesterday morning.
Yeah.
I thought it was really great. And sometimes I think there's this overlap between working groups and allowing to have a little bit more flexibility. Because yesterday morning, I guess there was 3 working groups I really wanted to be in, and like, you couldn't be in them. I know we got YouTube videos of all this is great, but having those overlapping is really a positive thing.
Yeah. Yeah, it's a good point. And I actually just had a really quick conversation with the chemistry working group. There's a lot of overlap between BGC and chemistry this year. I think there were 2 like really related fire talks going on at the same time because I was getting texts from the other room about what they saw. So, I think we can be creative about that. And I think we don't always have to have 3 parallel sessions. We can do 2, and one of them can be a joint working group for part of their time. So I do want to revisit that next year, and maybe we can think about it, several sort of joint, 2 working groups together going off at the same time. But yeah, absolutely. There are definitely times that I wanted to be in all 3 rooms at the same time this year.
I just wanted to express gratitude for the initial plenary session as well on the first day with Paula, Hansi, and Michael. I thought that was a really cool application of CSM, seeing it outside the academic sector, and I would, put a +1 for having something similar next year. I think it's important to highlight in these times, the reach that CSM has beyond just the academic sector, and I thought that was a really effective way of doing it.
Great, thank you. Yeah, I appreciate that. I've heard quite a few people come up and say how much they enjoyed that session, so I'm glad for the positive feedback, and we will, I think we'll almost certainly be trying to carry forward some element of that type of discussion, whether it's in plenary or whether it's a cross-working group session or what, in most years, because I do think that's important. Why are we doing this? It's for the impact, so absolutely. Thanks a lot. Great. Seems like that's about it. So thanks everyone for coming. Really appreciate it. Hope you had fun. I enjoyed it, and we'll cross fingers. We'll see you all again next year.